see my screen at any rate. Thanks, Lale. Morning, everybody, and welcome to our course this morning. Just as an introduction, I would like to remind all of those who are not yet members of the GSSA of our various membership categories. And student membership is free, so please do take note of that. We have the normal corporate membership and also the corporate membership with chartered status, which refers to those who want to use their GSSA status to sign off on public reports. We also have various affiliate and institutional membership categories. Along with that, other benefits of GSSA membership: continuing professional development. All our courses are accredited for CPD points, either with the GSSA or with SACNASP. You get the SA Journal of Geology, which is an internationally recognized and accredited journal. We also have various mentorship opportunities, both for mentors and also for mentees. Just a quick rundown of the events for 2023. This is where we are currently sitting here. And just to bring to your attention the various other events that we have later in the year. Our next one up is the Base Metals Day. You will find links to register for all of these on the website and also in the Monday mailers. So today we have the introduction to drilling course, your various presenters, and I will put a detailed CV of the speaker into the chat box momentarily. This is our program for the day. We'll start off with Colin Rice about drilling itself, and then we'll move on through the other various presentations. And I'm rushing through this because my internet thing is very weak this morning. Thank you to our annual sponsors. Without you, nothing would happen. Everybody, please keep your video and your mic off during presentations. Video so that we can handle the bandwidth, and microphone because it's extremely annoying if you're presenting and you hear other people speaking in the background. If you want to ask a question, please raise your hand. There is also the chat function where you can type a question that can be answered. There are CPD credits available once you have completed your assignment. There are 12 credits for GSSA and 1 credit for SACNASP. Important also is to make sure yourself correctly on the participants list, because if we have you as private or the name of your phone, you cannot get CPD credits. Okay, your assignment. We want to make this relevant to you. So what we need you to do is to give us a 1-page summary of important points for each of the presentations. In other words, I'm expecting 6 pages from you, 1 page for each presentation. It can be essay style and or bullet points. But don't think you're going to do it in 16-point text and double spacing. You will get the recordings and the PDFs so that you can catch up on anything that you may have missed. Do we have any questions so far about the assignment? I will talk about it during each tea time and again at the end of the day as well. Okay, so without further ado then, I'm going to introduce you to Colin Rice, who is our first speaker up this morning. Colin is was a founding partner of SA Mud Services and managing director of professional diamond drilling equipment for 11 years when the company was acquired by Atlas Copco. In 2009, Colin established Colin Rice Exploration and Training, and he works extensively with a number of local and international mining and exploration companies. He has presented drilling-related training courses for the GSSA since 1992 and is an honorary fellow of the GSSA. So, Colin, all yours for the next 2 hours. Looking forward to it as usual. Thank you.
Thank you. Thanks, Tanya. Thanks very much indeed. As Tanya said, I've been involved in the drilling industry for a while. I've been working with the GSSA for more years than I care to remember, and it's absolutely wonderful to be with you guys today. This is one of the nicest programs. I think it's great that the GSSA do this on a no-cost basis, and I really look forward to this day every year. I'm tasked today with kind of summarizing what a geoscientist, in the past we called them geologists, but now what geoscientists need to know about drilling. And so in the next 1 3/4 hours, 2 hours, I'm going to try and summarize for you what I think a geo needs to know about drilling. Before I do, let me just pause for 1 second, if I may. A number of years ago, as Tanya mentioned there, a very large international company called Atlas Copco bought my business from me. For a few years, I worked for them, and one of the jobs I had to do, one of the projects I had to go to do a presentation to a very high-level board in Atlas Copco. And I prepared my presentation and then ran through it with one of the vice presidents. And he said to me, hang on, stop. I'd started my presentation, stop. And he said to me, nobody knows who you are, tell them who you are. So I thought, what a waste of time. I've got such a short period of time to get this presentation across. It doesn't matter. So I went to do this very high-level presentation, got stuck into it. I was 3 slides into my presentation, and one of these guys said, stop. He said, who are you? And so this guy was right. So what I'd like to do, just very quickly, just to give you a little outline of my path in the exploration industry and how I've landed up where I am now. Very, very briefly, it'll take me 1.5 minutes. I started my working career as a maths teacher in Zimbabwe. I taught a senior school maths for about 8 years, 7.5 to 8 years. In 1984, I moved to South Africa with my wife and my little 2-year-old daughter and a dog and a cat. And I did not want to be a teacher anymore because teachers were earning salaries that were below the poverty line in those days, pretty much still are today. And I got offered a job as a development chemist with a mud company, a company that made fluids that were used in drilling. It was a brand new industry in those days, and I did my degree in maths and chemistry, and so I got this job as a development chemist, and that got me into the exploration industry. So my foundation was in drilling fluids, drilling mud, getting people to use these different additives that have now become commonplace in every single drilling operation. And later on today, you're going to chat to some guys from Imdex who run a mud company. They manufacture drilling fluids. From there, I migrated into myself and my business partner in those days started a borehole surveying company. We became the only contract survey company in Southern Africa. In other words, we would go out, and once you drilled a borehole, we would survey that borehole and tell you where the borehole had gone. That now is just a massive business. And again, you're going to chat today, later on today, with somebody who's going to talk to you about borehole surveying and borehole logging. And then from there, we migrated further, and we bought so excuse me one sec. We bought an equipment manufacturing business. It then became one of the biggest manufacturers of exploration drilling equipment in South Africa. So I'm very lucky in that I've worked through different sort of facets, if you like, of the exploration industry. And through all of that, a lot of the work I've done in recent years has been with mining companies. And very often the work I do is to help sort out problems or misunderstandings between the mining company and the drilling contractor. And I believe that a lot of the problems that we have is because geologists don't understand contractors, and contractors most certainly don't understand geologists. And so you have this disconnect, and so you have issues, you have problems that occur. Now, I believe that, sorry guys, just give me one sec. I believe it's critically important for geologists. Sorry, can you guys still see my screen? It switched off there for a moment.
Yes, can see.
Okay, cool. Sorry, give me 1 second, guys. Sorry. My computer had a mind of its own there for a moment. And so I believe it's really, really important. It's critically important that geologists understand contractors and contractors understand geologists. And unless you have that understanding, you're going to have problems. So what I want to talk to you about today is based on a number of years of working in industry is where I think some of the gaps are, some of the places where geos can improve their learning, can improve their understanding, and so improve their ability to manage a drilling project. Okay, so that's what I'm getting at. We've got 2 hours. This should take about 2 weeks to talk about what we're talking about here. So I'm going to really compact it, but hopefully it'll give you at least an introduction into what we think a geo. Okay, let's start. We know that all geological information is based on rocks and understanding what's in rocks. And so rock samples at depths can only be obtained by drilling. And so by default, geologists must have a good understanding of drilling as an art, if you want to call it that, or as a scientist. It's one of the core competences of a scientist, of a geoscientist. Now we know that we can produce core samples or chip samples using a number of different drilling methods. We'll talk about some of those later on today. And the choice of drilling method will depend very much upon the stage of the project, whether it's an early stage or late stage project. And very often I come across situations where geos have an incomplete idea of what a different drilling method can produce. And so they want to produce these fantastic results from a method that is not going to give you those results. And so I think it's really important for geos to have an understanding of that. In early stage projects, a chip sample will be okay. And so we can use a rate percussion or an RC method to produce our sample. But in later stage projects, we must have a core sample. And so it's really important that geos have a good understanding of how we produce those core samples and the factors that can affect the quality of those samples. So I believe that the objective of any exploration drilling project is to produce samples safely and efficiently. And when we talk about samples, we're talking about a representative sample. In other words, I want a sample that truly represents the formation that I've just drilled, and it must be from a known depth. That is so easy to say and so hard to get right. And I would argue based on some of the work I've done in the past, that many boreholes are not the depth that you think they are. Contractors either over or under report depth. And so it's very important that when we talk about this term representative sample, we're talking about the in situ representativity of the formation and the depth of that formation, of that sample that we've obtained. So if you look at this little definition, now there's three aspects that come out that affect you as a geo. Number one, quality. Number two, safety. And then three, efficiency. So a geo is involved in making sure that all three of those aspects are managed on their project. So to look at it, a geo needs to know about technical aspects of a drilling operation. In other words, how do we obtain that sample? Have we selected the best method to get our sample? And what factors affect the quality of the sample that we obtain? Are we getting the best quality that's possible? Is the contractor doing a decent job for us? Or are things falling through the cracks? In terms of economics, a geologist needs to understand about the costs of drilling. How much does it cost to drill? And what can the geologist do to minimize the cost, or more importantly, what can the geologist do to help the contractor make a profit? Now, that might sound a little bit contentious, but I'll explain that when we get down to the last part of today's session. What can a geo do that can either help the contractor make money or make him lose money? It's very important you understand that, because if you make him lose money, your project is doomed for disaster. I guarantee it. And then the third part, which is probably one of the most important, is safety aspects. In many regions in the world, in many jurisdictions, and most certainly in South Africa, geologists have got a very important role to play in terms of safety. And in fact, in some cases, geologists have a legal responsibility for safety. So I believe geologists, purely and simply because they're human beings and they're on a drill site, they need to be able to identify hazards and identify controls to prevent people getting harmed, to prevent people getting injured. And very importantly, they need to understand what their legal liabilities are. I've just read a really interesting article a short while ago. I went down to make some tea, and I was reading on my iPad here in Australia, a company, two people who own a company, it's an industrial company, have just been sent to jail for fairly long periods of time for not reporting an incident. Basically what happened was the guy was painting in a confined space. It was in a ship, in the hull of a ship, doing some painting using a toxic paint, wasn't enough ventilation, and the guy passed out, and he was quite ill afterwards. They didn't report it. The same thing happened again, and the guy got seriously brain damaged. He's in serious medical trouble, and they tried to hide it. Now these two guys, they're two brothers, in fact, who run this company, try to hide the thing. The law's caught up with them, and they're both in jail now. And I certainly don't think that geos will get themselves in that sort of trouble, but you need to understand what your legal responsibilities are. And so we'll talk a little bit about that later on. So I believe there's three major areas that I want to talk about today. I want to talk about some technical aspects of what a geo needs to know. I'm going to talk about some economic aspects and some safety aspects, and try and just encapsulate what I think you need to know about the drilling operation. So let's start. Let's look at the technical aspects first. Okay. Now, guys, what I'm going to go through here, we haven't got a lot of time, so I'm really giving you some broad brushstrokes here. Okay, but at the end of this little presentation, I'm going to show you some places you can go to get some more in-depth knowledge, because guys, I cannot stress strongly enough. The more a geologist knows technically, the more you understand about a drilling operation and how a sample is produced, the better job you can do in managing that project. in managing every aspect of that project. So I encourage every geo and people, some of you, I recognize a couple of names on the screen earlier when everybody was joining, a couple of guys who I recognize on courses that we're doing, some of our online stuff. And I say this all the time. As a young geo, when you go to a drill site, don't go to a drill site and talk rubbish and have a cup of tea. Watch what they're doing. Watch the operations. Try to understand. Ask questions, and try to understand what is going on. It's only by understanding those processes that you will understand what you can do to improve that operation in terms of those three aspects that we've spoken about. Okay. So drilling is the process of making a hole in the Earth's crust. And the whole idea is that we make this hole, we want it to remain stable so that we can do whatever we want to do in that borehole. And that hole that we've created, that void in the earth, we call that a borehole. And there's many different methods that are used to drill boreholes. And this is one of the most important things that I want you guys to understand. We generally tend to think that every drilling method, every way of making a hole is different. They're not. They're very, very, there's a great deal of commonality, many aspects of drilling across many different methods of drilling that are the same, with the same essential features. And that's what I want to talk about now. In every drilling operation, here I've said rock drilling operation, any drilling operation, if you're drilling a hole in the wall to hang a picture up, we have the same fundamental principles. And guys, at the end, this understanding is critically important. In every drilling operation, we have a drill bit. Let me try and get smart here with some of my things here. Give me 1 second. So we have a drill bit. And that drill bit is connected via a drill string to a drill rig, which is sitting on surface. So in every drilling operation, it doesn't matter what depth we're drilling, where we're drilling, how we're drilling, what we're drilling for, we have those two components. And the drill string is made up of a number of different drill rods all screwed together. They might be 1.5 meters long, they might be 3 meters long, they might be 6 meters long, they might be 9 meters long. And we join them together to make the drill string. And the purpose of this drill bit, the sole purpose of that drill bit, is to fragment rock, is to break rock. That's the sole purpose of the drill bit. And we will choose different types of drill bit for different formations and to produce different types of sample. You'll see that just now. So all the drill bit does is it breaks rock. It creates fragments. It fragments the rock. And the drill string, all the drill string does is it provides a means to get rotation to the bit. It delivers torque to the drill bit, and it delivers weight on the bit. It allows us to push down and provide weight on the drill bit. So every single drilling method you'll come across has exactly those same features. It's got a drill bit that makes the hole, and it's got the drill rods that are connected to the drill rig. In every drilling operation, we have a drill rig. The drill rods, the drill string is connected to what we call the rotation head. It's the part that allows the rod to rotate. We rotate the drill rods, and while we're rotating, we apply load to it. We push down, we apply a force, a downward force onto the drill bit. And that combination of rotation and load, what we call bit load, we'll talk about that just now again, that weight on bit, the combination of those two causes the rock to fracture, causes the formation to break, we create chips, and we advance the borehole. And every drilling operation works on those same basic principles. So in all drilling operations, we've got a drill string and we've got a drill bit. Now, as we advance the borehole, as the bit fractures rock, we create these fragments, what we call drilled cuttings. People have all sorts of names for them. They call it sludge. They call it all sorts of things. It's not. It's drilled cuttings. It's pieces of formation that we have fragmented. And we need to get that cutting out of the hole. So as this bit makes hole, we pump a drilling fluid. And that drilling fluid may be air or water. It could be air with chemicals added to it, or it could be water with chemicals added to it. But we have two main flushing mediums, either water or air. And we pump that water air down the drill string. It exits at the face of the bit and then flows up the side of the borehole, the space between the borehole and the drill pipe, the drill rods. We call that the annulus. It's the annular space. And the cutting then flows up the annulus to surface. So we have a bit, we have a drill string, and we have our flushing system, either water or air, that we pump down the drill string. It exits at the face of the bit and carries the cutting back up to surface. Important term you have to remember, please, guys. The annulus is the space between the borehole wall and the drill rods. We call that the annular space. Okay. So all that varies really is the type of bit that we use. And we'll look at all of these bits just now. These are common bits that we use all the time in drilling operations. Each of them is designed for a different, basically, I suppose, for a different type of rock, for different formations, and for different purposes. So very quickly, I don't think it's very hard to understand that bit A, this one here, and bit D, and bit E, these are what we call full face bits. In other words, when we drill with this bit, the entire volume of the borehole becomes chip sample, becomes drilled cutting. The entire volume of the borehole is fragmented. And we call these full face bits. So any of these three bits here that are circled will produce a chip sample. These two bits at the top here have got a hole in the middle of them. And these both of these bits are core bits. So when they advance, when they drill, they produce a core sample. So we will select the bit, we'll select the drill string, and a bunch of other things based on what we are trying to achieve. What do we want to get from this hole? Do we want a chip sample, we want a core sample? What size core sample? What type of chip sample, and so on. So that's the fundamentals that are common to all drilling operations. And we'll talk about those in a bit of detail just now. So this is the most important thing you'll take away from this little session today. There are 4 features that are common to every drilling operation. It doesn't matter whether you're drilling an oil well, a hydrothermal well, a blast hole on a mine, or an exploration borehole, or RC borehole, or a diamond core borehole. Every single drilling operation has these same 4 features. We have rotation. In every drilling operation, we've got to rotate the drill bit. In every drilling operation, we've got to put load on the bit. We've got to push down on it to put the bit in contact with the rock so it can do its job, so it can fragment the rock. Then we have to have this flushing system that I spoke about. And then we also got to have what we call a hoisting system. In every drilling operation, at some point in time, either the hole's going to be finished or the bit's going to be finished. I need to change the drill bit. And that means I've got to pull the entire drill string out the hole, change the bit, and go back into the hole. And we do that using what we call the hoisting system. Now, that's common to every single drilling operation again. So those 4 things, guys, please remember these, okay? Every drilling operation, we've got rotation, we've got weight on bit, we've got a hoisting system, we've got a flushing system. Okay, those 4 elements are common. Those 4 features are common to every single drilling operation. Now let's look at these in a little bit of detail. We said in every method of drilling, irrespective of the method, we have to rotate the drill bit. And the part of the drill rig that rotates the drill bit is what we call the rotation head. And this here, in this picture here, this is the rotation head. And in this particular one here, it's quite hard to see, I guess. I don't know how big your screens are, where you guys are, but this is a gearbox, this big chunky thing on the left-hand side here. And basically, we've got a hydraulic motor. We pump hydraulic oil into the hydraulic motor. That motor rotates some gears, just like the gears in a gearbox of a car. And those gears are then connected to a spindle that sits in here, and that's connected to the drill rod, and that's what gives it rotation. Different types of rotation head, they're not important to remember at this stage, but it's essentially, it's the rotation unit, the rotation head of the drill rig that provides the rotation that we require. Some drill rigs, because of the bit we use, we require very fast rotation. So some rotation heads are capable of rotating very, very fast, 1200, 1300 RPM. Other rotation heads are designed for slow rotation, 40 to 100 RPM. And so the design of the drill rig will be to suit a particular type of drill bit with a particular drilling method. And that will maybe become clear a little bit later on, okay? One quick thing here, this is not critically important at this level, but if you can remember this, this is great. There are two ways. In order for the drill rig, for the rotation head to provide rotation, it's got to engage the drill rod. It's got to grip that drill string or hold the drill string in some way so it can provide rotation. And that's done in two ways, only two ways. There's no other way, there's no third way. There's only two ways it can happen. The one way it can happen is like we can see on the right-hand side. This is a rotation head from a very big, what we call a blast hole drill rig used on a mine. So this big black thing in the middle here, this big part here, really is just a gearbox. Inside there, there's a bunch of gears that go round and round. And this little black piece sticking out the bottom here is the output shaft of that gearbox. Very similar to what you have in a car, where the output shaft of your gearbox drives a drive shaft that drives the wheels of your car. And the drill string screws directly into this output shaft. Now, this is what we call a top drive. Not important to remember that now. If you can, that's cool, but it's not critically important now. We call that a top drive system. So in other words, we've got the output shaft and rotation head, and the drill string screws directly into there. As the output shaft rotates, the drill string rotates, what we call a top drive system. The second way that we can impart rotation is using what we call a chuck. Now, chuck, if any of you have ever used an electric drill, it's got a chuck on it that opens and closes, and it either grips or releases the drill rod. So in this particular case, on the left-hand side, this black and yellow checkered thing here is called a chuck. Inside of it has got a set of jaws that open and close. When the jaws close, it grips the drill string. I can then rotate the drill string. If I want to stop rotation, I will open the jaws. And then I've lost contact with it, and I can't rotate anymore. So there's two kinds. What on the left-hand side, what we call a chuck drive, C-H-U-C-K, a chuck drive, and on the right-hand side, a top drive. Now, the important thing here, guys, every single drill rig you'll find anywhere in the world, will be one of these two types. Every single drill rig will be one of these two types. And one of the first things you can take away from this course is when you go back to, if any of you are working on exploration projects or even on mines or civil engineering projects where you've got drill rigs, go and look at the drill rig and try and identify if it's a top drive or if it's a chuck drive drill rig. Because if we understand whether it's top drive or chuck drive, it helps us to understand the processes that follow with the use of this rig, and that helps us to understand several other aspects about it. So that's the first thing, okay. The second feature that's common to every drill rig is what we call weight on bit, or bit load, or bit thrust. All of these terms we use interchangeably. And all it is simply is the pressure. It's the load, the force that we apply to the drill bit to make it cut. Now, in some cases, some drill bits require huge amounts of weight, tons and tons and tons of weight, to make the cutting elements fracture rock. We'll talk about that in a minute. In other drill bits, we require very little weight on bit. in order to make the bit cut. And so the drill rig has got to have the ability to alter the weight on bit. If the drill rig can't do that, we're going to have a very inefficient drilling operation. So the drill rig again is designed to alter this weight on bit. When the formation's really hard, we want to push harder. And if the formation's soft, we want to push less hard. So this is another function that is common. Every single drill rig in the world has the ability to provide bit load, to provide and to vary that weight on bit. Okay. The third thing we spoke about was a hoisting system. And as I mentioned to you, at some point in time, we've got to come out the hole. We've got to pull the drill string out the hole, change the bit, or pull the rods out the hole because we finished the hole, because the hole's complete. Whatever the case, we've got to have this hoisting system. And if any of you have had any experience at all in exploration drilling, you will know that mining companies are, what's the kind word I'm looking for? They are besotted with the risks associated with hoisting drill rods. Hoisting operations are hazardous, they can be, but they're not the most hazardous operation on a drill site. And in many cases, mining companies think this is the most hazardous thing on a drilling operation, but it's not at all. There's many other things that are far more hazardous than this. I've just put these two pictures in here just to show you when we pull the rods out the hole, one of the key things we've got to do is we've got to stack those rods. Now, in the old days, we used to stack them vertically in the mast, like I've shown you on the left-hand side. So in this particular picture here, these stands, that thing there that you see, those are 12-meter lengths of rods. So there are 4 3-meter lengths joined together. And we pull it as a stand because it's more efficient. We can pull more quickly. If I've got to pull 3-meter rods, it's going to take me forever and a day. But if I can pull 12-meter rods, it makes the operation far more efficient. The problem is that now I've got to stack those rods in the mast. The other way that we do it is we pull the rods and we stack them horizontally onto rod racks. The Aussies do it on what are called sloops, angled sloops, where they pull the rod and it sits at an angle. Now both of these methods of stacking rods are hazardous. They're extremely dangerous, and we're not going to go into it now, but if anybody wants to, I'm more than happy to have a chat to you and explain to you why I say that this stacking rods vertically is much safer than stacking rods horizontally. But most mining companies in the world have banned vertical stacking. They will not allow us to stack rods vertically because the thought is that if they fall over, they're going to kill someone. Very true, they will. But if you look at the mechanics of it, it's very easy to avoid, very easy to avoid. So we'll talk about that. Sorry, I keep on pushing the wrong button here. We'll talk about that with some time later. We'll discuss that. I'll be more than happy to have a chat to you. Okay. Very briefly, one of the reasons why this is more hazardous is because of the mass of these drill rods. This particular drill site where I took this picture, they were drilling what we call BQ. It's a 60-millimeter hole. Those drill rods are 56 millimeters in diameter. They've got a wall thickness of about 4.5 millimeters. So these drill rods weigh about 6 kilograms per meter. So a 3-meter rod weighs 18 kilograms. Okay. And this particular hole, they were pulling 1,660 meters of drill rods. Now take 1,660 and multiply it by 6, and you get a very big number. It's a very big number. It's about 3 or 4 or 5 bakkies, LDVs, small cars in weight. And those rods were balanced on these little stands here. Now, these little stands were just welded by some guy on a Saturday afternoon. They're not pieces of structural equipment. And can you imagine what would happen if these rod stands collapsed? And it happens frequently. So we can't just, because we don't like that way of doing it, we say we're not going to do that, we must do it this way, because we don't fully understand the risks involved. And unless we don't understand the risk, we can't manage the risk. So when you look at these operations, look at them with an open mind, okay? So the fourth system that is common to every drilling operation is a flushing system. What we mean by the flushing system is the method that we use to get the cutting out the hole. As we advance the hole, we create chips, and we've got to get those chips out. We've got to get that drill cutting out the hole. And as I said earlier, we either use water or air. We call that a drilling fluid. So water, pure water, very seldom we use pure water anymore. Normally what we do is we add chemicals to it. We add a lubricant or a polymer or something like that to change the properties of the water. And that then allows us, it gives the water different properties, allows us to drill more efficiently and to solve other problems that we might have in the hole. But basically, the water air, we call that the drilling fluid. So we either have a water pump that pumps water down the drill string and then up the annulus, or we have a compressor that blows compressed air, high pressure compressed air down the drill string, out the bit, and back up the annulus to surface. So we've either got a pump or we have a compressor that delivers that drilling fluid. If we're using water as the basis of our drilling fluid, we'd have a setup that looks something like this. We'd dig a hole in the ground, what we call a sump, and we'd have the circulation pump sitting on the side with a suction hose hanging into the sump. We start the pump sucks the fluid up, delivers it through the delivery hose, down the drill string, past the bit, and back up to surface. When it comes back up to surface, it flows through a series of troughs and settling ponds, if you like. And then, sorry, my mouse is very sensitive it keeps on going forwards. Goes through these ponds, back into the main sump, and so we recirculate the system, what we call a recirculated system, okay? And that's how a typical water circulation system would work. Now, in recent years, mining companies don't want us to dig holes in the ground because we've got to rehabilitate it and we think we're going to pollute the ground and we're going to cause all sorts of environmental problems. We're not, promise you we're not. So what mining companies want us to do now is to use above ground sumps, use tanks that sit above ground. Wonderful, absolutely super, but that also is fraught with problems. And very, very, very often they lead to huge numbers of down the line drilling problems. And unless we fully understand the dynamics of this, the flow rates and so on, we can get ourselves into a lot of trouble. One of the key things I want you to take away from this part is when we pump the drilling fluid down the drill string, it exits the face of the bit and then flows up the annulus. And the speed or velocity with which it moves up the annulus is critically important. And we need that velocity to be between 30 and 50 meters per minute. Now, if you guys do some of the advanced courses with us, I'll explain to you how to do that calculation, how to work out what your annular velocity is. But right now it's beyond the scope of our little chat today. But we need it to be a certain velocity. If the velocity of flow is too low, we won't get the cutting out of the hole quickly enough and we will cause problems. If the velocity of flow is too high, there's a danger that the drilling fluid can erode the sides of the borehole wall and it will enlarge the borehole. And that's a disaster. That's the worst thing that can happen in a drilling operation, is if the hole enlarges, if it's bigger than we think it is. So we must maintain that annual velocity in that range, between 30 and 50, 30 and 55, that order of magnitude, okay? If we're drilling with air, we have a very similar system. We've got an air pump, what we call a compressor, and that compressor sucks in atmospheric air, it compresses it, and it delivers it at high pressure down the drill string. When the air escapes at the bit, it then flows up the annulus and now blows the cutting to surface. Air, pure air, has got no carrying capacity. It can't carry the cuttings. It's got to blow the cuttings out the hole. And so when we drill with air, we need a much higher velocity. And what we call, again, I can't go into all the detail here, guys, what we call the upper hole velocity. The velocity of the air at the top of the hole must be about 1,000 to 1,500 meters per minute, much, much faster than it is with water. So we've got two flushing mediums, water and air. With water, we want about 30 to 50 meters per minute. With air, we want about 1,000 to 1,500 meters per minute. Very, very different cleaning systems there that we have. Okay, so let's summarize this part quickly. There are 4 features common to every single drilling operation, and just now we're going to talk about different drilling methods quickly, and you'll see what I mean. We've got to have rotation, we've got to have weight on bit, we've got to have a hoisting system, we've got to have a flushing system. Those 4 systems, those 4 features are common to every single drilling operation. And when you go to a drill site, have a look at the drilling operation. Are they rotating fast or slow? How do they put weight on bit? What is the mechanism for them to put weight on bit? How much weight do they put on bit? How do they pull rods? What mechanisms do they use? Do they use a winch? Do they use the rotation head? How do they pull and lower drill rods? And what flushing system are they using? Ask yourself those questions, identify those different systems on the rig, and then you'll start to understand how different methods of drilling work, how they make hole. All right, let's go to the second most important part of what we're going to talk about today. And that's how rock fails. If we understand how we can make rock fail, how can we fragment rock, we can then maybe understand why different methods of drilling are better suited to some rock types rather than to other rock types. And basically, there are 3 mechanical ways that we can make rock fail. There are chemical ways we can make rock fail, obviously, but we don't use that. We're only talking about mechanical ways. So we can either crush rock, we can shear rock, or we can abrade rock. Let me show you what I mean. So the one way we can make a hole in rock is with a hammer and chisel, a purely percussive action, and you all know exactly what I mean by that. Another way that we can crush rock, a mechanism, a method that is used in drilling and mining applications and in water well drilling applications, is to use what we call a downhole hammer. So again, you saw this picture earlier. We've got our drill rig, we've got a rotation head, but downhole here now, instead of just a bit, we've got a bit plus a hammer. And this picture on the right-hand side kind of shows you roughly what I mean. This bit here has got tungsten carbide cutting elements. So these buttons here, these are hemispherical buttons made of tungsten carbide. Tungsten carbide is very, very hard and it's very abrasion resistant. And this part here behind it, this thing here, is what we call a hammer, a downhole hammer. And the way it works is like this. We pump high pressure compressed air down the drill string, it enters the hammer, and it makes a piston. Inside the hammer, there's a piston. And that piston reciprocates. It moves up and down very, very quickly, 900 to 1,000 blows per minute. It moves very, very fast. And every time it moves downwards, it strikes the top of the drill bit, transfers an energy wave into the rock, and causes the rock to fracture. The rock chips are then blown up the annulus back up to surface. So the compressed air that makes the hole cleans the hole. That same air then escapes and carries the cutting to surface. Now we call this a downhole hammer. The term downhole is kind of obvious because the hammer is down at the bottom of the hole. And we'll talk more about this just now. Clearly, In making hole, the bit crushes the rock. It's a percussive action. We rotate it, and it's that percussive action that makes the rock fail. So we produce a chip sample through a crushing, cutting action. The second way that we can make rock fail is by shearing it or cutting it. And these two bits on the right-hand side here, I'll give you an idea of this. One at the top is a tungsten carbide, what we call a drag bit. And this one down the bottom here is what we call a polycrystalline diamond drag bit. And the way that these bits work is you put them in contact with a rock, you rotate the bit, and the bit shears the rock, almost like a knife sliding through butter, exactly the same cutting action. And as it rotates, it shears and breaks the rock, creates chips, and so makes hole. Completely different cutting action to a crushing type of bit, as we saw earlier. So we can shear or we can cut the rock. The third way that we can make rock fail is by abrading or grinding the rock. Now, a diamond bit works like this. And in these little pictures here, I've shown you some natural diamonds. These are diamonds that are mined in a diamond mine. And these ones here are synthetic diamonds, diamonds made in a factory. And these, both of these cutting elements are small, relatively small. The picture on the left-hand side here is what we call a natural stone diamond bit. So each of these little cutting elements you see here is a diamond, like you see on the right, these natural diamonds, hand set into a diamond, into the bit by a human being, by diamond setters. And this bit then is put in contact with the rock and it's rotated very, very fast. And those little diamonds abrade, almost like same cutting action as sandpaper or emery paper. And it's the speed of rotation of those diamonds that create the hole. So we've got three ways of making hole. Let me move forward quickly and then I'll come back a couple of slides. Okay, we can crush rock, we can shear rock, we can abrade rock. And each of those types of diamond bit I showed you, types of bit I showed you earlier, will cut one of these, will cut rock using one or more of these mechanisms, one or more of these ways. A diamond core bit is designed for producing core samples. These bits here, these are full face bits, and these bits produce chip samples. They don't produce core samples, they produce chip samples. And so if I wanted to produce samples at a very early stage of a project where I just want to see what's down there, I'm not looking at grade or structure at all, then I choose one of these hole-making mechanisms here to produce my chip sample for me. And the one I choose will depend upon the type of rock I'm drilling, how much money I've got, the type of drill rig the contractor's got, and so on. If I want core samples, then I will use diamond core bits. I'll use a diamond core rig, and I will core drill and produce a cylindrical sample, a core sample for the entire length of the borehole. So each of these bits, we select the bit based on the type of rock we're drilling, and mainly for the purpose of the operation. What are we looking for? Are we looking for chips, or are we looking for core? And it's as simple as that. Okay, so to summarize this part, we're doing fairly well for time here. Summarize this part. You're going to get sick of me saying this because I'm going to say it 30 more times today. There are 4 features that are common to every drilling operation, every single drilling method: rotation, weight on bit, a hoisting system, a flushing system, every single drilling method. Okay. Now, based on those principles, based on what we spoke about there, the 4 features that are common and the 3 mechanisms by which we can make rock fail, the 3 ways we can fragment rock, we can now use that, and this is so important, guys. We can use that as a method of classifying different drilling methods. This is something that over the years has driven me dilly. It drives me crazy. When I sit in meetings with mining companies, international mining companies, and we call things different names. So in Australia, for example, they talk about air drilling. Well, air drilling can mean anything, but what they mean is rope percussion drilling. Then we talk about RC drilling. There's no such thing as RC drilling. Well, there is, but not in the context we are talking about here. So I believe it's very important that we as geologists, I'm not a geologist, but if we, in the exploration industry, in the drilling industry, we must talk the same language. So the classification that I use, that I propose we use, is we talk about percussion drilling methods. And these are methods of drilling where there is pure percussion. So it's only a hammering action. There's no rotation, purely hammering as the method of making hole. Then we have what we call rotary drilling methods, where it's rotation of the drill bit coupled with weight on bit. There's no percussion, there's no hammering at all. It's purely rotary. And it's the rotary speed of the bit coupled with the weight on bit that makes hole. And we would call those rotary drilling methods. Then we've got a combination of the two, where we have both rotation and percussion, like a downhole hammer, like I showed you a minute ago. So those are the three broad categories, the three broad classifications of drilling: percussion drilling methods, rotary drilling methods, rotary percussion drilling methods. If we talk about that, if we think about that, when we're looking at a drilling operation, it will help us to understand some of the more complex things down the line. Now, I call those drilling methods. Those are drilling, there are three drilling methods. And then we have what I call different drilling techniques. So within rotary drilling, for example, I can drill with a full face bit, like I showed you a minute ago, or I can drill with a diamond bit. Both of those methods of drilling, both of those hole-making mechanisms are rotary methods. There's no percussion. I'm just rotating and I'm putting weight on the bit. This one here happens to produce a chip sample for me. This one here happens to produce a core sample for me, but they're both rotary methods of drilling. And then we can do the same. I can't go into this in a lot of detail. We just don't have the time, guys. But in terms of rotary percussion drilling, we have got two methods of rotary percussion drilling as well. We've got what we call top-hole hammer and down-hole hammer. So if we start talking about the same, start using the same language, I think it will save a lot of misunderstanding down the line. Now, because we're talking about exploration drilling, one of the most common exploration drilling methods or techniques that we see around nowadays is what is called reverse circulation, or what you guys call RC drilling. It's not RC drilling, it's dual tube RC drilling. And we'll talk about dual tube RC drilling in a minute. But dual tube RC drilling, that technique can be used with a rotary bit or with a downhole hammer. We can use it in both hole making mechanisms. That will become clear, hopefully, shortly. Okay. All right. So let's have a look now at drilling methods. We saw our definition earlier of what I believe an exploration project is all about. And so we can decide whether we're going to produce a core sample or a chip sample. Now, producing a good quality core sample is difficult. In some formations, it's easy. It's nice and hard and competent and drillable. And you guys often see on LinkedIn and these other social media platforms, drillers standing there proudly with a piece of core that's 6 meters long, and they say, "Gee, what a good driller I am." It's got nothing to do with the drilling. I promise you guys, that's just geology. You know, it's nice and solid, and anybody can drill 6 meter pieces of core. The real test of a driller comes in when you're drilling difficult broken ground conditions or very soft friable ground conditions. That's where the true art of drilling comes in. So we've got lots of potential problems with producing core. When we're drilling with a chip sample, those problems multiply. And a lot of that, I think, will become clear just now. One of your key skills that you've got to develop as a geologist, that will take years and years and years to develop it, is to understand or to recognize when poor drilling practices are reducing the quality of your sample, or whether it's geology that is giving you a poor sample quality. It can be one of the two. And generally speaking, contractors would like to say, you know, we've lost core or we ground core because of geology, when in fact it's not. It's through with poor equipment maintenance or poor drilling methodology. So it's one of the key things that geologists would have to do, that as you get more and more experienced in your field, you'll be able to recognize more and more easily. Okay. So we've got these drilling methods and drilling techniques that we've spoken about. Okay, let's talk first of all about diamond core drilling. Now, guys, I'm rushing through this. Okay, I just want to give you a kind of just a bird's eye view. It's a very complex topic, and I'll show you how you can learn more about this a little bit later on. But I'm going to run through the main principles here that you need to understand as a geo working on a diamond drill operation. Just like every other drilling method, we have a drill string, and down at the bottom here, the bottommost part of the drill string is what we call a core barrel. And this is a core barrel down here. And a core barrel is nothing more than the bit and what we call the reaming shell. So you've got the bit with a hole in the middle of it. And then the core barrel is basically just a thick walled tube. And the whole idea is that as this bit advances, as we advance the drill bit, we produce this core sample, and the core sample feeds into the core barrel. So the core barrel is the receptacle, if you like, of our core sample. It's where the core sample is housed while we are drilling. So the bottommost part of a diamond core drilling drill string is the core barrel. Core barrels can vary in terms of diameter. They can vary in terms of the core size they do. They can vary in terms of the length that you get. There's lots and lots of variety, and I'll try and explain some of that to you in a minute or two. Okay. So these are just some examples of different sizes of diamond core drill bit. And one term I want you guys to try and remember here, please, if you can, this width here. I don't know if you guys can see my little pen here. That, if you look at this bit, the third one, the middle one, and the one on the right, the diamond part, the cutting part, what we call the kerf. Let me spell that quickly. This is so clever with this little pencil here. K-E-R-F. We call that the kerf. This bit on the left is what we call a thick kerf bit. The second from the left is a thick kerf bit. The middle one and the one on the right are what we call thin kerf bits. In other words, the diamond cutting part, the part that creates the fragments, the rock fragments, that creates the drill cutting, is very, very thin. And so you can see here, this bit gives us a very big diameter core sample, and this bit gives us a very small diameter core sample. And that's to do with the way the core barrel is designed and so on. So the core barrel, we can alter the design of the core barrel. We can select the core barrel according to what we want to try and produce. The size of the core and the quality of the core. That is really what we would look at. And core barrel design is a complex thing. I'm going to show you very briefly how they designed. So when we core drilling a borehole, I will have my core barrel, my drill string. The bit will be in the bottom of the hole. This hole might be 100 meters deep, 200 meters deep, 150 meters deep. But we'll have the bit on bottom, and the core barrel will be empty. In other words, I've extracted the core from it. I will then start rotation. I'll switch on my pump. I'll pump water down the drill string. The water will flow past the bit and back up the annulus to surface. And then I'll start putting weight on bit. And the bit will advance. The bit will cut. And as the bit cuts, it produces this core sample. Now, according to the length of my core barrel, let's assume my core barrel is 3 meters long. The maximum I can advance is 3 meters. My core barrel will then be full of core, and I can't advance anymore. So I will then have to stop rotation, switch off the water, so there's no more water flushing through it, and I'll pull all the rods out the hole until I get my core barrel out. I will then disassemble the core barrel. I'll extract the core sample. I'll pack it into a core box. I'll reassemble my core barrel, put the bit back on, and I'll lower the drill rods back into the hole. I'll now be at this stage here. And then I'll repeat the process. I will start, put the water on, pump drilling fluid down the hole, pass the bit back up the annulus, start rotation, start weight on bit, and I'll advance again. The point here, the important point here, is the maximum distance I can advance is the length of the core barrel. I must then stop, I must retrieve the core, and then go back into the hole and carry on drilling. Now, this is what we call a conventional core retrieval system. We call that a conventional core retrieval system. I don't have to explain to you guys how slow that can be. In shallow holes, it doesn't take long to pull and lower a drill string. As the holes get deeper, it takes longer and longer and longer. In fact, when I was a young man back in 1984, when I first started in the drilling industry, the first deep hole I worked on was a 3,800 meter deep hole, a gold exploration hole here in South Africa. And it took us 13 hours to pull rods and 12 hours to lower them. So we were drilling with a 6 meter core barrel. So we would drill 6 meters. We would then pull rods for 13 hours. Get all the rods out the hole, get the core barrel out, disassemble the core barrel, take that 6 meters of core out, put the bit back on, then 12 hours back down to bottom to lower again. We would then drill for about 45 minutes to fill that core barrel, pull for 13 hours, lower for 12 hours, drill for 3/4 of an hour, and repeat that. So it wasn't a drilling operation. It was a hoisting operation. That's all we did, was pulled in and lowered drill rods. That's what we call a conventional core retrieval system. A couple of things that are important here. We can only advance a distance equal to the length of the core barrel. Now, core barrels come in different lengths. We get underground, we use 1.5 meter core barrels, we use 3 meter core barrels, we use 6 meter core barrels. Back in the old days in South Africa, when they drilled these deep gold exploration holes, they drilled sometimes with 21 meter core barrels. So you'd do a 21 meter run. Obviously, it's dependent on the formation, but you would drill 21 meters maximum at a time. Then you would pull and lower. So that's an important thing to remember. So the length of the core barrel determines the amount you can advance per operation or per tour. The second way that we can retrieve the core sample from the hole is using what's called a wireline system. Now, a wireline system was designed in 1954, I think, 55. Am I lying to you? I think it was the 1950s, middle of the 1950s. I was born in the middle of the 1950s, so it's been around for some time. And the principle is very, very simple. So what we have is exactly like we had before. We've got a drill bit, and there's our core barrel sitting down the bottom here. And the core barrel, the inside of the core barrel, I'll show you a picture just now. The inside of the core barrel has what we call an inner tube, and that inner tube is retrievable. In other words, what will happen, we will advance 3 meters, and the inner tube will now be full of core. We then lower through the drill string, we lower what we call an overshot, this thing here. It's called an overshot. And that device, we lower it on a steel cable, it grips the top of the inner tube, and we pull that then to surface. So the entire drill string remains in the hole, and all I do is I lower this overshot on a steel wire rope. We have this big drum full of steel wire rope. We lower the overshot, latch onto the top of the inner tube, and we pull the inner tube to surface. When we get to surface, we disassemble the inner tube, remove the core sample, reassemble the inner tube, and we merely drop it. We just literally go devil it, drop it down the drill string. It'll float down in the drilling fluid. It'll latch back in position. I can then advance again. I then advance another 3 meters, and I repeat that retrieval exercise. There's what we call a wireline core retrieval system. These are just broad. There's a lot more to it than this, guys, but this is just the broad concept here. So we've got 2 ways that we can get the core out the hole. One is using a conventional system, pull and lower the entire drill string, and the other is using what we call a wireline system, where we have a retrievable inner tube. And I think I've got a picture. That's what it looks like. So this is what we call the inner tube assembly. You see that little part at the top there, that's what we call the spearhead, and the overshot latches onto that. It grips that. It allows us to pull the inner tube out. And once we've cleared the inner tube, we merely drop it, and it goes straight back down and sits in this core barrel, this little cutaway sample that I had made for my lectures, for my training. So that's what we call a wireline system. Okay, now I'm not going to show you all of these parts. These are not so important to us. Okay, the important thing is that the core barrel, whether you're using a conventional core barrel or a wireline core barrel, the selection of the complexity, if you like, or the design of the core barrel will have a huge impact on the quality of the sample you get, and obviously on the size of the quality. So this picture here is similar to the one I showed you earlier. These are all diamond core bits. They all give us different sizes of core, different hole sizes, different core sizes, and they're all selected for different purposes. And that's what you will, as a geologist, come to recognize as you do more and more work in the industry. Let's look now quickly, and I'm going to rush through this fairly quickly, because what I want to do, guys, just now, I don't want to be late in finishing. So what I want to do quickly, I'm going to just do this part. We're going to have a quick 5-minute break, let you guys go and get some water or a cup of tea, and then we'll start again. So let me go through this part quickly. We'll take a quick 5-minute break. Okay. If we look at conventional core barrels, these are core barrels where I advance, I pull the entire drill string out the hole, and then I go back into the hole and I advance some more, what we call a conventional system. Now, conventional core barrels, there are basically 3 kinds of core barrel. I'm going to run through this quickly, but as I go through it, you'll understand why I'm showing this. The first type of conventional core barrel is called a single tube core barrel. So in every core barrel, no matter which one it is, we've got a bit and we've got what we call a reaming shell. This is the part that connects the bit to the outer tube. And this outer tube is just a tube. So as I advance, the core feeds into what we call the outer tube, into the core barrel. The important part here is that the drilling fluid that I pump down the drill string comes into the core barrel and it flows over the core sample. So if my core sample is soft and friable, I'm going to wash it away and I'll get very, very poor core recovery. So this type of core barrel I'm only ever going to use in hard formation, or I'm going to use it in cases where I don't worry about the core sample. In the soft stuff at the top of the borehole, where I'm not worried about the sample, and if it gets washed away, well, that's okay. That's what we call a single tube core barrel. If I want a better quality of core sample, I will use what we call a double tube core barrel. Now, just as I had before, I've got a bit and a reaming shell. I've got the outer tube, this gray bit here, but inside that outer tube is an inner tube. And so when I drill, the core feeds into the inner tube, not into the outer tube. And so purely and simply because I've got that second tube, it protects the core from water washing and it gives me a better quality core. Obviously, guys, it doesn't take much to understand that this core barrel, a single tube, is very cheap. This core barrel is much more expensive, much more costly. So if you're going to, if you want double tube core samples because you want a good quality sample, you're going to pay more money for it. It's going to cost you more. Let me scoot through here quickly. This is not so important now. Okay. This is very important, very important. Very often, and I'll say this more than once, very often the process of extracting the core sample out of the tube or out of the core barrel destroys the sample. And this is a perfect example here. Here's a guy, I don't know where this is, but he's, in order to get the sample out, he's hammering away on the inner tube of this double tube core barrel. And so you get this piles of chips. You don't get sample at all. Now, if we have, and let me say this again, if the process of extracting the sample destroys the sample, then what we can use is what we call a triple tube core barrel. So now we have the outer tube, the inner tube, and then inside the inner tube, we have another tube. And so the core feeds into that inner tube. And when I'm finished drilling, when I've pulled the core barrel out the hole and I disassemble the core barrel, I don't pull out the core sample, I pull out the inner tube, the inner tube. And my sample is then sitting inside that inner tube. And this picture on the left is a wonderful example. Those inner tubes are split, longitudinally split. So once I've taken the tube out, I merely take the top half off, and then I can see my my core sample. And you can drill the most amazingly friable formations using a good quality triple tube core barrel. So the point I'm trying to make here, guys, let me see if I can get to, yep, that's what I wanted to get to. We've got three kinds of conventional core barrel: single tube, double tube, triple tube. As you go from single to double to triple, the quality of your core sample increases dramatically. The cost of the core barrel increases dramatically, and the cost of drilling increases dramatically. But it's very important to understand that each of these is available, and your drilling contractor should know this. And depending upon the type of formation you're drilling, the depth you're drilling, and why you're drilling, and so on, you can select a conventional core barrel to give you the quality of sample that you require. We spoke about the wireline core drilling system. I'm not going to go into all of the detail here because it's just way too complex. But as I said earlier, I can show you, point you to places where you can learn more and more about this. A wireline core barrel is a fairly complex thing. It's got about 32 moving parts in it. And it's way beyond the scope of what we're doing today to go into this in any detail. But what I do want you to remember is this process here. The difference between a conventional system and a wireline system is that in a wireline system, the inner tube is retrievable. It's a double tube core barrel. We've got an outer tube and the inner tube. But in this case, the inner tube is retrievable through the drill string. Whereas with a conventional system, we pull all the rods out, disassemble the core barrel, extract the core, reassemble the core barrel, go back into the hole. So wireline is far more productive than a conventional system. All right, guys, I tell you what I'm going to do. It is, it's just gone 5:10. I want to just quickly can we take a 5-minute break? It's just after 10 past. Can we say we start at 16 minutes past? Please just go and stretch your legs, get a cup of coffee or a cup of tea or a glass of water quickly. I'm going to get myself a glass of water. If we can start again, I'm going to start babbling away at 15:15. I'm not going to turn my video or my speaker off. So please, guys, let's take a quick 5-minute break, and I'll see you shortly. Thank you, guys.
Hello, Colin.
Hi, who's that?
Marcy, long time.
Hello, Marcy. How's it, bud?
I can't complain. Good to hear from you.
Good to see you again. Yeah, I said to the guys, this is one of the highlights of my of my year. Is this day? I really enjoy it.
Yeah, I will share that, Colin. I look forward to the rest of the day.
How's
Down Under?
No, good. How's the Northern Cape there? All good.
Yo, it's freshly cold today, but that's normal for the Northern Cape, right? Apart from that, we could call it.
Where are you at the moment? In K2?
I'm in K2 in session at the moment. Yeah.
Okay. That's yeah. I miss my trips to K2. You know, I used to go there often. Since I've been in Oz, I kind of in fact I'm hoping to make a trip back there in the not too distant future. And hopefully we can touch base. We'll go and have dinner or tea or coffee or something. Eh?
That'd be great. Let me know when you are.
No, I'll give you a holler. Yeah.
Look forward. How's down under the weather?
Yeah, it's good. Thanks. It's good. It's cold. It's cold, but you know, the cold in winter in South Africa is dry. Yeah. And I don't miss that. I hate cold, dry winters. But here it's like Cape Town. It's a wet winter. So I'm actually enjoying winter. It's cold. Yeah, and it rains every second day, but it's fine. I don't mind it at all. I actually enjoy it.
No, that's good. Do enjoy it, and I look forward to see you when you're coming around.
Yeah, no,
Sorry to interrupt.
Hi, Tanya.
Can you please make Masi and myself co-hosts?
Yes.
Please.
Okay, give me a second. Okay, Tanya, you're done. Masi. Okay, you guys are both co-hosts now. Can you see that? Tanya, can you see that? Are you all right?
I can see it on my side.
Okay. Cool. Okay, we just give the guys another minute, and then I'll get cracking again. Okay. Okay, should we let's start again. I don't know if everybody is back, but if you are, welcome back. I just want to quickly, before we go on, there's one or two questions here and comments. I just want to quickly run through them. I don't know if you guys can see it on my shared screen here, but a couple of things I just want to mention, because there are some sometimes some misconceptions that come into what we call exploration drilling. Abdullah says here, thank you very much for the comment, Abdullah. Weight on bill is normally measured as a log versus drilling time when drilling in oil and gas exploration. Is that the same in onshore minerals drilling? No, it's not. we are moving towards more use or more monitoring of data parameters or drilling parameters, I beg your pardon. So more and more it's becoming part of it, but as a rule, we don't. We drill by feel, Abdullah, and the same with rates of penetration and torque. We don't do it as scientific as you do in the oil and gas business. Abdullah says here as well, I see you mentioned water and air is used as a medium for drilling fluid. I can't understand why you wouldn't use oil. We won't use oil. Let me try and explain it like this. When we core drill, typically a core drilled hole would be 76 millimeters and the drill rods would be 70 millimeters. So we've got an annular space of 3 millimeters either side. And you just won't circulate an oil-based drilling fluid through there. The yield point is way too high, you just won't circulate it. So we do not use, you use them as inhibited systems because you're drilling through water-sensitive formation. We don't do that in the mineral exploration. So you just can't circulate it. It's too, the yield point is way too high in those emulsions. I'm just going through these quickly. Demakatsu asks what sonic drilling is. Great question, but we haven't got the time to talk about it now. Do one of the later courses. In fact, if you do the drilling methods course later in the year, we talk about it there. Can a core barrel be more or less than 3 meters? Absolutely. We use 3 meter, 9 meter core barrels, 6 meter, 9 meter core barrels as well from time to time. Eric says there quite correctly that in the United States, core barrels are measured in feet and inches. United States is so far behind the rest of the world, hasn't caught up with the metric system yet, only joking. But there, yeah, they use imperial measures. So they talk about feet and inches. Different core sizes, I'm not sure. I don't believe I've done it in this little session here, guys. But yeah, the different core sizes, it's critically important you know that. What I'll do, there's a table I have of all the different sizes and diameters. I'll share that with Lali, and she can maybe then share it with you guys via your email link. Okay, so I'll do that. I'll send you those dimensions. Then Eric here says he was on a drill in Sweden. That's interesting. I'm going to Sweden early next year to do a training course, and there they use only water. Many drillers use only water, but typically they will use some sort of cutting fluid, some sort of cutting oil, and a polymer to enhance the properties of the water. And then what Obakwi says here, I believe the use of the polymer is for 2 reasons. One is to make sure the bit doesn't get worn off fast, and 2 is to assist with flushing our cuttings. You're half right. The polymer won't necessarily extend bit life. It may, but what a polymer will do, it thickens the water, it increases the viscosity of the water, and it's the viscosity that helps you lift the cuttings more efficiently. So you 95% correct there in what you said. Okay, so that's managed some of the questions there. Let's move on now. And let's carry on. Sorry, guys. Let me just find where I am here. My keyboard doesn't want to do what I want it to do. Let's talk now about the next method of drilling. And I want to talk about reverse circulation drilling here. But before I talk about reverse circulation or dual tube reverse circulation, I just want to recap what we spoke about here in terms of rotary percussion drilling. Earlier, we spoke about what we call a downhole hammer, where we have a bit, and then inside the bit is a piston. I beg your pardon, inside the hammer is a piston. And the piston reciprocates, comes down, strikes the bit. Every time it strikes the bit, it transfers an energy wave through the bit into the rock. The rock is fractured and the chips get blown up the side of the hole, back up to surface, up the annular space, back to surface. So now In a dual tube reverse circulation drilling technique, and please mark the words I use there, dual tube reverse circulation technique. We've got 3 ways that we can make the drilling fluid flow through our drill string. What I've been speaking about all the time so far is what we call a direct circulation system. The drilling fluid is pumped down the drill string, comes out of the bit and up the annulus. A reverse circulation system is the reverse of that. We pump the air down the annulus, it goes across the face of the bit and up the middle of the drill string. That is RC drilling. That is reverse circulation drilling, but that's not what we do in exploration. What we do is what we call dual tube reverse circulation. And it's very, very important that we use that distinction. In a dual tube system, I have an outer tube and an inner tube. And the air is pumped down through the annular space between the 2 tubes. It comes out here at the top of the bit, flows around the bit, and back up the inner tube to surface. So now, very clear from looking at these. In a direct circulation system, the sample that I produce at surface will be contaminated because the air or the water that's flowing up the annulus is in contact with the formation. I can get contamination as my sample is coming out the hole. Similarly, in a reverse circulation system, I can have contamination because the sample, I beg your pardon, the flushing medium, either the water or the air, is in contact with the formation. So I can pick up contaminants and my sample will therefore be contaminated. A dual tube reverse circulation system, however, will produce an uncontaminated sample because the air that is traveling down to the bottom of the hole is not in contact with the formation. It's in the annular space between the 2 tubes. It escapes at the top of the bit, moves across the bit face, and back up. The sample comes up the inner tube. So I can produce an uncontaminated sample. And that's critically important. That's what we call a dual tube RC system. Please, if I come to your drill site, please don't tell me you're doing RC drilling. Tell me you're doing dual tube RC drilling. It sounds pedantic, but we do use RC systems in drilling. But I don't have to explain to you how different these are. One produces a contaminated sample, one produces an uncontaminated sample. Okay. Now, I want to, guys, I have to move on quickly here because I want to get to a very, very important part. And I don't want us to run out of time. One of the key problems with a dual tube reverse circulation system is that the volume, the entire volume of the borehole that I drill, the entire volume of rock is made into chips. And all of those chips now come up the inside of the inner tube. And I need to take only a portion of that sample. For example, if I'm drilling a 140 millimeter hole, typically 140 millimeter or 4.5 inch in American terms, depending upon the density of the rock, I'm going to produce about 30 to 32 kilograms of cutting per meter. Now, there's no way I'm going to take 32 kilograms of cutting per meter to the lab to have it assayed. That's going to cost me an arm and a leg. It's going to be ridiculous. The cost of transport will be more than the mine's worth. So I want to reduce that mass of sample. I want to split that sample so that I can take a smaller part that is truly representative of that entire mass, that meter or half meter, whatever it is that I've drilled. And that is done using a sample splitter. And these are 2 typical sample splitters that you will find on exploration projects. The one on the left is called a riffle splitter, and the one on the right is called a rotary cone splitter. We just don't have time. But when you do some of the more advanced courses, you learn about all of these things in a lot more detail. Okay, so we get the sample and we split it, and it's only that part that small split part that then goes to the lab for assay. So to summarize this first part then, and I mean, heavens, we haven't even scratched the surface. What do you need to know about the technical aspects of drilling? Well, you need to understand different methods of drilling will give you chip samples, different methods will give you core samples. And you need to understand as you progress through your careers and you learn more and more about drilling, what is going to affect the quality of the sample that you get, whether it's a chip sample or whether it is a core sample, because the quality of the core is critical to you. And very often the contractor will have a problem that translates into a reduction in quality, and you have to live with that reduction in quality. And if you're drilling, imagine drilling a 3 kilometer deep hole and the zone of interest that you're drilling is ground or washed away. Well, you've drilled 3 kilometers for nothing, because the quality of your sample doesn't tell you what you want to know. So that's what you need to focus on. I want to quickly now move on to these last two aspects, okay? And we'll try and do some justice to these. In 2009, I kind of retired. I decided I was going to retire and see if I could get sick of playing golf. But I didn't play many rounds of golf before mining companies started to phone me and asked me to help them with problems. And one of the biggest problems, or one of the biggest projects I worked on, was a safety project where they asked me to audit a very big drilling operation, 38 drill rigs, 4 different contractors, 8 different designs of drill rig. And that led me into what we call the safety part of exploration drilling. And a huge amount of the work I do nowadays is around safety aspects of drilling, writing standards, doing audits on drill rigs, and so on. So I just want to share with you just a few things here, guys, about safety. In almost every jurisdiction in the world that I've worked, except 1 or 2, geologists have a legal responsibility for safety. What I mean by that is that if something goes wrong, they could be prosecuted. Now, in many jurisdictions, it's not the case, but in many jurisdictions, it is the case. And so geologists have to have a pretty good understanding of safety. And so what I always say to geos is you need to understand, let me just go back one slide there quickly. 2 aspects to safety that you need to be good at is, number 1, you must be able to identify hazards on drill sites. You must be able to, as an intelligent, trained, normally university trained person, you should have the ability, or you've got to develop the ability to look at an operation, identify where the hazardous parts of the operation are, or the hazardous parts of the equipment are, and then put in place a control to make sure nobody gets harmed because of that hazard you've identified. We call that risk assessment, hazard implication. So you need to have that skill. And then the other thing you need to have is you need to understand what your legal responsibilities are. Because if you'll excuse the language I'm using, but you need to be able to cover your butt. Because if something goes wrong, you don't want to be in trouble. And in order to do that, you need, in South Africa, I'm using a South African context here. In South Africa, you must be competent. It's a word that we use often in the drilling industry. We talk about competence, and this person is competent or not competent. What does competent mean? And I'm just putting this in here because I want you to think about this. Not necessarily this is what applies in your jurisdiction, but I want you to think about this. I believe that the term competence is very well defined in our legislation. In South Africa, it's defined in Section 4B of what we call the Minerals Act, what we call now the Mine Health and Safety Act. It used to be called the Minerals Act. And it's in the regulations of the Minerals Act. And it says this, it says a competent person is a person who was qualified by virtue of his knowledge, training, skills, and experience to organize work. So he's qualified by virtue of his knowledge, leave the word training out. Knowledge, skills, and experience to organize work. Secondly, the person must be familiar the provisions of the Act and the regulations that apply to the work. In other words, the person must understand what his legal responsibilities are. He must have knowledge of the Act. Now, in your country, in whatever country you come from, you will have legislation that has an impact on exploration drilling. You need to understand what that legislation says. And then finally, in South Africa, a person who's competent is a person who has been trained to recognize any potential or actual danger. So in other words, they have the ability to identify hazards in the workplace. So there's 3 elements to competence. And I'd like you just to bear that in mind, because when I train people, when I talk to geologists, when I talk to safety officers and safety professionals, I use this as the basis. At the end of the training, I want them to be competent. So I want them to have technical knowledge, I want them to have some legal knowledge, and then they must be able to identify hazards. So please bear that in mind. Okay. Now I'm going to skip that because that's not so important. I want to get to this last little bit here quickly. Sorry, guys. We are running out of time, and I do not want to delay Masi and the other guys because it'll make today very, very long. So I want to try and just spend 10 minutes on this last bit, because this is possibly one of the most important parts of what we're talking about today. 3 aspects to what a geo must know. They must have some technical knowledge, they must have some safety knowledge, and they must understand some economic aspects of drilling. And sometimes this is the most important part. And I'm going to show you a couple of slides just now. I'd really like you to pay attention to them, and it'll maybe change the way you think about your drilling your drilling project and the way you interact with your contractor. So there's 2 main things I think that are important here. The geologist must understand the cost of drilling. He must understand what affects the cost of drilling. And that's easier said than done, but I'm going to show you a little example of what I mean in a minute. And then probably more importantly, the geologist must understand how his actions affect the cost of drilling. Often, very, very often, too often to be comfortable, I see geologists on drill sites doing things that affect the contractor's ability to make a profit. And so it increases the cost of drilling, it increases safety risk, and it's a disaster. Similarly, I often see geologists who truly understand drilling operations, understand how a contractor works, understand how a contractor makes profit, and they help him. And let me try and explain that in a minute. Every 99.9% of drilling operations done for mining companies or exploration companies are done on the basis of a contract, where you have the mining company or the exploration company that's had a fixed budget, an amount of money they've got to spend, and they want to get the lowest possible cost per meter so they can maximize their information. The contractor, on the other hand, has got huge amounts of money invested in equipment, massive amounts of money. And he needs to see a return on that investment, so he wants to get the highest price per meter. So somewhere between those 2 scheming extremes, we develop a contract. And that contract allows the contractor to go and drill for you, give you your information, and allow him to make a profit, because he's got to make a profit. So we can say then that all exploration drilling is based on a contract. And so the geo must have at least a basic understanding of how that contract is structured. Normally, the geos are not involved in the procurement side of it. And so you just land up on site with a contractor, and sometimes the geo on site that hasn't even had sight of the contract yet. So you don't know what the costs are, you don't know where the guy can rip you off, where you can lose money, where you can make money. And it's very important that you have an idea of that. Because the contract, the way it's designed, will have a big impact on the relationship between the mining company and the drilling contractor. And guys, I can't stress this strongly enough. It's a contractual relationship, and the contractor will try, I'm not being unkind to contractors, he will try to make as much money out of you as he possibly can, because that's what he's there for. And you as the person, the custodian of your drilling budget, you want to take as much away from him as possible. So you ask him to do all these unreasonable things. And that's where the problems occur. So it's important you have a good understanding of one another. And so what I want to show you quickly, there are different kinds of contract. I'm going to run through this quickly because it's not critically important, but it does show you different ways of looking at problems. The first type of contract is what's called an all-in contract. In other words, the contractor says to you, I will drill you a borehole to 1,200 meters. I'll put 3 wedges in, and you're going to pay me $45,000 per borehole, or whatever the case happens to be. So in other words, all you're going to get at the end of the month is a one-line invoice. 6 boreholes at $45,000 each is whatever, 6 times $45,000 each, what we call an all-in contract. Sometimes used, they used to be very popular here in South Africa, not so much anymore. Now you can use an all-in contract if you know what the risks are. If you're not so happy about the risks, then we use what's called a variable rate contract. And in a variable rate contract, the contractor will charge certain fixed amounts, and then he'll charge a variable rate based on hole size and depth. So you'll have a series of rates that will change as the hole gets deeper. Then the third kind we have is what's called a fixed rate contract. So the contractor will come onto site and he's going to bill you $230,000 a month to have a drill rig on site, whether he drills 1 meter or he drills 7,000 meters. And that would be a type of contract that's used in situations where there's a lot of risk. So you might not have access to sites, and the contractor might have to stand for long periods of time because of political reasons or access reasons or just continuity of work reasons. And so he's got to cover his costs, so he will charge what's called a fixed rate. There's a fourth kind of contract that I'm starting to see now in the work that I'm doing. And this is called a minimum shift rate contract. What the contractor does here is he says to you, my shift rate is $6,000 per shift. And so he will work, he will drill, and if he doesn't generate more than $6,000 in that shift, he will bill you $6,000. If he generates more than $6,000, he'll bill you the higher amount. But it's designed to make sure the contractor covers his costs. That's critical, guys. The contractor has got to cover his costs. He's got to make a profit at the end of the day. Now, let me just jump through here. I want to jump to this most important part here. How does a contractor make a profit? Well, typically what happens is you produce a tender specification with a scope of work. The contractor will go away and he knows what his costs are. So you're going to certainly work out his costs. You'll come out and you'll say, it's going to cost me so much per meter. I'm going to, in my tender rates, I'm going to put in the amount plus X% profit. But in doing this, in doing these sums, and this is a very simple way of doing it, guys, and many contractors will tell you that they don't do it like this, that's fine, but nuts and bolts are they will. Every contractor will have fixed costs and variable costs. So fixed costs will be things like rentals, insurances, leasing costs on vehicles, salaries and wages, things he's got to pay whether he's drilling or not. Those are fixed monthly costs. Think about it in terms of your budget at home. You've got rent and lights and water and insurances and so on. You pay that whether you eat or not. Then he will have variable costs. These are costs that he only occurs while he's drilling: fuel and oils, bits and reaming shells, core barrels, drill rods, etc., etc. Those are the only costs that he only incurs when he's drilling, when he's making hole. Now, 2 principles here, guys, and this is probably one of the most important slides today. 2 principles are very, very important. Standard basic business principles. Principle number 1 is profit is the reward for risk. If you ask a contractor, because of the way your contract is designed, if you ask the contractor to to take on all the risk of the project, he's going to charge you a bomb. If you understand your risk and you share the risk, your rates will be much, much lower. And then the second principle, this is the most important, that if a contractor is not making a profit, he cannot perform on site. Let me say it again. If a contractor is not making a profit, he cannot perform on site. And what that means is your productivity is going to go down the tubes and you are going to have a safety incident. I'll give you a letter. You will have a safety incident. And most, I'm lying, not most, but many of the accident investigations you see, many of the situations where people have accidents, it's because the contractor is not making money, And when he's not making money, he doesn't maintain equipment, he doesn't train people, he takes shortcuts. He's got to increase productivity, so he'll do things that are outside of the specification. So it is critically important the contractor makes a profit. And I argue that the project geologist, the guy in charge of the project, it is your job to make sure the contractor makes a profit. If he's a bad contractor, you should never have hired him in the first place, and do what you can to get rid of him and get a decent contractor in. But if he's a good contractor, help him make a profit, because your life will then be much, much easier. So that's really, really important, guys. Really, really important to remember, please, those two principles. Profit is the reward for risk. You ask the guy to take on all the risk, he's going to lobby you in terms of price. He's going to want to make a bomb of money. He has to make a bomb of money. And then secondly, if a contractor is not making a profit, he cannot perform on site. Now, let me give you a very simple example here. Now, there's two more slides and then we're just about done, okay? This is a very old slide, so these numbers don't mean a great deal, but the principle's well explained here. You ask a contractor to come along and you tell him we need to do 12,000 meters of work. We think it's going to take 4 months to do this work. So you bring as many rigs as you need to do that work. So the contractor has looked, he says, okay, this is a lovely contract. And he says that he's going to bill $400 a meter to do this work. So his revenues will be 12,000 times 400. He knows that his fixed costs are $200,000 a month, and he's going to be drilling for 4 months. So his fixed costs are going to be $800,000. And his variable costs, he knows that it costs him $200 a meter to drill that particular formation. So his variable cost will be 12,000 times 200, which is $2.4 million. So he's going to have total costs of 3.2 million, and he's going to make a profit of 1.6 million. That is what his projected income statement is. Then, unfortunately, the mining house get the guy on site, and then they decide that their licenses aren't in order. So they delay him by a month, and then the geo doesn't do his work properly, and they delay him by another month. And so instead of it taking him 4 months to drill, it takes him 6 months to drill. And so his fixed costs now go, instead of being 4 times 200,000, it now becomes 6 times 200,000. And his profit now drops from 1.6 million to 1.2 million. Purely and simply because the mining company didn't do what they were meant to do. And you have the guy sitting, incurring costs that he can't recover. And it doesn't take much to recognize that it doesn't take long before he's in trouble. This is the last slide I want to show you. Probably the most important slide that many geologists see. It looks complicated, please just work with me. Okay, we'll run through this twice and then we're going to call it a day. Let us assume that there are 20 drilling days in the month. 4 weeks, we drill for 5 days a week. We don't drill Saturdays and Sundays, okay? And let's assume that the contractor makes 25% profit on his total cost. So his total costs are $100 a meter. He's going to bill you $125 a meter, making 25% profit on his costs, okay? Then, in the first 15 days of the month, all of the revenues he earns are going towards covering his costs. He's not making a cent of profit in those 15 days. in the last 5 days of the month, the revenue he earns there is profit. So if you, because you haven't done your job properly, if you delay the contractor for 1 day, you have robbed him of 20% of his profit. Stop him for 2 days, you robbed him of 40% of his profit. Stop him for a week, and the guy is losing money. And that is critically important for geologists to understand. Do not, if he's a bad contractor, he's going to lose money anyway. As I said, get rid of him, make an excuse. But if he's a good contractor, don't stop him unnecessarily. If you haven't done your work because you haven't pegged a hole out, or whatever the case happens to be, take it on the nose and pay him his standing time. But you can't have the contractor stand because you think it's your job to make him stand. Okay, guys, we are just about on time. I do not want to delay Massey. There's 1 or 2 more things I'll talk about, but they can wait till one of the later courses that we do. Last slide I want to show you quickly. Last slide quickly. In terms of where do we go from here? We've got the drilling methods and techniques course that we do in September. I think it's the 5th to the 26th. You might want to look at that. We're going to a lot of this stuff in a lot more detail. And then if you really want to get into a lot of detail, we run an online drilling skills for geologists program that takes a lot of these concepts. We go into a lot more detail. It's a very long, very detailed course. If you go to the website, colinriceexploration.co.za, you'll see all of the details there. Okay, guys, I'm going to. There's one last thing. There's one last thing I want to just say here quickly. In the comments here, one of the last comments here, we're talking about drilling fluids. I want to mention this because it's important. Abdullah said there, polymers also increase the pressure exerted by drilling fluids to overcome formation pressures if you're drilling through porous formations. Adding a chemical, adding a polymer to a drilling fluid will not increase the density of the drilling fluid. It increases its viscosity. And the only way you increase pressure is by increasing the density of the fluid. Adding polymer will not increase density. It will only increase the viscosity, which helps you to clean the hole more efficiently. Okay, Tanya, I'm going to leave it there. Is that okay?
Hi, Colin.
Tanya,
yes, that is perfect.
Okay.
Before you answer some of your questions, we'll go on further. Sarah is here. If you'll just, Sarah, if you will unmute yourself or put your hand up so that Colin can you make Sarah a co-host as well, please?
Give me a sec. Sarah. Give me 1 second. I was trying to find Sarah here quickly. Give me 1 sec. Sarah.
She should be up at the top with her hand up.
Yeah. Give me 1 sec. I can't see Sarah on the participants list here.
Yeah, she should be right up at the top.
Sorry. No, I can't see Sarah's name. Yeah, wait a minute. Sorry, I beg your pardon. I beg your pardon. There it is. Sorry. Okay, Sarah, there you go.
Thank you very much.
Are you there, Sarah?
Yep,
Yeah.
I'm here. All good.
I believe you
Perfect,
wanted to ask a
thanks.
question. Is that right or not?
No,
Not.
she just put her hand up so that we could see where she was.
Oh, I see. Okay, we can see you, Sarah. Okay, guys, I'm going to leave it there. I don't want us to delay the rest of the program. There's some really good stuff you're going to be learning from Massey as you go on. and from the other guys later on today. So thank you very much indeed for joining. If anybody, anything I've said that you want to clarify or any comments, whatever, if you get hold of Lally through the GSSA, she can pass it on to me, and I'd be more than happy to answer your questions for you. Okay. I wish you all the best of luck for the rest of today, and hopefully
before you disappear, please
Yes.
make me the host as you
Okay.
leave.
Give me 1 sec. Sorry, Tanya. Sorry, guys. This is for me. This is hard, eh? To understand.
Sorry,
all of this
guys.
stuff.
My internet is just so bad at the moment that we're having to just jump around all over the place.
Thank you guys for joining, and thank you guys for your comments. They were really good and very, very valid. Thank you very, very much indeed. And I wish you all the best. And you never know, I might see you on a drill site one day. Thank you so much, guys.
And thank you ever so much again, Colin. Much appreciated as per usual.
Bye-bye, guys. Take care.
Have a bit of a break at the moment.
Okay.
Till 10 o'clock.
Cool. I'm going to sign off. Thank you, Tanya. Thanks, Tanya. Take care.
Thanks, Colin.
Bye.
Bye.
Tanya, morning. Yes, I'm. Oh, okay. But I can't hear you guys.
Can you hear me now? Yes, I am. Okay, so just unmute yourself. Hello, Heino, can you hear? Yes.
I know.
Oh, if you tried selecting a different speaker, use your system. Okay, and you need to unmute yourself.
Okay. Morning, everybody. Apologies. Can you guys hear me?
We can hear you. Just hold on a
Yeah.
second. We'll start again at 10 o'clock, and I will
Okay.
give you a short introduction.
Okay.
But
Thanks, Tanya.
you can start sharing your screen if you'd like.
Yeah, let me do that.
And then just put it into presentation mode.
Yeah. There we go.
That's perfect. We can see here that. Thank you, Aboka, for the that message. Everybody, just those who joined in a little bit late, I just want to chat very quickly about the assignment. And yes, everybody will still receive a copy of the videos or the recording, as well as the PDFs. As long as you have joined in, you will get that information. Also, your assignment, which we spoke about earlier, is a one-page summary of important points for each of the presentations. In other words, I'm expecting 6 pages from each of you to summarize each presentation. You can catch up on the recordings and the PDFs if you have missed anything. And you send it to me directly at marshall.tanya@gmail.com. I will put that on the chat now. Okay, so that is my email address. You email it to me directly, and you will get your CPD credits. The assignment is to be submitted anytime up to the 30th of November. Do it sooner or later, but not beyond the 30th of November. I will put it up again on the screen during the next break, but I see Raya has already put something in the chat, but we'll talk about that again just now. Right, so now let us move on to the next part of our presentation, and we have Heino Hoops from MDEX as the operational manager for Southern, East, and Central Africa. He started off in 1994 as technical sales rep for SAMChem, managing drilling fluids on ultra-deep holes and grouting of boreholes. Heino specializes in developing mud systems for kimberlite core drilling. He then left SAMChem, joined Boyson Bore as a site supervisor, and then moved across to MDEX when MDEX acquired SAMChem. He has been at MDEX ever since then and brings a wealth of drilling and drilling fluids experience with more than 25 years in the drilling and drilling fluids industry. And so Heino is going to talk to us about what we need to know about drilling fluids. Heino, over to you.
Tanya, thanks. Thanks for the opportunity to be part of the organization and do a presentation regarding drilling fluids. I think you said it all about me. There's nothing more to say. I don't think that most of the geologists are familiar with Heino, are more familiar to the drilling companies, as we are dealing more direct to drilling companies and as towards the geologists. I don't know, Tanya, please stop me. But if there's any questions, please just fall in, stop me, and we can then address that specific point. Or if you want to make notes and you can ask me questions after the presentation. If you don't understand a term, please stop me so that we can explain that then as well. The content of this presentation is why should geologists have basic knowledge about drilling fluids on site, basic principles on drilling fluids, some tips on in-hole problems, and then how should drilling fluids be monitored on site to get the best properties out of it. So why should we care about much? Drilling fluids have an impact on drilling operations between 30 and 60%, and drilling fluids account only for 5 to 15% of drilling costs. Normally, drilling fluids are the lowest on the food chain, if I can call that food chain. But if you think of it, if you don't have the right drilling fluids and you're drilling through a difficult zone, you will not be able to get through, and therefore you will not be able to get the information out of the ground that you as geologists really need to understand what's going on beneath the ground. So yeah, drilling fluids, very, very important. Primary functions of drilling fluids, and I will go a bit more into depth on some of these 12 points, but in short, it's maintain well stability, remove cuttings from the well, control formation pressure, suspend and release cuttings, seal permeable formations, minimize reservoir damages. I think most of you guys already have read through this. Like I said, I will go into a bit more depth on some of these primary functions of the drilling fluids. Why use a drilling fluid? First of all, it improves productivity, achieves objectives that's been set by the geologist, help to drill through difficult geological conditions. It improves conditions down the hole. It prevents tool lossing. In other words, if you drill in a very broken formation and you don't have the right drilling fluids, the driller might lose the drill string in the hole. Impact on drilling cost, and drilling fluids must be looked upon as a useful tool to assist the driller in completing all his objectives that's been set out by the geologist. Functions of a drilling fluid, like I said, cooling of the bit. This is the primary function of any drilling fluid is to give lubrication on the drill string, especially where you drill deep holes, anything from 500 to 3,500 meters. You need to have good lubrication. And then also while cooling the bit face, cooling may be enhanced by inclusion of wetting agents. So in the old days, the only lubrication that was available was the rod grease. Saying that, we still have rod greases today as we speak, but Imdex developed liquid lubricants, and that's where the wetting agent comes in. So it's not just lubricating the drill rods or the drill string, it also opens up the diamonds in the bit face to give you a better rate of penetration. Then, very, very important, removal of drill cuttings. Now, there's a lot of factors that can influence the rate of how these cuttings are removed from the bit face, all the way up in the analyst space. Talking about analyst space, for those that don't understand the term analyst. So the analyst space is the opening. If you can have a look on the picture, it's that blue arrows. That is the analyst space. So the analyst space is the opening between the outside diameter of the rod and the inside diameter of the borehole being drilled. That is called the analyst space. So factors that have influence on how these cuttings are removed is the viscosity, and then the size and density of the cutting, and then something that we normally don't take notice of is the pump rates of the pump. So people might think the faster you pump, the quicker and the better you get your drill cuttings out of the hole. It's not true. There is a certain rate that's been set, and this is not been set by myself or Imdex. It's an API standard, and ideal annular velocity should be between 24 and 43 meters per minute. Saying this is that as the cuttings are moving up into the annulus, there is what we call slip velocity. So depending on the density of the sludge or the particle that flows up into the annulus, depending on the size, that particle might drop down 9 to 3 meters while you're pumping up. So that's where viscosity comes in. So viscosity in normal drilling terms is the thickness of the fluid, but I'll get to the properties of the fluids. And like I said, a big factor of removal of cuttings is pump rates. There is ways that you can quickly on site determine what is the pump rate that the guys are using. Each and every bit do have a pump rate setting as set out by the bit manufacturers. So, and that is just to quickly see whether you're in that rate or not. And we also try from our side, from Imdex side, is we also try and train the drillers that they need to use the correct pump rates. A part of not using, if you have too excessive pump rates and you're drilling in a very friable formation, that might also cause the hole of collapsing, and you might create cavities because you're pumping too much water up into the annulus. So just for information, so the recommended pump rates for drilling NQ is 30 to 38 liters per minute. For HQ, it is 38 to 45 liters per minute. And then for PQ drilling, it's 68 to 87 liters per minute. And this is really, really important to stay in these parameters that's been set out by the bit manufacturers. And thinking of it, all the bit manufacturers have the same pump rate that they set out. Another very important function of a drilling fluid is suspend cuttings when circulating is stopped and to release them at surface. So what does that mean? As you pump and the drill cuttings go up into the annulus, it gets onto surface, it goes into the settling pits, into the sumps, When circulation is stopped, and this is a very fine line, and you haven't done a bottoms up, there is still drill cuttings in the annulus, and you also have the drill cuttings on surface. So your viscosity must just be inspect so that once you stop, the cuttings in the annulus doesn't fall back immediately, but the cuttings on surface must be released. Also very important on this point is the site layout, how the guys are setting up their pits. So normally people will think for a settling pit, it need to be a wide, deep pit. No, it must be wide, but it's not necessary to be that deep. So why I'm saying this is as your fluids enter the pit area, it must take a very long time for that specific entering of fluids to get out to the other side. In that time frame, the viscosity mustn't be too thick, otherwise you're going just to pump down the drill cuttings back into the hole. Preventing stabilizing geological formations, allow maximum information gain. It all comes to prevent caving of the borehole. And this is where maintenance of the drilling fluid that's been recommended for this specific drill hole or project. This is where it comes in to be maintained. If the drilling fluid is not maintained in the spec that's been set by index, you might lose the borehole, especially when you're drilling in shales, kimberlite formations, swelling clays. Very important that the driller maintains the specs that's been set in the proposal that's been given through to them. Control subsurface pressure. It's very rare that in slim-hole drilling. So slim-hole drilling is normal core drilling, like we know, we all know it. So very important, or not important, but it's in rare cases that we need to add weighted agents to keep the gas or the water inflow contained in the borehole. But like I said, in slim-hole drilling, it's once in a blue moon that you do get the application where you might drill into methane, and then you need to have what we call weighted mud system. Otherwise, it's just normal drilling with a lubricant and a polymer. Provide buoyancy. It is just, I mean, buoyancy said it all. Outside the borehole, if there's still water in the borehole, outside the borehole, the drill string have a weight, but when you put it into the borehole, the weight is still there, but if you drop the rods, it won't fall like a rock out of the sky straight to the bottom. That is where the buoyancy support comes in with rods and with casings. Is there any questions regarding the function of the drilling fluid? Nothing. What counts as a drilling fluid? Any fluid is any medium which is circulated through a drill hole during drilling operations. This can be air and water, air and polymers, foam, bentonite and polymers. So in short, even in RC drilling, in production drilling, in normal DTH, there you can use fluids like the foams, and then in the core drilling side, it's basically polymers, bentonites and lubricants, and there we talk about a water-based mud. Other muds that you can get is oil-based muds. That's more for the oil field, oil and gas industry. And then the synthetic-based fluids, that's also more towards the oil and gas sector. But in slim hole drilling, we're using water-based mud. So in other words, you have two parts. You have water, that is the one part, and you have the drilling fluid, that's the B part, and you mix the two together. What are the major properties of a drilling fluid? Remember earlier I've said, there's parameters where this fluid system must be in. So what do we use to set out these properties is viscosity, or as we all know it in the drilling industry, is the thickness of the fluid, weight or density. Sometimes we also need to have a filter cake. I'll go in a bit more depth into it when we get to point 3. Then there's the solid contents, TDS, and then very, very important, and actually point 5 must be point 1, is the quality and the type of the makeup water. I'm just going to, in very brief, discuss these 5 points going forward. So viscosity is, like I said, it's the thickness of the mud, and you get viscosity by putting polymers into the water. You get liquid polymers, and you get powder polymers, and then you get bentonites. That is actually a clay that gives you viscosity. Now, the powder polymers, number 1, can handle more bad quality water than your liquid polymers. The reason for that is liquid polymers have already plus minus 50 to 40% water in it, where your powder polymers is anything from 98% active. The only difference between the two polymers for the drilling industry is basically the liquid polymers are mixing in very easily, where with the powder polymers, you need to have proper mixing equipment. If your muds are too thick, you can easily dilute it to get it back into the correct properties. You can reduce it by just adding water to it, or adding thinners to it. Specifically in a bentonite system, you will use a thinner to bring down the viscosity. For those that don't know what's on the right-hand side, this is the item that we use to measure viscosity. So just in short, you will fill up the funnel part with the drilling fluid, and then you will take the time what it takes to fill up a 1 liter bucket. Now, normally we will set out properties of 33 seconds per liter up to 38 seconds per liter, depending on the type of formation that's been drilled. So if you drilled a straightforward formation that is not broken, you will go with a 33 second Mars funnel reading. Just to give you an idea, water is 28 seconds per liter. So when you get towards, a 30 seconds per liter, it's almost water that you use. Now remember, viscosity plays a big role on cleaning the hull from the bit face. But normally running between 33 and 38, that is a fine viscosity. The other thing of viscosity, why we do viscosity checks, is viscosity is giving you a quick idea of what's going on down the hull. So if you have all of a sudden almost water coming out, there might be an influx of water into the hull. Other influences on viscosity, if you're drilling a very active clay zone, So the clays will take a lot of the properties out of the polymers, and by means of that, you will also see there's a drop in viscosity. Weight or density. Again, if you drill in an area where there's gas, you need to have a weighted mud system, and this is the item that we use to do mud weights. This is called the mud balancer, but in slim hole drilling, mud weight for us gives us more indication of how many solids do you have in your system. So if you have a lot of solids in your system that did not settle out in a surface pits, you will have a very high mud density. In South Africa, we use the term SG, specific gravity, as mud weight. In normal drilling fluids, the mud weight would be around about 1.01 SG. As this mud weight goes up, like I said, that will give you an indication that you have too much solids in your system. You need either to dump the whole system or start diluting. Also very important, you don't want to run with a too high mud weight, because that can causes fluid loss into the formation, and even do some hydrofracturing if you're drilling in very, very porous formations. Filter cake. So drilling in formations where it's very broken, drilling in formations that have shells. As your drill bit goes into the virgin ground, we use the term spurt lost. So before the drilling fluid can do any work, you have an amount of fluids that penetrates into this formation. Now, to cut down on the spurt loss, there's various products that you can use to build up a filter cake. Now, building up the filter cake will prevent the fluids from entering into the formation. But again, depending on the geology of the hole, will depend what type of formations, what type of drilling fluids we will recommend. But this is what filtration, we talk about filtration control, and the only way how you can prevent filtration is by having the building up this filter cake with certain polymers and even bentonites. Solid content. This is the item that we use to do a solid content. It's really that you need to dump your settling systems or your sumps, but sometimes what might cause a buildup of solids is your colloidal particles, especially when you start drilling in clays and in kimberlites. So your colloidal particles is so fine that it does not settle out. The only way how you can settle out colloidal particles is to use a flocculant. So what the flocculant will do is the flocculant will attract all the colloidal particles to each other till it's heavy enough, and then it will settle out. But almost must to have on site to check from time to time how much solids you do have in your system. Then the last one is water quality. If you have really bad water, like in bad hard water, high chloride content, then there's only one or two products that will work in this environment. So it's very, very important to know your water, to understand what is in the water before you start doing any drilling fluid mixes. Bentonites don't like high chloride contents. So for bentonites, you need almost to have clean drinking water. For our drilling fluids, a high pH is always good. So we look at a pH of around about 8 to 9. If the pH is a bit too low, there is additives that one can use to bring up the pH. So what do we test for? We test pH, we test salt content of chloride content, and we test water hardness. Now pH and water hardness we can treat, but unfortunately there is nothing that can treat out chlorides. However, like I said, there is natural polymers that work well in high chloride content. There's even polymers that you can use when drilling near the ocean, that you can use the seawater and mix these polymers in. So that option is there. Oops, sorry, I'm rushing through my presentation. Apologies for that. So, summary of selecting a drilling fluid for mineral exploration. So there's a couple of things that we from IMDEX side need to understand to give the best drilling fluid mud system to the driller, so that the driller can get down to TD, so that the geologist can gain good quality core, good quality hull, to get all the information out. So the number one is you must ask yourself of what is the primary purpose of the drilling program. Very important to go in with the right products to cover all the geology formations you can go through. We need to understand what type of rock will be drilled, and then the site layout is also very important. You need to have, if you're drilling a very deep hole, you need to have sufficient surface volume so that you don't run out of drilling fluids. And then what we bring to the table for the drillers is we give training to all crew members on regular times. Sometimes the guys, drilling companies might ask us to come and train their crew. And like I said, we also do this at this stage at the no charge. It's very important for the drilling crews to understand why they use the drilling fluid and how they must use it. If they don't understand that, then it's just going, then drilling fluids will cost you money. So a very, very important factor, a part of having the right water quality, is having the right mixing equipment. So at IMDEX, we do have, like I said earlier, we do have liquid polymers and we have powder polymers. So when using powder polymers, it's very important to have a proper hopper system or a centrifugal pump, so that you can share these powder polymers, and in order for them to go into the water and to give you the properties that's needed. Drilling fluids also, whether it's powders or liquids, needs to be mixed for at least 10 to 15 minutes to get to the desired properties. Sometimes if you're on site, you will see, we call it fish eyes. It really looks like fish eyes. And that immediately tells you that the people on site, number one, might not have the right mixing equipment, but the product is not mixed in long enough. So having the right mixing equipment, having the right water to mix drilling fluids, very, very important. Then just in general, there's a lot of drilling problems. Most commonly is lost circulation. This is where there's a dry fissure or a cavity or a crack in the formation, and all the drilling fluids are just running into this. And as you drill, you need to add water, you need to add drilling fluids, but we do have circulation loss material that we can add into the borehole to try and stop the circulation loss. Stuck pipes, again, various of reasons why you get stuck pipes. So like I said, a whole lot of in-hole problems, but by having the right drilling fluid and maintain your drilling fluid, maintain normal drilling practice, you can go through very, very difficult geological formations that's out there. Again, mud problems, we're looking at mud mixing, like I said, solids control, cutting settling, and like I said, we did discuss it earlier. So we do give some advice on site layouts if needed, because if your site layout on your surface pits are not correctly, you will start pumping sluts or drill cuttings back into the hole, and that also can cause you stuck pipe. So we take each and every problem as it comes up and see what solution we can put together to get the hole down to TD. That's all from my side. I don't know if there's any questions. Tanya, I would also share this short presentation if the need is there for. No issues to share it to the rest of the group. Thank you.
Thanks very much, Heine. That would be perfect if you could send me the presentation by email, and I will make sure that it gets out to everyone.
Cool. No worries.
I see there is a question in the chat from Eric Hansen. Under what conditions can diamond drilling be done with no additives, no polymer, bentonite, etc.?
Eric, good question. You can drill with water, just with water on its own, but your wear and tear on you will not get, number one, a good rate of penetration. You will not have adequate hole cleaning as the hole getting deeper. If you're drilling in BIF, specific that have a high SG, even shallow holes in drilling in BIF, you will not get good rate of penetration, bit life, and as your hole getting deeper, you will see that your torque will also start getting up. So I will not recommend drilling with just straight water. I hope I answer your question.
Yeah, thank you. Can you hear me?
Yeah.
Yes, we can.
Yeah, I was just wondering because I was on a drill job in Sweden last year and they only drilled with straight water, whereas I'm in Chile right now and they always use polymer.
Yeah, but again, it all depends on the formation being drilled. But like I said, you think you're getting rid of all the drill cuttings, but your larger drill cuttings, you will have regrinding on the bit, and that is where rate of penetration comes in and bit life comes in.
Ah, okay.
Yeah.
Okay, thank you.
Do we have
No problem.
any other questions from anybody else? Just raise your hand and ask your question. Okay, Hanno, thank you
Okay.
ever so much
Yes.
for your time and expertise this evening.
Yeah.
Really appreciate it.
No worries. Thanks a lot, Tanya. And again, thanks for inviting us. I really appreciate it from Index side. Yeah.
Pleasure indeed.
Thank you.
Okay, Masi, are you available?
Hi, Tanya, I am here. Can you hear me?
Yes, we can. Okay, wonderful. If you will start sharing your screen, let me just do the brief intro, which is who knows where.
Do you want to start now, Tanya? See, it's 10:37 on my side.
We are a little bit early, but just we start now, and then we can take maybe a little bit of a longer break after your presentation.
100%.
Okay, so we have Masi Zintwana, who is the section manager or control at Anglo American. He has an MSc in geology from WITS and is currently studying an MBA through the University of Suffolk. Masi has more than 12 years of experience in minerals and in the mineral industry, including leading the largest exploration project by an Anglo-American business unit in Africa. Masi lectures part of the BSc Honours Economic module at Free State University, primarily on drilling and basics of core logging. He is a fellow of the GSSA and currently is vice president of the branches and division portfolio. So with that, Masi, all yours.
Thank you very much, Tanya, for the introduction, and thank you again for organizing this stellar meeting. As you heard Colin and I earlier, I was saying that it's one of our yearly highlights. So it is indeed a great pleasure for me to be here, and I appreciate the invite and this slot specifically. Thanks everyone for also participating. So the part of the talk I'll be talking about on my side is what geoscientists need to know about borehole logging. And to get into that, we'll roughly cover 6 high-level topics. Some of them I will get into some detail, some of them maybe not so much. So if you do indeed want me to touch on certain topics in between, do please raise questions in the chat. If you feel that you want to interact, please raise your hand and we will then take the call and the question and then move on. So the intention for me largely in that is not to necessarily talk for the 2 or so hours, but to basically have an interaction to some extent. So we will have some context that we need to set in the discussion about why are we doing this. Then drill management, and a lot of these aspects are things that Colin already touched on, and some of them in the previous talk by Heino in terms of what considerations you need to take. Then the drill methods QA/QC, and this will focus particularly around core logging, since that is the largest part of this talk. The logging itself, and then some parametric considerations. And this for me is probably the one differentiator as a geoscientist that you need to keep in mind. And the last part is just beginning with the end in mind. Before we jump into it, and as Tanya said, I am an employee of Anglo American. I am also a fellow of the GSSA and registered professional scientist. Even though participating annually in this event for me is sponsored by the employer and giving this in my personal capacity. So anything I say is not and should not be taken as a comment that is attributable to my employer or the GSSA or SACNAS itself. I will try and be honest though in the talk. So before we jump right into it, may I request that you either scan or jump into the forms of this. And as we go along, please, we'll come into these questions that I need you as an audience to reflect and answer. It takes about a minute to complete the entire survey that I've put up there. But as we go in, we'll touch on on these questions that are put in there. And obviously you see there's already one response when you get in there. That's what I reflect as the day I started working, what I would have wanted to know about personally, that is about logging. So feel free to put your answers. And the first consideration, I think, right up front is, what would you want to know about logging? If logging is not something that you already are doing or knowing, even if you are knowing and are a logging professional geo, are you comfortable that what you know about logging is what the intention of the exercise is? So jumping then right in, and I'll come back to the answers as we go along, is setting the context. Just move this. Is in establishing why you do the logging. It's all around the concept of reasonable prospects of eventual economic extraction. And this is now applicable particularly to mineral resource management. Other forms of drilling would have a different framework of managing. And the key aspect in this part is the relationship of what we call mineral resources to mineral reserves. And as you go about your drilling campaign, for whatever the reason is, with time and more drilling, more logging, and eventually modeling, you're increasing your geological or geoscientific confidence and reporting in situ mineralization and the estimates. With application of modifying factors, and assuming now you have a reasonable prospect of eventual economic extraction, the consideration is around modifying factors that talk to your mining, metallurgical processes, infrastructure, socioeconomic factors that impact your ability to extract the commodity with which you are planning to do, and applying that into your resource statement essentially gives your mineral resource. And what that means is, much as we understand that mineralization and ore bodies are 3D entities, it's a careful and delicate relationship that we need to manage between what is a resource and what can you economically extract. And depending on where you are then in the mining value chain in that process, you'd have variable considerations of what type of drilling you want to do. Most of the talks that we give in this nature, most of our focus is around exploration drilling, which is about delineating and estimation eventually of economic deposits. And there might be different stages even in there between reconnaissance, the actual prospecting, defining the resource estimation and sterilization campaigns when you want to consider concept studies for infrastructure development. And all the way into the operation of a mine, where you have aspects of grade control variation issues that you still need to drill for. Maybe core drilling might not be the method that you turn to. Might be other options, as Colin touched on this earlier. In some instances, and which is something that's fast gaining traction in this day and age, is something called geometallurgy, which is basically the integration of, let's say, physical properties of the rocks and how they physically behave in your mining and processing processes, systems, to be able to extract the maximum value out of the ore body. Typically, most of the grade control we would do historically would be focusing purely on grade, which is what analytes you're dealing with, but the grades alone does not mean that your liberation and other processing consideration would be optimized. That's where geometallurgy as a field comes in. And obviously then there's always brownfield, which is trying to keep your mine economically producing as long as possible, and close and on lease exploration, that's where brownfields would sit, and drill and blast, where you need to blast hard rock particularly. You might still need to do further drilling in that space. But again, there might be a couple of considerations of what mining engineers want out of that, that you need to take in as a geoscientist. And failing those results, you would need to come back to that. The key thing, though, in terms of why drill to begin with is the fact that anything you see from a surface point of view is largely an XY expression, which is the 2D geological information, a map, a model in plan view most of the time. The third dimension is basically what you want to see from drill core, trenches, road cuts, or sidewalls of a pit if you are in an open pit environment. But again, ore bodies are not 2D, they are 3D entities. So the logging aspect fundamentally talks to, in the absence of any of the road cuts, outcrops, and trenches, when you have drill holes and drill core particularly, what is it that you're going to look for in the third dimension, in the Z dimension, to complete the story? As I've been saying in the previous slide, you'd see that here is basically a summary of a mineral system. So what is a mineral system? And this is what basically sets your broad scanning view of why you're logging. Is any economic deposit is anomalous in nature, meaning that it's a concentration of a particular commodity metal in a particular horizon in a controlled fashion, which is different from the surrounding rocks. It could be the same rocks that you're dealing with. It could be host rocks, which are fundamentally different information and age from what you are targeting. And the four basic things you are looking for is a fluid and a metal source. Where's the fluid and the metal that you're concentrating generally coming from? How is it moving to where it gets trapped? That's the second part. And the third part. And obviously, once you have your concentration mechanism and you're forming the mineral deposit, the excess fluid that has nothing to do with upgrading or preserving your mineralization needs to escape the system. And this outflow in other areas would typically be expressed as a flushing mechanism. And the idea is, if you do not flush, you cannot concentrate behind in enough scale the metal or the commodity you're after. No concentration, no deposit, straightforward. And in most ones where there is a fluid in a form of aqueous fluid being mobilized in some sort of plumbing structures, geology structures, there is obviously a fluid rock interaction. These are telltale signs of what is happening in your local and regional spaces. In the form of tectonics, most of us being geos, you would recall that tectonic events have major influence of certain types of deposits. And you see that you can have convergent, collisional, and extensional tectonic settings. And down here at the bottom in each view is geological time scale from present to about 3.5 billion years back. And you see where supercontinents have been identified to have formed. There is a general concentration of certain types of commodities. And for the case of South Africa, those that are here or in SADC in general, you would want to see, for example, the concentration of IOCG type deposits, and Australia is also quite big on this, would typically be anywhere in the Precambrian and the Archean. The likes of the Bushveld and the Great Dyke sit in that space, and in some places like Namibia, where porphyry, copper, and gold deposits are becoming one of the things that people are after. It's much younger in the Pan-African ages in the South African or African context. Why is this important? You may ask in the context, because all of it formulates the field settings. And the important thing here is you know what your 2D view is, and you know where surface expressions of what you are looking for as a commodity looks like. And you start off with a view of this nature where you're having delineation of where potential mineralization is, and how it looks like in the XY view, but you do not have the picture of the Z axis if you can. And obviously that talks to your stratigraphic section. What you're looking here at here and the previous slide is part of the Transvaal supergroup. And showing here is basically where iron or high-grade iron ore is being hosted and the overburden that is associated with that. And the importance of field relations is to know, once you have drill core in front of you, what are you basically dealing with in that drill core? And can you place yourself in that core where you are in the stratigraphic column? We'll come back to the image in the right a bit later again, but it's the same sequence of rocks, if you will, just not sitting in the stratigraphic order, and there's a number of reasons around that. So before we jump into then the drill management, may I just remind you of the plea I already put up earlier, and indicate that there is another question in there, and you'd have seen by now. The question is around just to set me up and set up the rest of the conversation. Give me an indication, and please answer all the questions and go back to the end and just submit what we're dealing with in terms of this question. So if we just allow me to bring this to your view. Those are the current responses at the moment. In terms of the first question, that's what most of you is saying. Good practices, logging, data, core importance, the impact, technical aspects, and half of our audience at the moment that have responded is less than 2 years of experience. And there's some, I'll be interested in this group of 5-year plus. I know I'm part of that group. I'll be interested in knowing who's in that group. So please do feel free to raise your hand and comment in some of the things I say, and let's have the discussion as it comes up. So as the responses are coming in the background, I will then continue. So, drill management. Colin touched quite a lot on this. And in this part of the discussion is basically going to take off, what do you do to manage your drill campaign for the end in mind story I was talking about. What that means is, much as you as a geo are not a driller, to get the best result out of your logging, you need to understand what the driller itself and this equipment that you use in your drill campaign does and does not do to your samples. Because it could be very easy that you do not know, you cannot tell, and your interpretations and your logging is compromised as a result. So what you have here is a diamond rig, and it's a platform rig. It's a type of a diamond rig. It's a coring method, and Colin would have gone into great detail of this. General site layout, and I picked a very old rig for this purpose, is for me one of the few examples I have worked with that shows general good housekeeping. You could be in the middle of nowhere, far from everything, and you need to make it as convenient as you can for the people that are doing the work to get the best out of results. So if you're not familiar with the drill site layout, The rig itself, the string and the rod, the drill string and the core barrel and the hole are down that part, as Colin was talking to. Lying in front of the rig there is what is called the core barrel bench, and there at the top would be the inner tube that is going to be used potentially in the next run. This is a wireline method. As you can see, there's a thin rope running through the pulleys there coming down. And there at the back, just next to the engine there, there's a drum. It's a reddish thing sitting in there. That wireline is a wireline hoist drum. And in there, that's where the up and down hoist system of retrieving samples sits. Important, the previous talk was talking about drill fluids. There you have the old fashion of making a sump. And this sitting in here is what is being dug out of the sump to make sure that you have optimal fluid circulation. And as you drill and you put your samples in there, you retrieve and wash the core, obviously you have to put it in a core box, and that's where you are, and you have stash depending on how you're drilling. The tank at the back is just to make sure if your sump runs dry, you have a backup water that you can use on the site to keep your water pump running, because you don't want to run that pump dry, because downhole friction increases, cuttings are not being washed out, steel, rock, all together cook under the friction and the revolutions that the rigs will be putting out. And the next thing, you have lost a hole in samples, which then calls for efficiency exercise. The drills come in many designs and forms. And some of the aspects that you as a geo need to also consider are non-technical aspects. In this view, you're looking at a different type of a drill rig, still diamond drill rig, different configuration of the operating panel. And as you can see, problem number one, you'd have to deal with, and you'd heard Colin talk about legal liability. There you are having an operator that is sitting on top of a drum, on top of something else that is a makeshift chair. Legally speaking, an inspector can't stop you if you have a site like this. But more importantly, you can see the background of where your drill rig is. It's within a community, and you will be generating quite a significant bit of noise in your drill campaign if you are drilling close to where people live. And being able to execute the work you have to do, you have to be mindful of what socioeconomic agreements and concessions you might need to get from the users and owners of the land within which you operate. You would hear most of these aspects in the mining industry space coming up in sustainability reports and in the form of ESG commitments that mining houses make. And long gone are the days where get in someone's backyard, drill a hole, and tomorrow you're mining. All those non-technical aspects are becoming fast and quickly becoming top priorities for many investors. And it's what you as a geo have to set yourself up to pay attention to and make sure that you address. Certainly, for Anglo-American, obviously, that safety is top of mind. And I will say this is not an Anglo-American site. It is a site that me, myself, as Masi has worked on in a different project before. How does modern technology and considerations of how to manage site and influence where we're going as an industry? This is a newer version of what is out there in terms of drill rig technology. The previous two ones, if I can just go back, there's the rod handling system and the wireline. Up there would be an assistant manually handling the rods. The gentleman sitting in there would be standing on that wood pellet there and manually handling the drill rods, as Colin was explaining the hoisting system, and putting them on this stand here in front of the drill rig. That is a manually intensive exercise. The only help the drill rig gives you is pulling it out of the hole. Once it's decoupled, it's a lifting exercise manually. So to put each 3 meter or 6 meter, however long your drill rods are, on these benches. Newer technology, you have automated rod handling capability, and hoisting systems that are included in the drill rig. And you can see some of them carry bigger hoist drums for the cable work. And you would think that technology in this day and age means less employment for people. In the previous sites I showed you, you could operate those sites with 3 people, an operator and 2 assistants on each site. And minus the gentleman standing there being a supervisor, you can see this site is operating with 4 people. The one in the background is just an Anglo person visiting the site. The point I'm making here is technology does not automatically always mean reduction in numbers of people that work on your drill site. It is important to translate the message why you are introducing changes, and the changes of this nature are changes that are there to help the people that operate the drill rig and are entrusted with your core samples while the drilling campaign is underway. The second part of the site is you'd see these drums sitting here at the back. These rigs and this setup is one of the initiatives we took that moves away from digging sumps in the ground and runs rather in contained sump systems where filtration runs through a drum. And at the end of the site, the only thing that will be left here that showed that we once drilled here is a 1 square meter footprint where the drill hole is, and showing the collar position of the big drill hole. The rest of the land around it will be rehabilitated to the background until such a time where mining, if that's where you're going, wants to take the exploration or the mining value chain goes forward. Obviously, when you do the drilling, you have to bear in mind, are you doing the green or brownfield exploration type drilling? Critical is manage your drill program accordingly, because it's not about having a hole in the ground. It's your roadmap from converting a resource development strategy or a plan to a life of asset plan if the intentions of the business or your client is turning economic. The geology can make or break a project. And this I cannot emphasize enough. You get the geology wrong, your project is dead. Not every exploration campaign, and the conversion rate is generally less than 20%, much less, in fact, of what starts as an exploration project that ends up, particularly in Africa at this stage, as a mine. And there's a number of reasons why that happens, but it all boils down to reasonable prospects of eventual communication, economic extraction, and what you as a geologist communicate throughout the project as value in the ground. And prospective areas and what brownfields, the difference is, for those that know, greenfield refers to a completely virgin ground in the middle of nowhere, no mine exists. Brownfield, there is an existing mine, you see an opportunity to expand in a particular direction, and your local geology and field setting tell you that maybe you are onto something, and that informs your drill management. Obviously, drilling is not unique to geology. As I said in the previous slide, it is definitely not about the hole in the ground. And arguably, when you as a geoscientist are part of a drilling campaign, there are 2 important outcomes you want to get out of a drill campaign. One is samples you can trust, and this is in no particular order. Samples you can trust and always go back to, and all the people that work with you on that drill site get back home safe. As I said and indicated earlier on, most of this is about core drilling, and particularly diamond. Why you want to pay attention to this? Because it is, comparatively speaking, non-destructive to the internal structures and textures of the rocks you're dealing with. And as you can see, relative to what you would get out of a chips sample, you can still see the relationship of all the textures in the core sample, and you can see the original lamination in this piece of core sample. So if you drill something like percussion or dual tube reverse circulation, as Colin was explaining, you would be destroying all those internal structures and textures you want to capture. It is also your opportunity to get the most representative sample of the in situ rock features. Remember, you are not logging for the core itself, you are logging for the ground within which you drilled that core from. So whatever you're describing needs to be as representative as possible of the XYZ of where that drill hole sits. It is, however, time consuming and relatively expensive when you consider the other drilling methods, much as the rotation speed is possibly the highest in diamond drilling compared to the other methods Colin was talking to earlier. The rate at which you recover the samples is actually even slower. And because of its slow and the expensive nature of the equipment, it is cost intensive. And to achieve all of these top four, obviously it calls for regularly checking in on your drilling quality, because this talks to what you would call a sample representativity index. This becomes very important when you transition into the discussions of mineral resource evaluation and knowing that what your target rocks at depths are, not the depth of the hole. What target rocks are you looking for? You could very well design a borehole for 250 meters and end up either finishing that hole at 150 or worst case, even much closer to 500 plus meters deep. So you're not drilling for depth, you're drilling for end of mineralization, if you will. And you need to know very well what your regional and field settings are guiding you towards that. And that's why this aspect of drill management is important, because it's not logging itself, but it is a methodical approach to making sure when you do eventually do the logging itself, you are capturing the most correct version of events, representative of the ground XYZ within which that borehole comes from. Going to get core samples, obviously, from your core drilling exercise. And these, this table just shows these types of core sizes, depending on the diameter. The one you want to pay attention to generally is the metric system. And for normal exploration, you'd typically be between the BQ and NQ hole, depending on what purpose that borehole will be serving. And the core diameter you're looking at fundamentally, especially in the JSE and SAMREC code space, you're aiming for about 5 millimeters of core sample. The whole diameter you're dealing with, you can see, is much bigger than that, relatively speaking. And these are the annular thing that Colin was talking about to make sure that your circulation system is functional. Your metallurgical core samples typically aim for the bigger core diameters. What I do want to highlight to you, as you can see, the whole diameter of an NQ size is big relative to the core you retrieve in this case, because the assumption here is you are dealing with a wireline drilling methodology, and the curve you can use there, if you remember what curve is, as Colin was explaining, is much thicker and your sample is thinner. It is an opportunity, if you are experiencing problems, before abandoning the hole and understanding drilling, assist you as a geo to know that because I have a particular hole drilling NQ in that particular hole, if I switch and I do a conventional at the HQ size, I can retrieve bigger core, keep my hole diameter relatively comparable, and advance past the problematic area by simply changing the curve of your drill bit. For various reasons, you might want to do this. That allows you the opportunity to advance through adverse and problematic drilling conditions, such that you do not incur unnecessary expenditures and not retrieving samples, and in the process frustrating your drill service provider if it is contracted out. If you are managing a drill campaign on behalf of a client, you do not want to frustrate the drilling guys and at the same time incur costs on behalf of your client. So understanding that entire exercise is important. Colin did touch on the cost implications as well. And this just shows a real case that I've worked on. I've obviously removed the financial figures here, not to raise eyebrows in this discussion, but the profile is representative of a true case. Between concept and post-mining rehabilitation, you need to be considering what your cost movement is going to look like. In your exploration space, you are building up costs and no returns. But those costs, as intensive as they are relatively minute considering what you will be incurring in a full-blown exploration. Because in here, you are still validating your target generation. Once you start the actual exploration, your costs for drilling climb until such a time you can hand over to mining, where your need for drilling might slow down, but it does not completely disappear. And this for me is the important bit for geos. Most geos would be doing exploration and logging and early drilling and logging for the first two arrows, if you will, where you want to get to the answer as quick as possible. And there is life forgotten that comes after your R&R statement. So bear in mind that you will be expected to give insights, whether through your original log or additional comments later on in your mine value chain. So do prepare and set yourself up to have those answers. And somewhere in the life of asset plan and the budget processes that your business or your client might be running with, that you do highlight upfront what sort of costs need to be taken into consideration for continuous data accuracy and all body knowledge to set up the operation for the best success. And obviously, when it starts closure discussions, it even drops further the need to do drilling, because at that stage you are winding down operations. But you might ask yourself, why is this kink there? As I said, this is a real case. This is the brownfield exploration coming in to say we realize that with changing economic and socio-political conditions, there's an opportunity in this particular area to expand the operation. You want to invest, and articulating that investment very well is very important for accountants and mining engineers, because that's what guarantees you the time to do the drilling and the money to actually do it. As I've been touching on risk in the previous slide, right here, I think I would propose we take a 5-minute break. When we come back, I'll display where we are in the survey. And I think if you haven't completed or you haven't started, you might want to scan again in this thing. I'll leave this version on the screen. Do please answer the questions so far. Tanya, can I propose now it's 11:15? We take a 5-minute break and I'll start at 11:20.
Yes, Masi, no problem with that. In the meantime, can you please raise me as a co-host and also Camille? It's easier if we all raise a hand so that you can see where we are.
Yeah. Let me just stop sharing for
Both myself and Camille as co-hosts again, please.
Okay. Emil is wait. I cannot see Camille.
Camille, if you'll put your hand up. I know you were there a couple of minutes ago. Maybe she's fallen off again. No, it looks like she's fallen off again. So
Before I start, I'll just double check on that before we continue, Tanya.
okay, cool. Thanks. Mercy, can you pop the exercise into the chat box, please? Sarah, you've also got it, if you wouldn't mind.
I am back, Tanya.
Okay, Sarah has just popped the link to the exercise into the chat box. Somebody was looking for it.
Great, I see it. Thank you, Sarah. And I see somebody else is talking about a picture for one of the questions, rightfully so. Just posted the picture and we're gonna come that when we talk about parametric considerations, but you can take a step at it, seeing that most of us actually use. Okay. Just scrolling back up, just want to make sure I didn't miss any questions I haven't touched on. Hendrik Smith, as I share my screen again, you put quite a detailed comment. Do you want to perhaps unmute and let's talk about it?
I must say, yes, I'm happy to chat about it. Just commenting on something I saw in one of your slides, and it's something I've encountered in conversation with people a few times, is that there's often a perception that mapping data and surface data is only a 2D product, which I think lets many people miss out on actually fully making use of their geological information.
Most certainly, and I think it is a very valid point to make. It's good starting position, if you will. And the key thing, I think, for me in that discussion is, if you're going to put a drill rig on the surface of the earth in a specific geology targeting a specific commodity, it is very important as a geo, especially while starting out. In fact, even experienced one, to understand where and why you're putting that drill rig, because you need to be certain of what answers you're looking for, and those answers must be answers you couldn't get otherwise from good old mapping.
Yes, for sure. And I think obviously the benefit in this type of scenario is that what most mappers never get to do is while they can develop a 3D understanding, based on their interpretation, they never necessarily get, or they often don't get to test that understanding or get to test the model they come up with, which is obviously, if you put the drill rig there, you can now really test your understanding of the geology further, because you're getting hard subsurface data.
Definitely. Okay. I really appreciate that comment, and it's certainly most valuable. So please, if as a geo you do conduct logging, do keep in mind, why are you doing it? And certainly it's because you've drilled, but why were you drilling to begin with? Let me know if you can see my screen. I see there's still that delicate balance between the 5+ years and the less than 2 years geoscientists. I find this, I didn't expect this, Tanya. I think in post this, we can perhaps reflect what it means. I expected more than half to be starting out, which is the case if you consider that I'm a student and the less than 2, but the amount of, let's say, competent geos that are participating is also something that is a wonderful surprise for me. So in terms of the risks, I see in terms of what risk geoscientists are aiming to mitigate during mining, a significant portion says all of the above. Certainly you want to be clear of what are the sources and potential contributors to dilution and contamination. That basically downgrades your ore body. Financial losses, in the sense that you get the geology wrong, your mining might be inefficient, effective in your processing. So you do want to do that, have line of sight of that. And obviously a reputation, where you cannot deliver a product you promise clients that you want to deliver a certain spec of a product, and because your geology doesn't allow you, you cannot deliver that. And in some of your things, you have to either put out poor product quality or take force majeure, which marketing people do not want to hear, because it means they have to go back on agreements with clients, which often means penalties, and nobody can trust you. I did post the picture with regard to question 4, And as we continue, we'll come back to this one in the session. Just before I move on, is there any other comment or question? Okay. Soldier on again. Swap around. Sorry, we were here. Oh, so we did take our 5-minute break. Now we're talking about the drilling methods themselves. The drill methods and the QAQC, as I said, we are now focusing on this one on core logging. So most of these things you can extrapolate and by implication figure out how to apply them in other drilling methods. But please note the conversation here on is specifically focusing on core logging, predominantly diamond core, but you can get core samples from sonic drilling and other methods. But they are rare. So in terms of the QAQC, I think the key thing in terms of the logging, you want to deliver an accurate description of lithological properties as observed in the context of precise understanding of your field settings. And in the discussion we're having now with Hendrik, that's where your field mapping comes in. It is very crucial that you understand and get a feel of what your local and regional geology is, and where possible to generate a working model from there on already is very important. And when you drill, you're drilling to not only complete your view, but to make sure that your understanding to begin with is correct. It does happen where exploration and other models are used, even in the mining stage, where the mine has a mining model that they are using for the ore control space. But if you look at it and you think about it and you look at what the regional and the rocks are telling you, chalk and cheese. And what you want to do when you set yourself up for the logging is to make sure that you do not shortchange yourself and your business or your client or whoever you're doing the exercise for from what they would need. So certainly what we are aiming for as an exercise is to deliver good accuracy and good precision. In this depiction, you want to be on the bull's eye of what the lithological setting you're dealing with, and your description enables another geo, especially in the resource space, that might not have seen the core itself, or even in the production space, the metallurgists and the production geologists that might not have seen the early stages of developing a project. But if they go back and sift through the data that they have to their disposal, can understand fully on what Masi was saying. I can accept when accuracy might be off, but you still have precise understanding of field settings, and your descriptions might be a little bit off. These are the nature of things that give an opportunity to somebody else that might have developed further understanding to trace your steps back and see, okay, these were the misunderstandings and errors made in the description. We correct them. It helps a correction of the understanding and the interpretation. This is what assists the conversation around a review of a genetic model or an ore body model. What you do not want is too many different descriptions of the same setting, because that is neither accurate nor precise. And all it is a checklist exercise when you do your logging. So you want to make sure that you test continually what your genetic model is. And as you drill, you can place your outcomes of the logging in the field settings. And how you do that, you go back to your model, regional and or local model, as depicting the regional setting you're in. And if you plug in that hole that you've drilled, it must be a match. If it does not match the setting, either your logging is incorrect or the assumptions you went with in that model are incorrect. One of the two needs to be adapted. And it's an iterative process that you have to keep in mind. So the first type of QAQC method I would want us to talk about is where deflection survey comes in. And before we talk about what it is, I want to introduce to you a concept of directional deflection survey is dependent on a gyro technology, and what allows this gentleman here to do a wiggle with our birdie friend here is a technology that sits in the neck and the skull of this creature that allows that any part of its body can move while the head is perfectly stationary and keeping reference of its whereabouts. And it's part of its flight mechanisms to get its bearings correct. Moving on right along, the gyro technology basically has three components in it. Is a spin axis through a rotor, which sits in an intersection with the gimbal, and the whole concept of the gyro technology, which sits in the directional survey. And most people that drill deflections would want to use this, is what helps this tool as it follows your drill string or your drill hole depth to pick up and map a XYZ position of your hole, and as it propagates through the hole. Because you're going to make an assumption that most of your drilling is vertical, -90, and the assumption you can make is that your drill string follows a vertical path, but that is not necessarily always the case. So you want to be certain and have a checking mechanism, if you will, of how is my drill string propagating through the surface of the earth as I drill, especially if you're going to drill extremely complex geology or very deep holes, because very deep holes, what is a couple of degrees of deflection can end up being tens to close to hundreds of meters away from your collar position. And we'll come back to what collar positions are in a little bit later. What that looks like graphically is when you look at this graphical view, or you can look at it in an Excel view that says that your drill string, and this is compared to things, how far off is it deviating from what you're saying you're doing? And as you can see, with depth, your deflection increases. And the same thing when you look at it north-south and east-west. There is movement. What does that look like in plain view? Your drill rig could be standing there on the surface of the earth, but your hole with depth is going roughly northeast. And it does not necessarily mean it will always go that direction. It all depends on your geology, your complexity, and your operator's skill. What you do not want is to not have a view of this deviation and make an assumption that you are drilling vertically. Obviously, in other cases, there is a special case why you want to also do directional surveys. And as I said, it's for deflection purposes, where you would drill a mother hole that goes in a particular direction to a certain depth. Once you're done, instead of pulling all the way to surface and drill multiple holes, you pull up to a certain depth above the mineralization zone. You insert what is called a wedge, and you deflect the drill string on purpose in a particular direction to intersect a different portion of the mineralization. And these different deflections are what help you string your mineralization network and ultimately inform how your mineralization is sitting. Most gold and platinum operations like doing this in precious metal space, but that is not the only application where you'd want to do deflection surveys. Especially if your mineralization sits deep for underground operations, you want to be good and have your drillers good at managing the direction of the drill string, and have the directional surveys being done to help you manage and make sure that the data you gather is both repeatable and reproducible. The second part of QAQC we want to talk about is the material recovery. And in simple terms is you drilled a certain depth, or you advance a certain amount of thickness, depending on how you want to call it. Did you recover the same? And how far off have you? In this example, the runs are about 3 meters, and you recall that Colin did touch this. It might be 3 meters, might be some other figure depending on your core barrel and inner tube configurations, but typically 3 meters. And you see in this, the run starts at 965.5, it ends at 968.5, and that is 3 meters. But the question is, did you recover 3 meters? So the two things that are most important here is, what do your rocks look like, and what did the operator do? The things that you're going to be checking for in this conversation is, how is your core in general packed? Where the depth markers sit versus your core, and locking ends. I'll say that this is potentially a very important thing that most geos overlook, and I dare say the younger ones do not understand. When you pack a core box, it is packed left to right, left, right, top, down, and you read it as you would read any book. It does happen when your drillers retrieve the core from the inner tube, because it's open at 2 ends. Depending on how they take it out, do they take it out of the bottom or the top end? They can place the core in the core box in a jumbled manner, typically upside down. And if they do this long enough and inconsistently, you might be troubled picking out the natural progression of your rock sequence through your drill core. Now, this is fundamentally important, because the only way you can test continuously, where you see they had a break in the core, they stopped drilling there and they started drilling again. Where possible, in this case, it would be very difficult, because on either side of the depth marker, it is broken. The ends of the core need to fit together. And where the core is solid enough, they can even lock. There is exactly one position where if you tightly fit them together and you try and twist, the twist resists your hands. And that locking feel is telling you that is the only way those core pieces fit together. That is how you test the locking mechanism. And most geos overlook this part. The broken portions, just because it's broken, does not necessarily mean you cannot test it. It means in those broken pieces, there will be portions of core that stitch together exactly one way. And when you glue them in your mind together like a jigsaw puzzle, back together, they form a surface that locks with the other side. You do not need to twist hard, because it would be a very futile exercise if you do, and time consuming, I might add that. You want to give yourself the absolute certainty that these pieces go together, even though there's a depth marker between. Because if that depth marker is not sitting in the correct position in the drill hole, then any of the following material recovery techniques are meaningless. So you've satisfied yourself, the core is sitting left to right, bottom up, right way up. And you can string all the core boxes together from the first one to the very last one in your core. And if your hole is 900 meters plus, that is a very long exercise. So goes back to what we were covering in the previous session, your drill campaign management. You do not wait for you to reach 900 meters. You do as you go. And we'll come back to this point, but it's part of your chain of custody of what happens in each core run in each core box. Then you as the geo that is responsible for logging that hole can tell. If you cannot do that yourself personally, make sure you know how to reach who was managing the drill campaign. Hopefully it is your colleague or your teammate that you can always reach out to them if you encounter a problem, so that you address the issue before you move on and you log. Because again, you log things that are not representative of the ground, your geology is incorrect, your assumptions going into the resource and reserve model discussions and subsequent mining are flawed. Now, the first recovery method you're going to look at after assessing your core packing is going to be what is referred to as the total core recovery. You preferably want to do this at the drill site, not where you're going to be logging. In some other campaigns, like some of I've worked on, you have multiple drill rigs, up to 30, depending on how big your campaign is. And it might not be practical for the number of geos that are available to do this with your technical support, non-drilling technical support, that is, to do total core recovery for all the drill holes at their drill sites. So you might want to move them to a logging facility a couple of kilometers away from where you're drilling. So bear that in mind, and when you do the transportation, just know that there are risks of handling that core before you do this. However, what total core recovery is what is the entire length of rock from that piece immediately after the previous core run to the one that you are stopping at, basically what's your advance. If your advance was 3 meters, did you recover 3 meters, yes or no? In this example, we're saying our recovery was 2.98, so there's 2 centimeters short. Depending on the commodity you might be logging in, you'd have to have a sensitivity in your sample representativity index that talks to TCR and tells you what is the allowable percent in terms of thickness that can be missing to accept a run. Most agreements would say the drill contractor must deliver at least 90% recovery. What that 90% recovery is referring to is this TCR. What that means is if you drill 90, you recover 90% plus of your 3 meters, then you are delivering on the contract. Otherwise, there is a penalty that might be imposed by the client or you if you are the one conducting the drilling towards the drilling contractor. And what the nature of the penalty is functional to what the contract is. But bear in mind, please, the contract has cost implications for you and the drilling service provider if it's a contracted exercise. And these are type of the things that you need to consider as Colin was talking about. So in a normal 3 meter run, you can give yourself a rule of thumb that says your recovery must be at the minimum for every 3 meters, 2.7 meters. Anything smaller than 2.7 is less than 90%, and whatever the conditions that need to kick in need to be invoked. Typically, this is a very crucial business decision between the client and the drilling service provider. So you as a geo make sure that whoever needs to make the decision, might not be you, might be somebody you report to, has enough detail to understand that this is backed by factual and accurate data management. Otherwise, it's going to be a dispute and it causes friction between you and your drilling friends. The second part of this is something called a solid core recovery. What that what refers to is basically what part of your drill recovery is solid. What that means is the diameter, the length of the pieces, which pieces of your core have a length bigger, and depending on, again, the commodity and the environment you're in and the guidance from rock engineers, they might give you a figure like to count a solid core, the length must be at least 1.5, 2 times, 2.5 times the diameter you are drilling. So if you're drilling NQ size, you're typically looking at pieces of core that are at least 10 centimeters or bigger. That forms part of your solid core measurement. And in this case, we are saying roughly 2 meters is solid core. Now, why that is important, it defines what now becomes what a rock engineer or a geotech engineer attaches to what is referred to as an RQD. And that stands for a rock quality designation. And where the RQD information becomes valuable is mitigation of slope failure or rock falls. If your RQD is extremely low, obviously what it means to a rock engineer or geotech engineer that you've got bigger chances of rock falls or slope failure in that particular horizon. And that's what they want to know well in advance, because you do not want to gather this information after you've started mining. You want to know it as you advance and have a view of what your RQD is. And obviously, as I mentioned already before, that what you want is ultimately to establish a couple of matrices which collectively can be called something like sample representativity index. What this means is basically how much geological confidence are you attaching per horizon that you are logging through. That sets up your resource model conversations. The poorer the recovery, the poorer you can, by implication, assume your interpretation of what and your descriptions of your logging is going to be. So you want to also share such information with your modeling team, if you're not doing the initial modeling, at least yourself. That brings us to a quick exercise that I would propose that you take. It takes about 5 minutes at most. And the exercise is on the slide. So the exercise is basically satisfy yourself that if you know the core barrel length, the quill rod, odd rods, and your rod string, and what your stick up is, you can estimate what the depth is. This ties you back to the principles we were talking about in the previous slide. Displayed here on the left is a form that we developed in one of my exploration campaigns to address these QAQC methods on the go. And you'd see there at the top, it wants to know what was the whole number, because everything you're going to log and describe is going to be attached to that, and we'll come back to this later. What drilling method were you using? Which drill rig of the many you might have? If you have one, then it's that one drill rig, but you want to know which drill rig did the exercise, on what date. In the drill method, is it a percussion or a diamond drill? Obviously, I said in this exercise, most of the discussion we're talking about is diamond, but most of this you can apply back into things like percussion with a bit of difficulty, but it is not impossible. And the date you are writing there is different from the dates down here. The dates down here is what I was referring to, which informs your chain of custody down here. The date started refers to when did you start drilling? Because the date you complete this form is not the same date most of the time as you start drilling. Most of the time it might be the date you completed the drilling, but please do not wait for 900 meters of core to be drilled before you do this exercise, because to your surprise, you will end up in a core yard with an extremely long drill core for you to log, and you are finding issues, and now the drill has moved kilometers. In fact, your drill campaign might even be done, and you're trying to solve a problem that you can no longer solve. and that's water down the drain in simple terms. So please, even if you do a multiple of these, the last one you do is at the end of the hole, which talks to your end of hole, and we'll get to that at the moment. Date delivered is, as I said, you might not be doing your detailed logging where you did your total core recovery. So it will be delivered to a central facility where you are going to do your core logging, maybe sample prep and the rest of sampling processes that you need to do to get assays done. So you want to know, when did it get there? Why do you want to know there? So that if it's a problem that has nothing to do with the driller, you want to trace when did it get there and how did it get there? And obviously the information I'm referring to that is for the exercise here on the right is information that goes in there. And the SHE and quality checks are the 10 that in the campaigns that I've been running, and I developed this with my team, were the 10 things that I always wanted to know. Whether I have any risks, risk both in the quality process of the drilling itself, but also safety, health, and environmental risks. Because as Colin said, and I'll reiterate, you might not carry a legal appointment in the South African context. I'd be interested to know if it's different in other jurisdictions, but you want to have the certainty that you do not have legal liability on your doorstep. Chain of custody, as I explained, you want to have instructed whoever is supervising the drilling with certainty that the downhole survey, this is the deflection survey I was talking about, is conducted, where your core shed is, and as a supervisor maybe, did they check the state of the core and counted the boxes as they arrived? Because you are drilling 900 meters, let's say, or 200 meters, it doesn't matter. We want to be sure that each and every borehole is numbered per core box correctly, and the core box intervals correctly, and you can account for each and every box as they arrive where your core shed or your logging facilities is. One thing I personally like, and I included this later, was comment on the state of the core number of boxes and whether you have any ore intersection. This is talking to your mineralization. And the answer you can give here at the very least is a yes or no. If you can estimate the thickness. If you cannot in the exact thickness, how many boxes? If you know that it's 2 boxes that have full mineralization and 1 core box is 9 meters, then you can say roughly 2 boxes, approximately 18 meters. Does not need to be accurate at this level. What this helps you do is have an ability to track which holes hit mineralizations, which do not. And if you have to answer somebody quickly, is your campaign advancing in a positive or negative direction for exploration purposes? You can have a rough figure that you are working with to say, I've already drilled 20 boreholes. Of the 20 boreholes, I've said yes 15 times, I've said no 5 times. So you are hitting 75% of the times you are hitting mineralization. And on average, between all the 20 boreholes, my mineralization is about a core box thick. That makes it maybe 9 meters off whatever you're targeting. In some commodities, that is decent. In other commodities, that is worrying. It will depend on the context within which you operate. But being able to give answers like that from almost at the back of your head enables whoever is managing your drill campaign at a strategic level to have confidence that you as the geo managing the campaign are on top of things, that things are under control, they don't need to panic. And if they panic, it's because they generated the concern themselves. It's not something you offered to them, particularly when you are dealing with a client and you are a third party. There's a driller, there's a client, and you are entrusted with the logging process. You want to be able to facilitate the conversation on behalf of your client. Is their investment on the drilling campaign yielding results they can back, or they need to pull the plug as early as possible? This helps you in decisions that follow your logging exercise. I'll take a pause here just to reflect on whether we have answers that are similar to this one or different answers. And please feel free to unmute yourself and comment if you have a different answer in particular. Generally, they say silence is golden. It is something I want to reflect on. Juan Lorenz made a comment here about QA and QC. Do you want to unmute and share your comment there?
Yeah, sure. I don't mind. I mean, it's more like I have these little nitpick bugbears like sulfur that I commented on earlier, but I think it's just important that we not necessarily make a distinction between QA and QC, but the way I see it, we need to have sort of documented procedures in place and how we're gonna handle the drilling, you know, to say this is like you're doing now. This is the plan of how things are gonna go. And then separate to that is the monitoring of whether or not those procedures are being followed properly. You know, I work in the resource estimation space, and too often we sort of just get data from a client and there's no documentation per se on how those data were collected, what the procedures were, the chain of custody, all of that. We just get a report that says, or sometimes not even a report, sometimes just a table of, oh, these are the QC results from the assay laboratory, you know, and then you dig through them and you go, but there's questions related to these. So I think it's just important to make sure that we don't always talk about QA and QC, but to maybe just make sure that we understand there's a bit of a difference between the two while they are interrelated.
Certainly, I think you're making a very good point there. How the monitoring is done is basically in this context then part of your drill management exercises, and not wait for the driller to call and say, I'm done with borehole number 12, I've drilled to 1,500 meters, come take your core. But as they progress and advance through that drilling, you are continuously monitoring and managing the campaign actively. And
Certainly.
what you look at into that is governed by procedures and protocols that ought to be in place. If they do not exist, aim to close and create those protocols, because that becomes what, as you say, your backfall to say, can I assure my client that what I've done is repeatable and reproducible? And that's
yeah, you know.
Yeah.
Exactly, because if we produce a mineral resource estimate, for example, you know, one can do that without having that documentation, but there'll be very strong wording to state that, and that severely impacts the quality of the estimate and the confidence in any estimates done from that. And estimates, you know, estimates can be an estimate of the volume if you're putting together a 3D solid. It could be estimates of grade or density or all sorts of things. It's not just gold. Anyway, thank you. I'm enjoying this.
Thanks for that comment, and I'm glad that you are making it from the resource space, because half the time field, let's call it exploration geos, forget that they might not be the ones looking at the data to try and tell a story.
Yeah, that, I mean, you'll see my answer to your first question is, what do you want from the drilling program? Is I want to make sure that I am assured that the data I'm collecting I can use later on. And for a few years, we gave a short course at the local universities here in Cape Town to the honor students on mineral resources, with the explicit aim of giving the guys who are literally going to be going into the field to collect these data an idea of what are these data going to be used for ultimately. Because if you know how they're going to be used or what they're going to be used for, you're in a much better place to be collecting and monitoring that data than if somebody just says, go log this hole, and you don't know how somebody needs to use that later on down the line.
Most certainly. And that's where this QEQC part, or the monitoring part, as you're referring to, becomes part of that assurance process. And it is one of those things that make or break an exercise of trying to do the estimation. So certainly, thank you. I see there's a question from Anza around what is the allowable minimum RQD percent. There isn't, if you think about it geologically in a broad spectrum of geology, an allowable minimum RQD, because rocks can be friable by design, and your drilling just exacerbates that. What you want to know is the RQD variation within the sequence of rocks you're dealing with. And why this is important, again, it goes back to, if it's going to be for a mining exercise, you want to know that when you're putting up shafts and developments and high walls, you are putting them with the correct geotechnical and rock engineering inputs as best as possible, because the last thing you want is to build a final wall bit boundary on a rock that has a low RQD and it keeps failing, because that is going to put your mine and ultimately the people who operate in it at risk. So I'd say if you are aiming to have a competent high wall, anything less than 75% is a risk in your RQD, because it means there is greater than 25% chance that you are dealing with a not so competent rock. But we can get into much more geotechnical and rock engineering details around that conversation. So I think, Anza, the answer to your question is that in terms of RQD itself, you want to know what it is. That is the answer you're after. Whether that's acceptable or not, that's the conversation that follows, depending on what you want to achieve. If I try and explain this way as well, is in a different setting, if your ore horizon itself has a poor RQD, that means in your mining process, you do not need to spend as much energy as if it had a high RQD to fragment a rock during your drill and blast exercise. Case in point, as I said, I work for Anglo American. I'm particularly in Sishen mine. It's one of the hardest iron ore mines in terms of competence now. Significantly hard iron ore to drill and blast, load and haul. It's very hard and abrasive. Comparatively speaking, Anglo iron ore mine in Brazil does not drill and blast on a routine like Sishen. Why? Because a significant portion of the ore body in Brazil, you can mine without drilling and blasting. Why? There's many reasons, but the RQD is certainly high in Sishen and extremely poor in Brazil. That allows them to mine their ore horizon without as much investment in the drill and blast space. So again, it depends what you're after. If you are a geotech or a rock engineer and you are trying to mitigate rockfall and slope failure risks, you want to know which rocks will hold your pit standing. If you want to be in the control space and have your mining processes efficient, you want to know, is there an opportunity of being smart about your drill and blast to fragment the rock with good enough energy, but save on the costs. And RQD is one of those things that can be a telltale sign in those exercises. Abdullah asks, what is stick up and what is odd rod? Abdullah, in the example we're looking at, the rod string, if I can start the example there, you are dealing with 77 rods making up the rod string, and each length is 3 meters. So that would be your standard length for your drill campaign. However, it might happen that you are drilling in a very remote area and your rods are coming via a ship from a different continent. Let's say you're drilling somewhere in West Africa and your rods are coming maybe from South Africa or Europe, or even North America. So they need to be delivered at a port and then trucked to you wherever you're drilling. So depending on your supply chain efficiencies, your rods might not get to you. So as rods wear and become old, the end joints become weak. One way to sustain your drilling while you're waiting for new rod supply, depending on the supply chain routines, as I said, you might send it to a local guy who's good ironsmith or good with machining, where they would cut off the worn parts of the rod and refashion the coupling points, the box and the joint, to basically make them fit with the other rods. But now your length is no longer 3 meters. It's an odd length. You don't know exactly what that length is, but these are the rods you want to measure individually and know that that particular odd rod is 2.5 meters, the other one is 2.7. Ideally, if you aim for the same length with your local help, it makes your job easy. In some other instances, the length can vary. So that's what an odd rod is those rods that are not standard length. There are some arbitrary lengths different from the standard length. Stick up is the portion of your drilling as you drill. Let's see if I can now draw on the screen. But as you drill, you'd have your drill string with your pulley at the top and your box or your chuck, as you call it, and you'd have a drill string going down at depth. And that's your rig and the surface it's standing on. And as you advance drilling down, you're going to move your chuck bottom part, where basically you are holding the rock with your rotation head, to somewhere at that level. So you're going to advance that thing, and maybe that's your 3 meters. That allows you to advance. Now, when your drill head is sitting there, the portion of the drill string from there to where the surface of the ground actually starts, where you're breaking flush, that distance is the portion of your drill, your drill string, not rod string, drill string. The portion of the drill string that is above ground or sticks above the ground, that is your stick up. So it says if you have a drill string of so many meters, the 1.89 meters of that drill string is above your ground. By implication, is not part of your drill hole, should not be part of your drill core in your estimation. So what is a drill string? Your drill string is your core barrel, your quill rod, your odd rod if you have, and your rod string, inclusive of the stick up. To get to the depth, you need to account for the stick up. Hope that clarifies what is a stick up. Dimakatso got the answer, and I assume you mean it's this one, Dimakatso. Sarah, hi. Would you want to maybe unmute and let's unpack your comment?
Hi, Matsi. Yeah, so I come from the exploration phase, and so I'm assuming, you know, with being on the major, you guys understand your ore body and you've defined an ore body. Whereas, you know, I'm generally greenfields going in there before we know much about anything, and we've depending on the mapping now looking at seeing what's in the ground and seeing how we can advance it. So I really like this, and I think it's a great piece to add to your work, and you know, especially depending on the drillers that you have, you do want to understand, or you do want to validate what your depth calculation is, and do a depth check. I just at the bottom there on the left hand side, we discussed, or you mentioned about the ore intersection, and personally, if it was me running the project, and not necessarily on this one but on mine, I think I would change it more to mineralization intersection, which is also a term used, just to be, you know, really nitpicking here, but it does have quite a big yeah, thanks where your mouse is. It does have quite a big influence on the project, and you know, getting terminology is quite important, or getting it right is important in the project.
Certainly, thanks, Sarah, for that comment. And I think you heard in the beginning, as you point out, I was jumping between mineralization and ore, because it would, as you say, depend on what you're dealing with. In this sense, yes, you're quite spot on. The mineralization is more inclusive, if you want to put it that way, of setting project phase and what your target mineralization is. So it is, you can change that. But if you already know what you're after, and you are advanced in your project, and you already at least have exploration results that back up your further phases, you might also be at a stage where you know whether saying or not is kosher, depending on the project's funding model. So it's a point well made. Thank you for raising that. I see Magabia, welcome, and you're saying you are lost in the calculation. So I think when I was saying do the calculation, I just wanted to see how many of us get it and how many of us are lost. I'll come back to now. Abdullah, if I understand your question, considered ground level. So the depth of the core and the hole is always referenced to the zero being at the collar. And obviously, when you're done with your drilling campaign, you will do the deflection survey that I was talking about. You would typically have that confirming how your depth propagates. This depth check exercises helps you have a feel of what your deflection survey must sort of tell you. And when you go into the modeling space, and Juan can help you unpack this one in this discussion, is that you match then that collar position, and we'll come back to this, with additional surveying methods, if you want, of where is it on the surface of the earth. Then depending on your modeling approach, you would use then what is applicable to your elevation model philosophy, depending on your setting and your considerations. If the surface is not flat, that's where the survey, and I think we'll come to that part. Can I maybe then consider that we can maybe go through this exercise just to give comfort to those that haven't, how we get to the 236.13. So as I said, to those that are lost a bit, you first consider what is your drill string, which is basically that part. Say, what is 77 multiplied by 3? What is your barrel length? And what is your cool rod? So that would be, if I redraw this thing, is the portion of your drill string from where your water or fluid intake is through the chuck into the ground where your end of hole is, right? That length from your cool rod to the bottom of the pit, that's your drill string. That gives you a total, That gives you a total length. That is a total length. That is not the depth of your core. And where the stick up comes in is the portion of your drill rod that is not part of your hole. By implication, you should not have core because it's a void above the ground. In is the stick up portion. So you need to know what is the portion of your drill string sitting above the ground so you can remove or subtract that. So in this particular exercise, what you are then dealing with is your total length in this should be something like 238.02. Tell me that you got here if you've gone that far. And when you now take that 238 and you subtract your stick up, that is not part of your drill core and your hole, then you get the depth estimate. Remember, this depth estimate is a working figure. It is not the final figure. What you're going to use here comes from your deflection survey later on in your database management. And we'll come into that in a second. Any other questions? I am not seeing any. One has yes, as you call itself, you are interested in the depth below surface of the rock intersection. Yes, that's essentially what I was explaining there. Thanks, Juan, for adding that. So now you came here for logging. Now we're talking logging a couple of hours later. So logging, I used very carefully earlier on is if you do not take certain considerations, this can quickly turn to a tick box exercise. So please bear in mind from here on, it's one of those things that we were avoiding tick box exercise logs. So what are you aiming for? You are aiming to delineate an ore body or mineralization, as Sarah was pointing out, depending on your setting. And when you begin this, always have an end in mind. And the end in mind is not even a resource model or an R&R statement. That is part of the journey. If you're going all the way for mining, the end in mind is reasonable prospects of eventual economic extraction. And you want to remove the term prospect in that configuration. You want to realize economic extraction. So the end in mind is you want to set up the subsequent activities to deliver the most cost-effective extraction method. Because obviously the more economic it is, the more you can get out of the ground. You crank up the cost, your grade and tons take a knock. And your targets, as you know more, you do better. So you keep a working model and you iteratively refine what you know. And it goes back to the discussion around what is your field setting versus what your boreholes are saying. And the working mineralization estimates is exactly the conversation Sarah and I were having now about mineralization versus ore in your chain of custody. You want, as you confirm through your logging, that yes, I have intersected mineralization and my rough estimate is this volume, tons or whatever your client is interested in. And bear in mind the reporting guidelines you're gonna have to work with depending on the stage of the project you are in. Do not overcommit yourself in what you are finding. But if you are on a tight budget project, you certainly want to keep your investor or your client, depending on the situation, abreast. And what I'm showing down here at the right is, in this case, intersections of mineralization in plain view with on a project that was being taken through a feasibility study. and already there was a primary pit that was initially set up from the earliest resource models that were generated. And the point I think here with iteration I want to make is you would see there's a significant amount of mineralization that sits outside the initial pits. And being able to do this iterative reflection on your work and your model assumptions enables you to test whether you are delineating your mineralization in our body with the end in mind. The reason this was the setup in this particular case is what lies in this whitish color. I hope we are all able to see the same color. The whitish color there is an environmentally sensitive portion of the area. And by implication, there were restrictions imposed by the regulator about when and how to drill in those areas. It cannot be that you forget your environmental, social governance dependencies of your project, as I mentioned earlier. So at the earliest stages of this area, all that could have been drilled is basically the majority of what falls within the boundaries. When the environmental compliances and environmental management plans and guarantees were given to the regulators as part of the mining works and the exploration works program, things were changing over time. So the duty of us that know the start of the project and that have been part of it, and those that came later, was to always make themselves familiar of what conditions can I not do certain things and what conditions should they changes my approach to the drilling exercise. And being able to always go back to your core and what you are looking at as an iterative process keeps you right on the money. And the communication by the end of this feasibility study was there is an opportunity of expanding the pits and potentially drilling further between them, considering environmental considerations and limitations, potentially see if there's an opportunity to connect the two areas that were initially thought of as isolated. In terms of whether this is a reasonably prospective eventual economic extraction, the initial assessment was yes, but further work needs to be done. In terms of now what you consider in your capturing exercise is a good old statement for industrial engineers. They like the statement for different reasons, but a Peter Drucker quote that has been reinterpreted to mean that if you are not measuring it, you are not managing it. But one of those versions is if you can't measure it, you cannot prove it. And the point here is back to what I was saying is aim for good accuracy and good precision as an intended outcome. What you can accept with caution is around what precision is, even though your accuracy might be questionable. However, some, and I dare say most logs, when you are in a tick box exercise space, end up being in the space where there's a long sheet that tells a resource modeler or even a mining engineer what you said you saw in the ground. But if they look a hole or an area 10 meters away from your log, chalk and cheese. What you want to avoid is exactly that. And obviously, when you are logging, you bear in mind you're going to capture the information in a database. This is a database we use. Those that are familiar with the looks of it might tell what it is. But for the purposes of this discussion, I've covered the name. But the point is here, you are going to use a relational database to store what your observations are based on the unique hole ID. And everything, basically, what you log into is going to be your borehole name. What hole are you logging? And please bear in mind, you mislead the database, it's going to mislead you, straightforward. There is no two ways about it. And that's why even the QA/QC and the protocols and monitoring throughout your entire drilling, logging exercise are absolutely critical. And as you can see, in the various workspaces, you can set up validation processes. Please do not see this as unnecessary workload. It is absolutely critical. And Juan will even tell you as he was articulating the resource modeling space, this information makes or breaks a model. Not have access to a database, whether it's because of where you are on the surface of the earth, that database wants you to be connected to the internet and your network doesn't support that, does not mean you can't do this. This is a sheet, again, we made on Excel and printed it out in a piece of paper, but all the things that are highlighted in red are things that when you go back to the database a week, a month, 2 years later, please don't make it that long, but just making a point, is going to be the things that the database are going to ask you, but where's this information? Because somewhere in the database you've built in your protocols and your monitoring mechanisms, in a QA/QC mechanism, that it is a mandatory field. That borehole must have a from to, a name that is primary. If you want, you can put a secondary one. Color, we'll come back to color. For me personally is one of those. And then you go into, if it's a sedimentary setting like this one we were in, you want to describe the class if you're encountering any class, any structures, mineralization. And this is where, again, Sarah's point comes back, is if you do not know and you do not want to commit, do not call things you do not know as ore, rather call them as mineralization. And in here, you do not, if you are in an iron ore business, you do not capture what is iron ore and forget what is not iron ore. You might intersect something else that in somebody else's life is mineralization. You want to certainly make somebody know that, hey, hang on, you sent me here to come find a diamond, but I'm finding other things that we should maybe have an answer to. And obviously where fluids and metamorphism and hydrothermal alteration might be real, depending on your geological setting, there will be alteration by implication. So you can have a relational database that is cost effective, but the point is your data management needs a well-governed structure. That brings us to now what we were talking about in terms of what are parametric considerations. So parametric considerations basically is back to the point I made in the previous slide that says it's basically talking to quality-based logging, and you are talking about quantifiable or measurable properties. Now, some geos will argue with me that you cannot measure everything. I dare say, perhaps, let's have the discussion. And the point I want to make here is logging is a science. It is not subjective. What is subjective is the interpretation. Your job in logging is not to interpret, is to describe accurately. So if you are not measuring it, you cannot prove it. So where do we start? Normally we start with collar information in general. So what are we looking at is the borehole and project data. What is the whole name? Which project is it on? Is Masi the geo or somebody else the geo? Maybe it's Sarah's drill campaign. Who is the driller if that is relevant? When did you start and end the drilling? From what depth to what depth? This part might seem trivial. It often happens where you start drilling. For a number of reasons, you stop and you do not finish at the desired depth, and you case the borehole and you plug the collar to come back years later, or maybe weeks later even. And then time flies by and you wake up, it's 10 years down the line, and that information now becomes necessary to get. Instead of going back and sticking another borehole next to that one, the simpler exercise is to cut off that part, open the hole and stick a drill rig in there, lower a drill string back to bottom if you can get there, and start drilling and advancing further. So this information of from to is absolutely critical to say this particular hole, my mineralization ends approximately 500 meters. For odd reasons, I did not get to 500 meters. So instead of telling the modeling guys in resource geology that they can terminate your mineralization at 500 meters, you want to give them a heads up to say, I did not finish my mineralization for reasons that are important for the execution of the exploration phase. I need to go back, so that when they treat that information, they do not terminate at 500 meters. They give you the leeway to say, please go back and finish that area so that you can advance past the mineralization, and they can plug in that information at the next model update, whatever your routine is. Survey data talks about essentially where on the surface of the earth is that borehole. Now I know, yes, it's whole ID. It's on Charlie Hector project, but you might also have a project in Cleffam Farm. Now, when you do your borehole ID, you have CH1, 2, 3, 4, 5 to wherever you've gone, and maybe another alphabet at the end. And your project is CH in abbreviation, but comes Masi on a different project, same company, has another CH, totally unrelated, maybe on the other side of the country. It's also a CH. How do you distinguish? This is where this comes in. Say what spheroid we're using, and more importantly, the coordinate system that tells you XYZ. There was a question around what if your surface is not flat? That Z there is where you put your zero. So on top of this hill, you are 40 meters above elevation than you were up there. So that will have a Z based on your GPS as you were staking the borehole initial position. So that becomes your Z entry there. And as you log there, where the borehole becomes flush is your 0 point. But everything that you log will always attach to the whole ID is 40 meters above at CH1 versus CH6 as an example. And the survey devices, your GPS, how accurate is it? Depending where you are, you might use your cell phone. That gives you at best 3 meters these days, or an old GPS that cannot do anything better than 6 meters. But later on, when you do your final collar surveys, you come with a robust high-tech GPS that gives you a meter or less in terms of your accuracy. So that information might again seem trivial, but 4 meters out or 10 meters out might be very important for an application. So you want to give an inclination to somebody who's looking at this data is, when I was surveying this position, this is how far out I was. And obviously we've touched on the drilling data already. What is the core size you're drilling? Is it NQ, BQ? And of the NQ, BQ, which one? NQ2, NQ3, NQ1, PQ, T2101, that's what it's referring to. Did you case the borehole? To what depth? Somebody unmute, question? Happy to take comments and questions at this stage. I see somebody is unmuted. Okay, we shall continue. So casing is how much casing sits in that borehole. As you heard in the previous talk, when they were talking about drilling fluids, depending on how you are managing your drilling rate and your fluid rates and your composition, you might have to be drilling through friable material, and you might wash that material away. And that might pose a risk to your ability to advance further in that borehole. To mitigate against that, one of the ways is case the borehole past the problematic areas to keep the hole open so you can advance in and out. And the casing depths are important for that conversation. And if you are doing deflections and wedges on purpose, you want to capture information in terms of where and how many wedges are they sitting and in what direction, and any other information you might deem relevant. So again, all of these things can be quantified, can be measured. where necessary. The next and the biggest one is the geology itself. What is the rock? The rock is made up of minerals that makes a name for you. So give it a name. And please be as accurate as you can on what the name of the rock is. The contact, you'd see a lot of logs that says it's gradational. Ask yourself a couple of times, especially if you are the one logging or reviewing that log, to say, is it really a gradational contact? It can be gradational, and that might mean something. It can that you're saying it's gradational because maybe it's a bit difficult to place what type of contact you're dealing with. But please be accurate and considerable effort put in describing and taking guidance on what type of context you're dealing with, depending on the geology. Weathering, some low, high, medium. What is low, high, medium? Be bold, put a number. If you're wrong, but at least the number also gives the person looking at it in that it is relatively fresh. I need to consider that there is some weathering and maybe it's close to surface, so it'd be highly weathered, or it's a depth far from any weathering. This is important because you can distinguish from alteration. Alteration high, again, you'll see a lot of logs say it's highly altered. Yeah, it is highly altered. I agree with you. What type of alteration? Again, parametric. When you say it's retardation, you are specific about what type of alteration minerals you are seeing, if you are able to observe them, or textures that are going with a specific type of alteration, so that the person looking at that can tell, okay, if I'm seeing this type of alteration, that means I'm dealing perhaps in this zone with this type of setting, maybe fluid movement if it is. Brownish, grayish, talking about color. Again, some logs, and quite a lot, I've seen even myself logged in such where I, at some stage, put color as grayish, brownish, reddish brown. One of the codes that I personally like when I log is what is the Mansell code. It is very difficult if you are working in a multinational organization where there isn't a color management approach and measuring scale, but please consider at the very least to get there if you do not have at the moment. It's not the end of the world, but it's quite important, because consider that you're going to be mining in an environment like iron ore, where you're going to tell an operator sitting 10 meters away from the material they are supposed to load for you in your ore control environment, and at night looking for ore that is red when everything around them is red. So you want to be able to help them distinguish, and any other tracking systems. And of course, again, this is going for perfection, but there are means of measuring color. In the Mansell system, what you're basically looking at in terms of quantifying the color, you are looking at three components. You are looking at the color itself, what distinguishes from this color from that color, which is the hue. And then you're looking at the value, which basically indicates how dark or light is the red you are dealing with in that scale. And as you can see where they sit in that queue. And then the chroma, which indicates how rich or strong or weak the color is. So if it's a deep red type color, you can give it a number there that talks to a red, and you're putting it at a 5/14 thing. And that red might then mean something for your grade qualities and any other descriptions you might want at a later stage. But it's absolutely fundamental that if you can measure it and your system allows you to migrate from grayish to that space, please do it. And for historic stuff, if you know that quartzite is always yellowish to white in your area, ask whoever helps you set up that database to say, instead of me going through 9,000 logs from 1900, changing all the logs manually, quartzite, yellowish white, or a color that sits there in the Mansell code. Write a script to say, go look for quartzite in the length column and look for color entry. If it's this color, leave it. If it's not, change it. And you can even be fancy, put additional conditions into that. But before you log and accept that change, you need to validate it. Do not just change things for the sake of changing, and their database management system trusts you to make those changes. Texture, again, massive. You need to be really sure when you describe certain things. As an example, in this picture, you'd say, it looks all gray, it looks all uniform. Really? Are you sure? Is there any structural geology, fracture pattern and frequency, and any fill material you want to take note of? Kumba stopped mining Tabazimbi pit because of structural geology. Long story short, unexpected amount of rain percolating through a structure that over the years daylighted into the pit. The geotech engineer picked this up as the mining was advancing and did say, at a given stage, that structure and that amount of water is going to be absolutely problematic. So a decision will have to be made. When that decision came, the information was available. Everybody was removed from the pit because the pit collapse was imminent. And at that stage, the call was made to pull back, and the slope gave under its own weight. Long story short, the amount of rock that came down meant that it is no longer economic to advance mining in the Satan mine I'm referring to. And at this stage, it was also quite an old operation. So we're really pushing the limits in that discussion. In terms of orientation, this one talks to, is your drill direction or drill setup vertical or at a particular angle, and any contacts and angles you measure, are they relative to the axis or are they relative to vertical, whatever you do there? And if you are having an angle, if you can orientate the core, even the better. Stratigraphy, obviously, this is tying back to where are you placing yourself in the core relative to your field settings. Remember, I made a comment that if you can pick up the core and you place it in the field setting, does it match the environment where you say you drilled it? If your mapping exercise and your field setting understanding is not that good, you will almost accept any drill log. But if it is good and you are supported by a good model and a good log, those things must talk to each other. If they don't talk to each other, either the log needs to be reviewed or your field setting and assumptions are problematic. One of the two. Having said all of this, that brings us here. And here I can illustrate the things I was talking about. There above, you have something that could be easily described as reddish, but you wouldn't necessarily tell what the difference to some of the things that are red in there. And this looks only whitish because of the effects of the drilling itself. In actual color, it's between red and purple, if you think about the hue. So again, on color alone, this forces you to be absolutely pedantic. Texturally, you can see bedding is very difficult to see, but you can see some foliation perhaps in there. There's some joints coming through at almost set directions through the core. And some portions of it are broken, others look quite friable. Others you might get competence and perhaps good RQD. And as you advance, you need to be able to pick out this. There are two logs on similar areas in similar core where one of the geos said it's a sharp contact, the other said it's a shear contact, and another one said SHR, which is short for sheared, and put an angle to it. If you ask a resource geologist, which one of the three would they work with? Because this means sheared. This one just went an extra step in most databases and said it's the angle I can measure there is 15 degrees from horizontal. So if you imagine the structure, they're estimating it's about a shallow structure. The bottom one, again, sharp sheared, same geo here. Again, when it said sheared, 45 degrees. So question becomes, are you dealing with the same type of a shear or different structural geology interpretations? There might be a number of interpretations a modeling person attaches to this information, but in the absence of this data, you can ask a resource geologist which one they prefer, assuming this is not available. And then obviously, as you place this thing to a stratigraphy, you are saying, I'm dealing with clastic and chemical sediments. And because I've said where I am in the stratigraphy, you can estimate the ages. And now the question that follows is this question that I asked earlier, reviewing what we just looked at here in the order of oldest to youngest. What is the correct sequence? And again, the same link applies, or if you've closed it, you can scan again and complete if you haven't completed. At this stage, we'll do this and bring back our responses. I see we have about 35 responses of the 100+ that are online. So if you were waiting for the stage to complete, or 56 responses now, great. So those that have responded, I think good to see the various expectations coming through. As I said, this is a very interesting outcome. I'll have a chat with Tanya on this and see what opportunities and considerations are we setting up for in this. Risks, certainly. Overwhelming majority says all of these we are ticking through as we are addressing this. Now, the question that now we are dealing with in the previous image says the majority. I'll take this with a pinch of salt because some of you answered this question without seeing the image. The correct order is CBA. A significant portion is saying ABC. It'd be interesting, I think, for me, Tanya, to say, considering question 2, how does that affect this response in question 4? It will be a very interesting exercise that I'll do post this event and share that with you. If you remind me, there's about an equal split between ABC and ACB. Again, if I read this with question 2, it will be quite interesting to see what the makeup there is. CBA as the oldest to youngest. So coming back to where we are, can we take a 5-minute break at this stage and we'll wrap up to the end from here on. Then I'll come back and I'll explain the relationship of this picture to this picture, which then we can get to the answer that I think we can finally agree which one is the correct order of these things. Yeah. Hello? Can you hear me?
Hi, I see we can hear you. I assume Tanya's just stepped away or she's struggling with power. Oh, I see she's just come online or she's just unmuted.
I was knocked out. I've just come back inside.
Okay,
Um,
I was just checking in that we basically take a we take a short break here.
Mussy, you've only got 10 minutes left.
Have I?
Yes.
Sorry, I've lost completely track of time. Let me then do this push for the end, Tanya. Apologies, everyone. So if we look at this exercise, I've been very economic previously. If we look at this exercise and what I've already.
Mussy, you need to swap presenter view.
We are basically looking at this image, which is a section through that stratigraphy. This is the correct stratigraphy of events, and I displayed this picture earlier on. What I did indicate earlier on is we'll come back to this picture as the correct version of what's actually happening. As you can see there, the bottom part where the ion formation sits is the chemical sediments at the base. The subsequent volcaniclastic sequence is that portion of the drill core, and sandwiched between the two is the younger clastic sediments of the case supergroup that is sandwiched between the two. And if you come back to this image, that's that portion there between the two rocks. And the important thing is, as a geo, you have to form the rock before you can share it. So if the geo in the field tells you it's shared, then that is valuable information in the interpretation. And again, as we come back, massive is boring. As you saw the picture, if you look at this at the field setting, there is layering. This is now an igneous setting, and you can see there's a preference in the orientation on the minerals that form the rock. You don't see that well in the core, especially if it's dry, but if you make it a little bit wet, that comes through. Yes. Okay. Please mute yourself. Obviously, there's mineralogy in that I just touched on now. And obviously, what are your all-forming minerals and what are the host minerals? Other people would refer to this as gang. Gang minerals are quite important. And if you do not have the answer, that's quite all right. And you cannot get it in a hand lens, but trigger somebody to do detailed mineralogy post the exercise. And if you already set up in your database to capture the information, all the more better. Because then you can get either things of this nature where you're just looking at a simple microscope to describe the rocks and the textures that you're dealing with in the host rocks and your mineralization, or you get something that is to the nature of describing what is your ore mineral makeup and what gang mineral for liberation purposes sits in there. The rest of these are analytical considerations which we have discussed already, in the sense of what are your sample IDs and what you send to the lab, what are the assays and related QA/QC processes and monitoring and the validations, and setting up what your expectations in your geostats to have this. And obviously this is just a view of a reference material. Before you can accept lab results, you need to have gone through these checks. Do not assume labs are always correct, please don't. Ultimately, what you want to be able to do is look at your drill core with your estimated model abundances, especially if they are validated by detailed mineralogy, and to what your analysis or your analytes are doing. Because in things like this, you get to pick out things like this. If you look at the Mg number in this case and the aluminum, they are both controlled by different coexisting minerals, but they are telling you different geological processes. One is telling you getting evolved, the other one tells you getting primitive. That can't happen at the same time. So there must be another process at play. If I consider the geophysics aspects, if you have the ability to run geophysics, you can again run geophysics in coal. They do this as part of the logging exercise. And all these geophysical methods give you additional information. Key for me here is what you get out of the iron ore grade in this case, and your conductivity and your density are quite interesting matrices to look at. And this helps you validate your logging. Because ultimately what you want to come to is connecting the dots, the end in mind. And what you want to end up with, at least for yourself in the bush while you drill, is a section or an iterative view of what you're dealing with, where your mineralization or your ore body sits, and any other material that sits. Obviously, this is ultimately what your borehole will look like. And please do note that between a section line and how the modeling guys can do, the section might look completely different, because the end in mind and connecting the dots is being able to say, what are you dealing with? And the issues that we're talking about here is things like simple logs are not very useful because it doesn't tell you much in that portion of the intersection versus that part. That part there is much more detailed and can help you sort of see where lenses of certain rocks are and things that were negated. Yes, the color is different here, but it's still part of the same sequence, but there's these lenses that you cannot interpret in that portion, and simplified logs are not very helpful there. Consistency in your logging, this is the precision I was referring to, that one person logs one thing, the other logs another, and mixing and matching is a problem. And then stopping boreholes short. At a time, it might be important, but if you don't tell anybody, that's what modeling people will do. They will terminate everything there, and by implication, your basement, it gets pushed up when it might not even be the case, because if you look there, there's actually a possibility of connecting certain things through where the model says there's basement rock. Because what you want is a model that will work, and reasonable prospects of eventual economic extraction are the focus area, because where your resource development plan takes you is a life of asset plan and where value sits. And things like this, where you see you are terminating your pit with mineralization shown at deeper levels, needs to be the question you ask yourself as a geo. Did I do my absolute best in informing the mine planning and actual execution? And where you have detrimental factors like dikes running through your ore body, you want to know where they're sitting, and any cross-cutting structures that might influence your mining engineering conversations, you want to depict them and perhaps give them names in the process. Tanya, thanks for flagging me, and apologies for taking it quite to the end, but thank you very much. I have.
Thank you, Marcy. I'm sure everybody could quite happily have continued on to listen to you. If you can send me a PDF of your slide deck, please, I would be grateful so that we can send it out to everyone.
Certainly will do almost immediately, Tanya. Thank you very much, and I'll send you the results of the surveys I put in between.
Thank you. Okay, we're going to have a break now and come back at 1:15. So you get 15 minutes to go and have a break. And in the meantime, I just want to share this. Okay, this is your assignment, the information there. Everybody who was originally registered for the course, you will receive a link to the recording and the PDFs. The recording will also be on YouTube, so you can catch it there. And then you send your summary to me at this address. Does anybody have any questions? Okay, this will be up here during the break. So if you have anything that you want to think of, you can ask before we go on to the next presentation. Mercy, are you going to stay on the call for the rest of the afternoon?
Tanya, I'll stay around till 2 o'clock. But I need to jump off at just before 2 o'clock. So
Okay.
it might be close, but I'll jump off before you.
Okay, Sarah, that is Sarah Turnbull. Are you're going to be staying on longer, eh? Okay, Sarah's gone off to get some coffee, obviously. So Mercy, before you go, if you can make Sarah the host when you leave.
I see Sarah is co-host as well.
Yeah, she's co-host now. And then when you leave, just make her the host.
Let me do it now, Tanya.
Okay.
Yep. Yes.
Super, thanks. Then at least somebody is still online. Thanks. Sarah Solway, would you like to start sharing your screen, please?
Yeah, sure, I can do that.
We got two Sarahs. This can only lead to confusion. Okay, that's perfect.
You can see it. Oh, great. I'm not overly familiar with Zoom, so
no, we can
seem to have got it first
we
go,
can
though.
hear you. It's perfect.
Fantastic.
Okay, so next up is looking at structural logging. We've done a lot about lithological logging, and the next stage is structural logging. And our presenter today is Sarah Solway. She's got 30 years of experience as a geologist and is currently product manager structural solutions at MDEX. She has a deep passion for technology and enjoys collaborating with multidisciplinary teams. Her background includes greenfields exploration, resource estimation, workshop facilitation, training, and product management. So Sarah, we look forward to hearing from you about structural logging. Off you go.
Lovely. Thanks for the introduction and also for the opportunity to present today. I'm going to be talking about structural logging, as Tanya's just said. In the field of geology, understanding the structural characteristics of rock formations is vital for interpreting geological processes, resource exploration, and hazard assessment. Structural logging is the systematic recording of geological structures within diamond core. And throughout this session, we'll delve into the significance of structural logging, look at the process of core orientation and preparing the core for logging. We'll look at the essential tools used for measuring structures in diamond core, the application of stereo nets for data visualization, and also the crucial aspect of quality assurance and quality control in structural logging. So as geologists, our job is to study the physical properties of the Earth. We need to understand the forces that have occurred over time to shape the rock and resulted in some of the fantastic structures and outcrops that we see today. But why is this knowledge essential? Well, understanding geological structures is crucial for multiple reasons. Firstly, it helps us identify and manage natural resources, minerals and fuels, which are vital for sustaining a modern society. It also allows us to assess and mitigate geological hazards, such as earthquakes, volcanic eruptions, landslides, safeguarding human lives and also infrastructure. And lastly, comprehending geological structures aids in predicting the impacts of climate change, enabling to make informed decisions to protect our environment. In essence, geologists play a pivotal role in unraveling the Earth's mysteries and ensuring a sustainable and safer future. So if we think about the primary objective of exploration activities, especially in the context of geology and natural resources, the purpose is to gather data and information about the Earth's subsurface to identify and assess the presence of valuable minerals. Exploration it's the initial phase of the resource extraction process. It aims to discover new deposits or locate additional resources in known areas. Basically, it's all about the rock. Rocks contain a wealth of information that provide valuable insights into the Earth's history, processes, and resources. Through the use of advanced technology, we can extract information about the rock's composition, its mineralogy, the grade of any economic minerals, as well as the structure and texture. Of course, that information is completely and utterly useless if you don't know where it came from. You don't know its in situ location and orientation. So all this data is collected and integrated with existing information and used to reconstruct the sequence of events that have occurred over millions of years and to develop and refine geological interpretations. The confidence we assign to those interpretations and subsequent resource estimations rely heavily on the quality of the underlying data. This confidence is or becomes the foundation upon which exploration and mining companies decide which projects to pursue and which to put on hold. Similarly, investors base their decisions on which companies to invest in on this sort of level of confidence. Consequently, the value of the data collected and how it's interpreted directly impacts on the cost of these critical decisions. It's not only about costs and finance. Understanding the rock's structural complexities plays a significant role in rock mechanics by helping us to identify weaknesses that could impact the stability of mine designs. Failure to grasp these structural complexities can lead to substantial negative impacts, both from financial and safety perspectives. The orientation of discontinuities plays a critical role in evaluating rock strength and assessing potential for surface failures. And as we delve deeper into understanding of rock structures, we enhance our ability to make informed decisions, mitigate risks, and ensure the success and safety of mining operations. So drilling is a major source of the rocks from which information is extracted and used to inform geological models. But it's an expensive and time-consuming process. If it's carried out without accurate geological information and planning, it can lead to a great deal of waste of valuable resources and misinterpretation of geological structures. The determination of structural data from drilling can be done either using borehole imaging techniques such as optical or acoustic televiewers. These methods involve lowering sensors downhole after drilling is complete, capturing high resolution images of the internal drill hole walls from which interpretations and measurements can be taken. The second method involves determining the orientation of the core before it was extracted from the ground and using that information to measure the orientation of structures within the diamond core during the logging process. And this is the method that I'm going to focus on during today's presentation. So in order to accurately measure structures in the drill core, you need to know where the hole has been drilled in 3D space and the orientation of that core as it sat in the hole. This is done by marking the core face to reference either the gravimetric bottom or the top of core in inclined holes. Errors in the hole location and the core orientation will significantly impact the accuracy of your structural measurements. A little bit of an example. Let's consider this beautiful bit of core, and we have a fracture sort of running through it. We know that the hole was dipping at -65 degrees, for example, with a dip direction of 90 degrees. And we know that its depth ranged between 135 meters to 150 meters. We know this from the planned orientation of the drill hole and from the information that we get from the drillers. So that's where we think the core is sitting, and there's the orientation of that fracture. If, however, the orientation was unreliable for some reason, and that core may be still in the correct spot depth-wise, but was orientated just 15 degrees differently, then that does affect the orientation of that particular structure and has implications on where you're going to drill your future drill holes. If you add into the mix the drill hole trace and the trajectory of that drill hole, this is a planned trace. Of course, we all know that holes do not necessarily get drilled in a straight line. They wander around a little bit, and we take into account the actual hole trace. we can get a completely different view of the data. So it's really important to understand where and how the orientation process takes place. You'll hear more about the downhole surveying and trajectory of drill holes and measuring drill hole traces in the next presentation. So I'm not going to talk about that too much now. It's just really to, I guess, emphasize the importance of getting it right. So the first core orientation system was developed 169 years ago in 1854 by a French engineer, approximately 10 years after he developed the first core drill, which was a free-fall percussion type tool. It produced quite short lengths of core, about 30 centimeters, and a core breaker and lifter mechanism grabbed the core, preventing it from rotating as it was extracted from the hole. Over the next 30 years or so, rotary core drills were developed, and a system that marked the core before it was extracted from the ground also developed. The first half of the 20th century, compasses and cameras were incorporated into the process, and by 1950s and 60s, the core orientation was pretty much a standard practice in many drilling operations. First digital solution was released to the market in 2004. This method orientates the core tube and allows the core face to be marked by the driller at the bottom of each of the drill run rather than the top. This is the method that is by far the most commonly used today, and it's the one that I'm going to sort of take you through and explain. So digital core orientation solutions, no matter which vendor you use, they all comprise a downhole unit. Let's get my laser pointer here. So a downhole unit, which is incorporated into the drill string and goes down the hole during drilling. It's represented here by this silver part of the drill string. And in here, this particular tool sits between the grease cap and the inner tube. Other downhole units from vendors are incorporated up into the back end assembly here. The other component they all contain is a controller, and this controller remains on the surface, and they also provide a marking jig. Most marking jigs look like this. They're a V block with a blade and a spirit level for making sure that the jig is level when the mark is being made. So the downhole unit includes an accelerometer. An accelerometer is the same technology that is used in your smartphone or tablet that allows the display on your device to switch between a horizontal or vertical as you flip it. The accelerometer detects motion and orientation with respect to gravity. In other words, it measures down. Sorry, is that a question? No? Okay, so in other words, it measures down towards the center of the earth. The way that it works, and it's important as geologists to understand the workflow, even though we don't operate the tools, they're operated by the driller. They are highly precise and highly accurate, the sensors that are in these tools. However, things still go wrong. And it's important to understand the workflow and what best practice looks like. So in the event that you are getting unreliable ORIs, you can know the types of questions and types of conversations that you can have with your drilling contractor. So the workflow starts with, well, the first step is to initialize the downhole unit. And this is done by synchronizing a timer or stopwatch within the downhole unit, and that sits inside the controller. Drilling commences, and the downhole unit takes readings every 30 to 60 seconds, depending on which tool you're using. When the inner tube is full of core, a break is registered by pressing a button on the controller at the surface. This also records the reading on the timer, which is how the controller knows which reading on the downhole unit is the one to use to determine the orientation of the core. It also starts a countdown during which drilling completely stops. This point in the process is really, really important because, as you can imagine, drill strings rotate very quickly, and there is a lot of torque and a lot of movement in that drill string. If the drill string is vibrating or still rotating when that reading is taken, then it's not going to be very reliable. So at the end of that countdown, the driller pulls back on the drill string, causing the core to be grabbed by the core lifter, or sometimes known as a shoe, and breaking the core from the bedrock. This is another possible point of error, because if the core lifter is old or damaged, it can cause the core to slip and spin within the tube. So once the inner tube is retrieved and laid out on trestles, the orientation reading that was taken after that countdown was completed is read from the DHU. And depending on the tools used, either the tube full of core is rotated until the gravimetric bottom of core is facing down, or a special orientation jig is rotated until the core is in the correct position for marking. The driller then uses the marking jig to mark the face of the core that represents either the bottom of core or the top of core. They may also mark the side of the core if this is possible and the core is extending out of that core lifter a little bit. An example of that is shown in this picture here. So the next step on the journey to preparing the core for structural measurements is to create and draw the orientation line along the side of the core. Now, this can be done either at the rig by a member of the drilling crew or a geologist or technician, or after it has been transported to the core shed. One big recommendation I would have is if you are asking the drilling crew to draw the orientation line on the core, that they get the proper training involved and they understand the importance of getting this right and also understand what best practice looks like. So the best way to do this is to actually remove the core from the core tray and place it into a V-shaped rack, like shown here in this picture, sometimes referred to as an angle iron, where the pieces of core are fitted together a bit like a jigsaw puzzle as best as possible, but that they possibly can. The mark on the face of the core is then aligned with a straight edge on the angle iron, and a marker or crayon used to draw, or the straight edge of the angle iron is then used to draw a line from the orientation mark on the face of the core along the edge of the core across the breaks. The downhole direction of the drill hole should also be marked on the line, as you can see in this top image here. It's really important, obviously, to get that right. I have seen instances where core has been placed in the core tray the wrong way round, and so you do get segments of core which have got the downhole direction incorrectly sort of marked on that core, and that becomes very important for when you're doing your structural measurements, because that's your reference line. So I've already mentioned that the sort of accelerometers and the sensors that are used in these tools are highly precise and accurate. So what happens if the core locks together beautifully, but the orientation line between the two runs does not? Is it because one or both marks are wrong? Or is it one or both of the orientation lines have been drawn incorrectly? Errors do occur, and it's our responsibility to understand what can affect the reliability of this data that we're being given with regards to the location and the orientation of the drill core. So let's talk about that in a little bit more detail. There are a number of factors that can compromise the integrity of data, and they fall into one or more of the following categories. So there can be a problem with the tool itself. Probably by far the most common error is due to human error. It doesn't matter how precise or good the workflow is, as soon as you insert a human being into any type of workflow, the potential for errors skyrockets. Other issues can be with poor systems integration, especially even with the use of all this technology. Having systems talk to each other and being able to transfer data between them is still probably a little bit more difficult than it should be. And quite often this leads to transformation errors. So as you manipulate and wrangle that data to get it into a format that your system will accept, that's another point in which errors can creep in. Inadequate processes and workflows are the other problem or source of errors. So if we look in regards to the actual orientation process, what can go wrong? The tools. So any errors associated with the tools themselves are generally due to them not being calibrated properly. All vendors should run calibration checks on the tools when they return from the field and for service, and a calibration certificate is generally included in the kit when it's returned to field to prove that it is working correctly. Other issues that could affect the orientation reading is if the tool is operated outside of the temperature ratings. So the vast majority of these tools have an operating temperature of between -30 to +60 degrees. So if you are drilling through hot rocks, and there are some very hot rocks, especially sort of north of Australia and Indonesia. I have a customer who is drilling through rocks that get up to 200 degrees centigrade, and that obviously heats up the tools to a degree that the orientations are just not reliable. As I mentioned, human error. Even though some of this process and some of the workflow is automated in terms of the sensors in the tools, there is still quite a few manual steps in orientating core. And so some of the common errors are breaking off bottom too early. So that is the drill string isn't stable. It's still vibrating or rotating when the core's broken off bottom. Now, some tools will take 3 readings 5 seconds apart. And if these 3 readings or angles are different, then you know that the tube was rotating when the orientation reading was taken. Now, unfortunately, you can't go back and retake that reading at this point. But what it does tell you is that the mark that is on that core face should be treated with a little bit of caution. And if it doesn't match up nicely with the orientation line on the drill runs above and below, then that is probably the reason why. Another problem is breaking the wrong joint. Now, what I mean by this, if we look at this tool here, the electronics for the downhole unit are sitting in this part of the unit, which means that this joint here must be broken in order to take the reading. If you break the joint between the inner tube where the core is and the downhole unit, you lose the orientation completely. Core spin is another cause of unreliable orientations, and strictly speaking, if there has been core spin, then the orientation shouldn't be made. Sometimes though, the drillers do still mark that core, so you look for evidence of core spin, and that's shown in these sort of concentric circles that you can see in the image in the bottom right hand corner there. The other issue can be poor mark quality, and a poor mark can affect the quality of the orientation line. So if we look at a few examples here, you can see that the best marks are nice sharp lines, which you can then extend down the side of the core quite comfortably. This core here, you can see there that that could cause an angular error of up to about 15 or 20 degrees. Do you start marking the core from the center or from the edge? Part of the problem of these types of those kind of smudged marks, if I can call it that, is something like this. If you do not get an even break on the core, it can be very difficult for the driller to mark the core with these, especially if they're using these V block type marking jigs. Other problems could be if the marker that they're using is blunt, or they don't angle it in towards the blade. It's also quite difficult on these types of breaks to get the marker, the marking jig completely level. Some marking jigs, like this one here, use a constrained marking slot, which makes it very easy, or a lot easier, for the driller to get a nice sharp mark on the face of the core. Errors also can occur when you're reconstructing the orientation line. So if the core hasn't been pieced together correctly or with care, then you can get the orientation line can sort of waver and move around a little bit. If you use a shorter and even guide to draw the orientation line, so in the photo I showed before, the geologist was using the straight edge of the angle iron to draw the line. Now, if that angle iron has been damaged in some way and has got like divots taken out of it, you're not going to get a nice sharp line. So use a nice long straight edge to mark that orientation line. I mentioned before marking the downhole arrows facing the wrong way. So pay attention when you're taking it out of the core to make sure that it's not flipped around. So look at the geology, look at the structures to make sure that it's fitted together with care. The other thing is extending the orientation line across broken core. Now, when I talk about broken core, I'm talking about rubble. All right, not sort of clean breaks. If you have got a patch of rubble or very broken core in the middle of your competent drill core, you can't draw the line across it with any sense of reliability. So one element of quality control that is commonly used to assign a confidence rating to the quality of the orientation for each of the drill run. Now, there's a number of methods that can be applied to check the orientation line and resolve errors if they are identified. The simplest form, a rating, is based on the continuity between drill runs is assigned, with the highest confidence classification being assigned to drill runs where the orientation lines match within a sort of specified tolerance for 3 or more consecutive runs. Now, the tolerance does tend to differ between projects. It's very, very reliant on the degree of complexity of the geology and the structures. But generally speaking, as a rule of thumb, differences of 10 to 15 degrees tend to be a sort of a common tolerance. In some projects, it would be less than that. Another method that is documented by Rod Holcomb, and I've put the reference there for you. It's available on his website. It involves piecing as much of the core together that is possible, and then using the driller's bottom of core or top of core mark from the first run, draw a preliminary line along the entire length of pieced together core. And then for each drill run, measure the mismatch between the orientation mark and the line. Discard the outliers and then apply, and then the average mismatch, if you like, is calculated with the drill runs that is showing significant deviations are corrected based on the mean. Okay, there's quite a detailed step-by-step guide on how to do that in the document that I've referenced there. A confidence score is then, like between 1 and 5, is then assigned to each of the drill runs. Another method that systematically rates the quality of the orientation mark and the orientation line independently, and then a confidence classification assigned, is one that is outlined in this article in the SEG newsletter. The quality of the orientation mark is based on the potential angular error due to the mark not being a nice sort of sharp line. A angular error of less than 5 degrees is given the highest level of confidence, whereas no orientation mark at all obviously is the lowest. The orientation lines, the quality of that or the rating of that is based on the lock angle or the mismatch between consecutive runs. Something called a bamboo diagram is then used to help visualize the orientation log, which allows to help identify errors, allowing them to be corrected. So if you look on this hand-drawn log there, we've got the mark depth. We've then got the quality down here, which is, as I said, rated 1 through to 9, with 1 being the best, highest quality, and 9 the lowest. Lock angles, or the angular error of mismatch, are measured and reported on the bamboo diagram. You can see in this section of the core here, or this drill run, the mismatch is at 30 degree on one end and 330 on the other. That is clear evidence that the core has spun, and providing the geology is sort of helping you out here and confirming that, then that orientation line could potentially be corrected and before you take your structural measurements. Another common sort of quality control process is to assign a confidence rating to the entire drill hole, and this is based on the cumulative mismatch angle over the entire hole. So before you start logging the structures, there are a number of questions that you need to ask yourself. In geological terms, many different structures can form from a single deformation event or stress field. These structures can exhibit varying orientations, and when related, they can be understood as a unified system. So it's important to just sort of step back a little bit and look at what structures are present. You need to look at the properties that define the various structures in terms of the composition, the texture, the infill. you need to look at the relationships between the structures, particularly the cross-cutting relationships and associated alteration. It's important to recognize that structures may appear differently depending on the perspective. So is the hole being drilled at a low or a high angle to a particular structure? And lastly, how do these structures observed fit in with the understanding of the larger scale geological interpretation? Does it validate the interpretation or not? So there are a variety of tools that can be used to take structural measurements in drill core. These can be split into manual and digital tools. And before we look at each one of these in turn, it's important to understand the measurement conventions that are used. So many of the manual tools measure the orientation of a feature relative to the core axis and the orientation line. Planar structures that intersect the drill core present as an elliptical shape, as shown in this sort of cartoon diagram here. And the orientation of these structures are defined by alpha and beta angles. The beta angle is the angle between the orientation line and the apex of the ellipse, measured in a clockwise direction around the core. Whereas the alpha angle is the acute angle between the core axis and the long axis of the ellipse. These alpha and beta angles are converted to dip and dip direction, generally using a computer program or a stereo net. To measure the plunge and azimuth of a line on a plane, a third angle needs to be measured. This is the gamma angle, and it has a number of definitions, so care should be taken to be consistent with your measurements. I'll also mention that the literature can be a little confusing around these measurements because authors use different naming conventions for the same measurement. They all tend to use sort of Greek letters from the Greek alphabet, but whereas some refer to gamma, others refer to delta and even omega. So the main thing to remember here is to be consistent. The first method involves measuring the angle from the long axis of the plane in which the lineation lies to where it intercepts the ellipse for the first time in a clockwise direction. The second method involves measuring the angle clockwise from the orientation line to the first intercept of the lineation on that plane. These measurements are then converted to plunge and azimuth in relation to the plane that they lie within. Okay, so manual methods. So these are some of the tools that measure the alpha and beta angles directly. They include the chronometer, a goniometer, wraparound protractors, and protractors or protractors with pivot arms. The beta angle is measured using the horizontal scale on these sort of tools here. Sorry, the horizontal scale here, and then on the goniometer, it's the circular measurements on the end. So to use the chronometer, you insert the core facing in the correct direction, and this is marked on the tool. And the beta angles are measured by aligning the apex of the ellipse of the bedding plane or the structure to be measured with the 0 degree measurement on the horizontal scale there. And then the angle is read off the scale as where your orientation line intersects the measure. alpha angles are aligned and measured off the side measurements here. For the goniometer, it's a little bit different. So the beta angles are measured by aligning the orientation line with 0 degrees rather than the apex of the ellipse. And then the angle, the beta angle, is read at the apex of the ellipse using the scale on the end of the tool. Alpha angles are measured by the measurements along the side of the tool. Wraparound protractors are the same as the goniometers in that beta angles are measured by aligning the ori line with the 0 degree scale and the angle read at the apex of the ellipse, and the same angle, the alpha angles, are measured using the side measurement markings. So common sources of error with these types of tools. Firstly, the core is placed in the tool in the wrong way around. You can see on the tools here, we've got a clear indication of which is the downhole direction on the chronometer, and then with the wraparound protractor as well. Obviously, if you insert the core the wrong way around, you are going to get an error of 180 degrees. Other very, very common sources of error, particularly if you've got chronometers and wraparound protractors or goniometers being used on site, is that people forget that the tools are used in a slightly different way. So for the chronometer, when measuring beta angles, the 0 degree mark is aligned with the apex of the ellipse, whereas with wraparound protractors and goniometers, you align the 0 degree mark with the orientation line. The wrong tool size is used, and this can cause errors, particularly with the alpha measurement. So you get different size tools to cater for the different size diameters of the drill core. The picture that you see at the top there, you've got the core or the chronometer is too big for the core, and the core is sitting on the base of the chronometer and showing there. You can see the structure here. It's aligned with the 60 degree measurement mark. If, however, you hold the core so that the apex of the structure is sitting at the 0 degree mark, which is where it should be sitting, you can see that it actually moves the measurement to a point of around about 55, 54 degrees there. So it's really important that you do use the right size tool for the core that you're using, or the core that you're measuring, I should say. So the thickness of the orientation line itself can cause errors. So you can see here that the thickness of the blue orientation line here is it's almost 10 degrees thick, and that introduces a potential measurement uncertainty of around 3.5%. In the bottom picture there, again, this is a fairly small diameter core, a B size, and the ori line has an angular width of around about 5 to 6 degrees there, resulting in a potential error of around 2%. So again, it's really important that you think about the orientation line when you're doing your markup. Identifying the apex of the ellipse when you've got high alpha angles. So these are very shallow dipping structures, and shallow dipping structures can be very difficult to read with manual or with some of the digital methods. You can sort of see here that the apex of the ellipse, it's really quite difficult to know or to identify where that is. So just be mindful of that. Finally, errors due to manual entry, that human error again. So with all of these devices, you're measuring the alpha and beta angles, and then you are entering them into maybe a spreadsheet, or you're writing them onto a paper, which was then going to be translated into the computer. Also typing in the alpha and beta angles, errors can be made, which will then be passed on to calculating the dip and the dip direction. Another manual method, which is very, very common, a very common tool, is an orientation frame. It's also known as a rocket launcher. So these frames are set up to allow you to physically orientate the drill core as it was sat in the ground before it was extracted. The geologist can then measure the orientation of the features directly using compass chronometer or a smartphone app. So this method measures the dip and dip direction of the feature sort of directly. Now, there's many, many different types of these frames, ranging from sort of precision engineered devices through to homemade frames. No matter what type of frame you're using, it is very, very important to ensure that the frame is level and it's sitting on a level, stable surface. The core needs to be placed in the device so the downhole direction matches what is downhole. You can get errors associated with the measurements. You can see there in the top right-hand picture, a lot of people will use sort of flat planes or edges or even straws when measuring lineations to sort of steady the chronometer or compass and taking those measurements, and you can get errors creeping in there, and again errors due to manual entry into whatever system that you're using to capture this information. Those errors due to manual entry can be dealt with by using a digital method. Now, this is a handheld device. It's called an IQ logger. The new version of it is called a Logger X. And it uses something called an inertial measurement unit, or an IMU, to measure the dip and dip direction of the feature using the orientation line as a reference point. So an IMU combines the functionality of a gyroscope and an accelerometer. And the gyro used in this device is a reference or rate gyro. So the measurements are taken in relation to a reference plane. You align the device with the orientation line. So you place it on the line so it's aligned perfectly. You press a button. Pressing that button, what it does is it sets the IMU's plane of reference to the planned dip and azimuth of the drill hole. As the device is moved and rotated, so a laser is aligned with the structure of interest, and the measurement is taken relative to that reference plane and captured in an application running on Windows. It's a handheld device, so humans, again, can be the cause of error. So common errors are not calibrating the device when starting it. So a gyro needs to be woken up. And the way you do that is that once it's first started, you wave it in a figure of 8. Other problems are that reference gyros will drift over time. So it's really important to align the device regularly with the orientation line regularly, or after the core has been moved. Other problems are not holding the device perpendicular to the core face when measuring lineations. Remember, this device reads its orientation. It's the orientation of the device as it is lined with the structure. So not holding it in the correct position will have an impact on the measurements. Other digital methods that are being increasingly used include determination of structures and measurements from core photos. Now, the process of taking core photos is common practice for a long time, and there are a number of software solutions that take advantage of these photos to allow the identification of structures. either manually by drawing elliptical traces to match the structures in the core photo, or using machine learning to identify the structures directly. Both these methods have the advantage of automatic determination of the alpha and beta angles, as well as the dip and dip direction of the structure, in eliminating errors associated with manual entry and calculation. Some of the limitations associated with these methods are that some solutions only see one side of the core. Poor image quality and resolution can be an issue if you're using photographs, and some subtle structures might be a little bit difficult to see. So, how many measurements should you collect, and what should they be? Well, the short answer to this is it depends on the complexity of the geology, the geological system, and the objectives of the project. Another way of thinking about the term geological complexity is the variability of the structures present. So if the orientation and characteristics of a structure is relatively constant throughout the whole, then 1 or 2 measurements in every drill run is likely sufficient. However, if the attitude is variable within and across the drill runs, then you'll need to take more frequent measurements in order to help verify and validate understanding of the geological interpretation. Ideally, measurements should be evenly distributed throughout the drill core in order to capture any variations. The purpose of collecting structural measurements should also guide the number of measurements. If the goal is to understand broad-scale trends or major structural features, then a smaller number of measurements may be acceptable. If, however, your goal is to understand and characterize individual structures, then a larger number of measurements will be needed. Ultimately, in order to be useful, you need to collect enough structural measurements to allow for statistical analysis, and this means they need to be representative and relevant. So I'm going to talk a little bit about stereo nets and what you do with these measurements. A stereo net is a method for viewing 3-dimensional data in 2D. Imagine a plane cutting through the center of a sphere. If we remove the upper half, you can see lines of latitude and longitude marked on the lower half of the sphere. So the stereo net is basically the lower hemisphere graph. An arc is formed where the plane cuts cuts the sphere. And if we project the intersection points of this arc to the zenith of the sphere, the points where it intersects the stereo net forms the great circle of the plane. Steeply dipping planes will plot closer to the center of the stereo net, whereas shallow dipping planes plot towards the edge of the stereo net. Now, obviously, it gets pretty messy when you have a lot of measurements, and it becomes almost impossible to interpret anything useful, which is why it is common to represent the plane using a point, which is called a pole to the plane. This is an imaginary line which is run perpendicular to the plane, and where it intersects the sphere and is projected up to the zenith, where it intersects the stereo net, is the pole to the plane. For lineations, lineations lie on a plane and they're measured using the plunger and azimuth. They're represented by a point on the stereo net. So in this image, the lineation is represented by the blue line. The point where it touches the edge of the lower hemisphere is projected back up to the zenith on the sphere and plotted on the stereo net at the intersection point. Note that it plots on the great circle of the plane that it lies on. So I've talked about the various points in the orientation process where errors can occur. So this is the orientation reading itself. Placement of the orientation mark is incorrect or of poor quality, making it hard to draw a high quality orientation line. Errors associated with the orientation line can be due to not piecing the core together properly, or making mistakes like the down hole arrows are facing the wrong way. Errors can also be introduced when measuring structures through incorrect use of the tools or entering information incorrectly into the database. Statistical errors can also occur through the choice of which features to measure and the number of measurements taken. So stereo-nets can be useful in identifying these errors. So the top image there shows measurements of the same feature in a single drill hole. When we superimpose a small circle, which is essentially the best fit line onto the data, the center of the small circle distribution, if it's centered on the drill hole, then you need to look at the drill hole here is marked as a circle. The center of the small circle distribution is the cross. Possible causes of this include spun core, poor quality orientation marking, and poor quality logging. If you've got a pervasive feature of known orientation, it's worth taking at least a couple of measurements in each drill run to check for relative spin. It's quite common for these types of features to be undermeasured because they're well known and therefore considered not all that important to measure. But it is very useful in identifying potential issues. Another useful diagram in identifying issues is a rose diagram. So this is where the frequency of measurements of a particular feature is disproportionate to other features, potentially resulting in data bias. The distribution of points from well-orientated core will have a relatively small spread on the stereo net. This slide is an example of what angular errors look like. So the drill hole is inclined at an angle of -60 degrees towards 270 degrees. The structure being measured has an alpha and beta of 45 degrees each. Now, what I've done here is the red points on the stereo net show a systematic change in the alpha angle of 5, 10, and 20 degree errors. Similarly, the green points show the same errors for the beta angle. And so you can see there that it actually creates quite a big spread on the stereo net. Ideally, those clusters should be as tight as possible. So, messages I'd like to leave you with. So, quality structural measurements are only as good as the driller and the geologist. Okay, this is a shared responsibility. The drillers are using the tools, and it's important that they understand why it's so important to get quality orientation. And geologists have a responsibility for understanding what tools are being used, how that orientation line gets on the mark, and ensuring that they're doing it correctly. Spending time marking up and assigning confidence classifications to the drill run and being consistent. Understand how to use the structural measurement tool correctly and each one of their limitations. Take as many relevant measurements as you need. Beware of cumulative errors. So an error in placing the mark on the core of, say, 5 degrees, add to that an error of 5 degrees when drawing the orientation line, another error of 5 degrees when you're taking the measurement. It all adds up. And lastly, do not, please do not try and rely on technology to fix poor data quality. It's very good at identifying errors, but collect the information correctly in the first place. So in conclusion, understanding structures of rocks is not merely an academic pursuit. It's a fundamental aspect of geological investigation. It underpins our ability to uncover valuable resources, to assess environmental impacts and mitigate hazards. It also allows us to make informed decisions about land usage. So by delving into the intricate details of rock structures, we can unravel the Earth's geological history and better prepare us for the challenges and opportunities that lie ahead. So thank you all very much for your time, and thank you for the opportunity of presenting today.
Sarah, thank you very, very much for that. I appreciate it's fairly late where you are, but thanks for taking the time. We have a minute or two. Does anybody have a question for Sarah? If you can't think of one now, please write it down and we'll send it off to Sarah in due course. Just hold on, there might be two. Okay. Okay, if there are no questions, Sarah, thank you very much again for your time and your experience today.
Yeah, okay, no problem at all. Thank you very much.
Next up, we have Werner Huelefeld, who's going to talk to us about downhole surveying. Werner is the Business Development Manager for MDEX for the Middle East and Africa. He comes from Port Elizabeth, where he completed his MA in geology at UPE, and then went to Northwest University to do an MBA. He's also registered with SACNASP and holds a project management professional certification. He's worked for a number of small exploration consultants, as well as Xstrata and Glencore, and more recently worked for international drilling contractor Master Drilling before moving to MDEX in 2021. So, Werner, if you would like to share your screen, and it's over to you.
Thank you very much, Tanya. Thank you for the opportunity to the GSA as well. I'd just like to confirm, am I sharing the correct screen before I start?
You're not sharing any screen at the moment.
Then let's see. There we go.
Yes, that's the correct screen.
Okay, thank you, Tanya. Okay, so today's presentation, I would just like to take the audience through a basic introduction of directional downhole surveying in the exploration industry, but also touch on some other areas within the mining industry. So this will just be a basic introduction, and my email is at the bottom if you want to get in touch with me. And I'd just like to acknowledge some of my more expert colleagues in MDEX as well that assisted me with putting this presentation together. So I think I'm sort of in a unique position, as as Tanya said, I've been in the geology industry as an exploration geologist, but also worked in the drilling industry, and now I finally moved to MDEX, which is one of the core businesses of the company I'm in is downhole surveying. So I've had just unique knowledge of experiencing downhole surveying as a geologist firstly, then as a driller, and now actually working together with the supplier that actually supplies these tools. So in today's presentation, I'll just take you through the following topics. So, so why do geologists need to have a basic knowledge about downhole surveys on site? And to be very honest, initially as a geologist, I took also the data quite for granted, the accuracy, and just accepted that everything is correct and 100%. And as technology has evolved since I started, the accuracy and precision of data has become very, very good indeed. I'll take you through some of the types of downhole survey tools we get. Then I'll specifically tell you a bit about gyroscopic survey tools and north-seeking gyros, especially. Then I'll also allude to what is survey accuracy and precision. And then I'd like to go through some more practical topics for geologists that maybe start out on site and do not have that much technical knowledge of surveying, downhole surveying and surveying tools, and that is when should they use what gyros, and specifically when should they use a north-seeking gyro. And then I'll tell you a bit about how the data should be presented in my view in best practice, and how do you know the survey is good. And with that, I'll also give the audience a bit of a practical do's and don'ts when you're doing either your driller or service provider is doing downhole surveys on site. So why should a geologist have basic knowledge about downhole surveys? Well, like Sarah alluded, not only to the structural geology and knowing the actual orientation of your structures in space, boreholes are never straight. So to know your actual directions is very important, but I'll focus more on even the more basic thing is that everything you might think you know where you are, but you actually are not there. And if I just take the laser pointer, this is what I'm alluding to is where the ore body really might be, and this is just a idealized, very simple square little ore body, and where you think it is because of maybe using a lower standard survey tool or not following best practices. So that accuracy that you have there then obviously moves into all your models and everything you do after that. So that data is really right at the beginning of the process, and if either you're in your beginning stages of your exploration and you're trying to find out where to explore and define an ore body, or even when you're trying to infill and define the ore body better and just get better confidence on the data, you might be far away from where you actually might be. So this is just the basic sketch we all know. The other thing is to calculate the volumes of these basic ore bodies. We need to know those true thicknesses. That's one thing, and that's just mentioning on our inclination. So this is just in a simplified ore body. In complex ore bodies, this becomes even more important, and you have to drill denser patterns and be even more accurate and sure of your accuracy and precision when you're doing downhole surveys. So that's on the inclination. So if you have this true thickness and you're quite confident of what it is, then you can at least calculate the volume based on the inclination or the dip of the borehole and where it's actually intersecting that ore body at the top and also at the bottom. But also the other aspect you should also think about is your azimuth as well. So it's not only in that one dimension, it's also in the azimuth dimension as well. So not only do you need to have the true thickness of the ore body, but you also need to intersect it as perpendicular as possible to the strike. So to get that true thickness of the ore body at that point of your borehole. So already the ore body might be complex and might be moving. So if you at least know at that point that you're intersecting it at the best perpendicular angle, then you can at least work out the true thickness at that sort of intersection area of where you drilled your borehole. So why is it also important? Where does this borehole survey data fall? It falls right at almost at the beginning year of your mining cycle, and it's the exploration and discovery portion. And that's also those human errors that occur here is already, like as Sarah mentioned in her presentation, the human errors is already propagating and compounding if you're making errors. So if your tools are also adding to these errors, it just becomes bigger and bigger, and the error just accumulates as you go further down this mining cycle towards where you want to start developing and producing actually something from the mine. So I said that's just why it's important for geologists to know a little bit about surveying in terms of exploration and target delineation and definition, but it's also important in the production space and the development space as well. So if you take the scale of economics, the pricing you might pay on rentals or services for doing proper surveying is minute when you compare it to having to potentially redevelop a mining drive because the survey was not accurate enough and you actually didn't hit the target you wanted to. So it's not just for planning at exploration level and making sure your volumes are correct in your resource definitions, but it's also during your current operations, your blast design, are you over and under mining, you minimize the grade control required, and so the more accurate the survey is, the more accurate you will be, and you will actually know where you are and where here actually is when you're down there. So what are some of the common types of downhole survey tools? Well, they use basically two principles, and you get your magnetic types survey tools. That obviously is the magnetic field of the Earth is there to determine determine where they are and what their orientation is. And then you actually get your gyroscopic tools, which use the centripetal forces or angular momentum forces of the Earth to actually determine what the orientation is in space and where they are. So in the magnetic tools, uses like I said, the magnetic field of the Earth. Usually these tools originated from the oil and gas industry, and the oil and gas industry has been the main drivers of technology and getting us to where we are now with gyro tools. But this tech has since become quite aged, but is still reliable in certain instances, depending on the accuracy and precision you require. It's still relatively cheap compared to some of the best gyro tools today, and it's usually used in a more low confidence initial exploration. So if you have it's commonly used in RC drilling and percussion drilling applications actually. So just to take note of it, but we'll also talk about it a bit more later. These tools are affected by any ground magnetism and even magnetism that can be induced by some of the drilling equipment itself if not used correctly. And obviously these tools give you magnetic north, which you then need to transform into true north before actually using the data in any spatial models. So then we get the first type of gyro survey tool, and this is called the reference gyro, or sometimes also referred to as the rate gyro in the industry. And these were some of the first gyros that were introduced, and they're also sometimes known as free gyros. These tools are not affected by magnetics, and they use the Earth's axis of rotation to calculate their relative positions in space. So one thing about the reference or the rate gyros, it needs to be set to a known bearing on the surface, and then it actually measures its change in position or its rate of change, which I'll also get into a bit more detail later. With these gyros, drift is often error, and they're also prone to human error. So if your initial angle is not set correct, or your direction, then the data will be compromised, and that error will actually compound. So most of the older tech in the market in the gyro space uses these gyros, and over time, people have moved over what they call the north-seeking gyro. These are also not affected by magnetics, and one of the main differences is that they do not need a starting bearing like the reference gyro, and they're also less prone to drift, and also have a higher vibromechanical resistance to impacts. In other words, they can take a few harder hits than the rate gyros. So I just took the slide to just show you a bit what these look like. So along with these survey tools, you often also have what they call the running gear. The running gear is basically just the protection and the subs that protect these tools from bumping, and also just allow them to actually connect to whichever equipment the drillers have, if they're using the wireline, or if your survey company has got the external wireline that they're using, it will connect to the spear point, and then you have various adapters, and also you have spaces depending on the borehole size you're drilling, so that survey tool always sits flush in the middle of your rod going downhole. So here you can see this is an example of a magnetic tool on the left. There's the bump sub, so that just protects it if it falls right through the rod or it's going too quickly, to just give it a bit of a cushion when it hits the bottom of the hole. The actual survey instrument will be enclosed within this capsule here, and then because it is a magnetic tool, with this one you obviously need some rods to actually push through the bottom of the rod string, so you don't have that interference with the metal of the rod string. On the right hand side we have a gyro tool, and the tool actually also sits at the back here, and this is even a bigger bumps up here because the tool is even more sensitive. And here on the right you can just see an enlarged picture of what this running gear looks like. So let's talk a bit about how gyros and north-seeking gyros actually work. So as I said, the term gyroscope comes from the ancient Greek language. So it is it uses the Earth's natural rotation in order to determine probe's heading relative to north. So it basically actually uses some Newtonian laws. In other words, the gyroscope is in a constant state of spin, the older mechanical gyroscopes, and if you try and move that gyroscope anywhere relative to that position it's in, it actually detects that force that's incurred on it, and by using that force, it actually has 3 accelerometers measuring the X, Y, and Z on that force relative to it. And those gyros, the 3 movements is called the pitch, which is basically the dip. So in other words, pointing towards the bottom, towards the top, then the roll, and that is actually the 360-degree turn of the tool, and then the yaw, and that's your azimuth. That's moving. You can basically think about it if you're looking north, moving to the left, to the west, or to the east. So as I said, that consists of 3 accelerometers, and they measure the gravity relative to the position of the tool, giving us that inclination on the roll, and then also the relative position change. And using that principle, the tool actually measures what its relative movement in space to its starting position. This is just to show you a bit, I'll just some different types of gyros and what they look like in theory when all the housing and the armoring and everything has been removed. So we get mechanical gyroscopes. Those are the start of the gyroscopes, the older gyroscopes. I think many of us had that one where you actually spin it, and you can actually put it on its pivot point, and it remains standing on any position or point while it's spinning. And those gyroscopes, like I mentioned, work by actually detecting the relative change in force or of external force, the relative change in acceleration as a result of external force that's imposed on it. And by that, they know actually where they're moving and what the orientation is. And since then, we've actually moved on to more advanced type of gyros that you actually see these PC boards, which is the microelectronic mechanical or the MEMS gyroscopes, and that's what most of the rate gyros have in them these days. And then we have much more accurate gyros, which actually use fiber optics and lasers. So in other words, like a fiber optic gyroscope will have 2 lasers that are actually running in separate, I can almost say like lanes. So this is the bottom, and due to the effect of change on force on these fiber optic laser positions, they actually detect which way they're moving in space, either X, Y, or Z. So at the bottom here, you can just see a graph of these gyros and where they actually plot in their accuracy, or we can call it sort of their reliability. So we get everything in the range from gyros that's in the consumer. This is the really bad watch gyros that you use when you go jogging or on some of the earlier cell phones, and these have a relatively high bias stability. We'll also touch upon it a little bit later. So that basically means, so if you have an average path and you keep the gyro on that path, how much would it drift from that average whole path over time? And that's measured in degrees per hour. So you can say in 1 hour, if you left the gyro in going in the single path, in a straight path, this is how many degrees it would vary from the path. Obviously not good on this side, and obviously very good on this side. And then the scale factor stability measures how sensitive is that gyro to detecting a change in its angular velocity. In other words, how sensitive is it detected and accurate and detecting a change in its position. So obviously the very high performance, high cost, low volume gyro sort of is in this block. Here you can see is the ring laser gyros. So they in this block, and then most of the gyros that's used in survey tools fall within the MEMS gyros, and they would be somewhere in this area here. Most of the downhole gyro survey tools that geologists encounter in the field. This is just to show you, this is just like I mentioned, we have the mechanical gyroscopes, optical gyroscopes, or those ones I mentioned with the 2 lanes and the lasers actually running in opposite directions, and they actually measure that the change by measuring the effect of the lasers on it. And then we also get some other gyros like ring laser gyroscopes. So this is the one this is a type of gyro that's used mostly in rate tools or reference tools and north-seeking gyroscopes, and that's called the microelectric mechanical systems, or MEMS gyroscopes. And this is just to show you what it looks like, and it works on the same principles, but it's got it's actually a sort of a solid state gyro that works in the circuit board. Usually it's this little circuit board that if you open everything in that gyro, this is what you'd see. And most 90% of the value and the technology of that gyro is contained within this little circuit board here. So what are the factors that determine if a gyro has a quote unquote good or bad performance wrap? Well, the things we need to look for is the angular random walk. And the angular random walk is basically includes also the noise that the gyro experiences in the background. And it describes basically the average deviation or the error that will occur as a result of noise on the gyro. And too much noise will cause it to drift. And every time, over time, it will actually increase the error on the initial angle that it measures. So it will change that error the whole time. But I mean you can calibrate this initially, so your gyro can have a error in the beginning, and you can actually calibrate that to correct it. And another big element you need to look for is the bias stability. That's also known as the bias instability. Some people call it the bias instability as well. So this can be defined as how much the gyro or the sensor drifts from its mean value of the output rate. In other words, if I sent the gyro on a known Borehole path, it would on average maybe have a standard error of 1% this way, or 1 degree this way, 1 degree that way, 1 degree this way. And this is a measure of over time how far it actually drifts from that average. In other words, if it has a very bad bias instability, it would over time just drift further and further and further from this average change in the accuracy of the gyro. So other things you need to look out for is the bias offset error. And this is when you have say an input of a certain value, and you always get an output of the other value. It couldn't be a 0 value, but you always get a non-zero output value of the gyro. And this is usually measured at sort of 25 degrees Celsius, which is the room temperature or best optimal temperature for operation for most gyros. but this can also typically be fixed by sort of correcting it. So always putting that same offset error. Then another factor that actually determines the performance of a gyro is the temperature, as Sarah also mentioned in her presentation, that temperature affects the gyros. And I think to put it in basic terms, that is more the higher the temperature, the more the background noise, and the more your gyro will vary from its performance, accuracy, and precision range. So, and another one that's very important and more practical in the field is shock and vibration sensitivity. So these gyros can get damaged and do get damaged, and some of them are more sensitive to damage and others are less. So that is always important that you handle the gyro according to the spec sheet in terms of what temperatures it should be stored at, and also what shock and vibrations and speeds you can move the wire line with. Here I've just shown you some of the different stats between the different types of gyros. So you can see here that consumer gyros are the really cheap ones, the poor ones, they're everywhere. And the bias instability is between 30 to 1,000 degrees per hour. So if you left that gyro and you sort of didn't calibrate it, or almost do like the figure of 8 on some of them that Sarah also mentioned, then you can have a 30 to 1,000 degree drift. So in other words, if you leave the gyro there and it's telling you I'm lying at north 30 degrees, when you come back an hour later, it might be west at 50 degrees. So that's going to be the sort of a very inaccurate gyro. And then you get down to the real high-end tactical gyros. Those are the fiber optic gyros and the ring laser gyros, where, as you can see, there's almost no difference. When you let that gyro stand at the known angle and azimuth for an hour, it almost has no difference in the degrees and the accuracy that we left it at. So now that I was just mentioned a little bit about gyros and the different types you get, there, as I mentioned earlier, there are two main differences between the main differences between gyros is you get the north-seeking gyros and you get the rate gyros or the reference gyros. So what's the basic difference that a geologist needs to know? Well, a reference gyro needs to have that initial azimuth. So you need another device or a surveyor with a very accurate device to tell you that the borehole is starting at this azimuth and this inclination. And you need to put that into the gyro. And the reference gyro actually measures the rate of change when the gyro is in motion. So in other words, this gyro vector adds. It says I'm at point A, this is my azimuth and inclination. I've moved at this orientation at this distance. So here is my next point in space, and it vector adds. So if the initial reading is incorrect or not done very well, you will have error accumulation down the whole hole. That's not to say they always have high bias instability and higher random angular walk. They sometimes do have good accuracy and precision, but then often you compromise a little bit on the speed of your surveys. You have to stop longer and at more shorter intervals to actually get that higher resolution survey. So now we've spoken a bit about gyros and what the differences are, and we've measured survey accuracy and precision. But what is survey accuracy and precision? And I think most geos know that what is accuracy and what is precision. So you want to get this bottom left target. This is what you want it to look like. You want your gyro or your survey tool to be as reliable as possible. In other words, lowest biased instability, lowest angle, random angular walk. We'll talk about the accuracy now in terms of degree, and you want it to get that answer every single time. So it doesn't help your gyro is very accurate. It's very accurate, but it gives you answers all over the place. This gyro is very inaccurate. Sorry, apologies. This is very inaccurate, but at least it's giving the same inaccurate answer. And this is where you want to get to. Sorry, the bottom right. This is the top north-seeking gyros, which are very accurate and give consistent answers the whole time. Here I've just taken a little table to show you some of these inertial measurement units, or IMUs, and how their accuracy can vary. Obviously, at the bottom, these ones are sort of the fiber optic gyros again, and these technologies are often used also in ships actually to guide them exactly and what azimuth and path they're going, bearing they're going. So if you compare some of the best sensors, you have said to some of the best north-seeking gyros in the market, some of the best gyros has 3.75 to 26%, 26 times better bias stability than the best miniature inertial measurement units available. Those are the ones that are used in your phone or in your watch. So here I've just taken an example of a graph of some of the 3 gyros on the market, and I've just called them gyro 1, gyro 2, and gyro 3. And obviously they've got different specs, but here's just to show you that you shouldn't take the specifications of any gyro you're using on your project for granted. This is a example of a borehole that's drilled to 1,000 meters at a minus 60 inclination, and we're assuming the borehole is going in an exactly straight path. So here we can see the difference between gyro 1 has an area ellipse of up to 19.6 or almost 20 meters. In other words, you aiming for a certain target, and it's telling you you're at that target, but you can be anywhere within 20 meters around that target. And that's similar to gyro 2 and then to gyro 3, which is obviously some of the higher, these are obviously some of the higher quality north-seeking gyros that's on the market currently. So let's just recap that section and just talk about, so what are some of the differences of the gyros, types and modes, and north-seeking and continuous modes and gyros. So the reference gyros often referred to as the free or rate gyros. So the basic difference in operation compared to the north-seeking is that they need to be given that starting direction, either with the help of a surveyor or a rig aligner tool. The rig aligner tool also has to be scrutinized by the geologist. So the rig aligner tool also has to give you a correct azimuth and inclination. If that is compromised, then the whole will be compromised and the error will be added or accumulated. They are superior, the pros are they are superior to the magnetic tools and can work in magnetic environments. In other words, if you have any environment that has magnetic tools or has steel downhole or in the area, you cannot use your magnetic tool, and you can then rather opt for a rate gyro. They are cheaper than the north-seeking gyros. Some of the cons are the human errors. They're more prone to the drift and sensitivity to temperature changes, any impacts, and they can only survey in multi-shot mode or single shot mode. That means you need to pull the go downhole with your wireline or either uphole, and you need to stop at certain positions and wait a few minutes at each of those depths to measure take the survey at that depth. So the north-seeking gyro. So these gyros are again not affected by magnetism as well, and usually they are consistently more accurate than reference gyros at greater survey speeds. They do not require any manual inputs or referencing like the reference gyro. In other words, these gyros know what the absolute position in space is, so they don't need that initial azimuth and inclination to be inputted into the tool before it starts its vector adding. So the pros are the much higher accuracy and precision, which we'll see in some of the tools in some of the next slides, and we have seen as well in some of the previous slides. Both compared to the reference and the magnetic tools, and these tools, have the capability to survey continuously. In other words, you can pull the wireline at the set meters per second, and the tool actually takes shots every half a second or every second or every third of a second, depending on what you set it to. So it can be pulled up at constant speeds at certain angles, And you can still also revert back to the multi-shot method, the one stopping and taking a reading at every depth on the tablet. And as I said, most do not require any manual input while surveying. What are the cons of the north-seeking tool? Well, not going to beat around the bush. They come at a premium and are more expensive than both the rate or reference gyros, and considerably more expensive than the easy track or than the magnetic tools. So when you are assessing a requirement for your project, and the surveyor or anyone's going to give you a spec sheet, or how do you actually know what to look for on the gyro spec sheet? So one thing I've realized in my time is that different suppliers actually quote this accuracy and precision of the tools with different sigma values. In other words, statistically speaking, a 1 sigma or 3 sigma is better indication of what the accuracy of the tool is, or what all the data sets of the tool is, than the 1 sigma. If a person gives you a 3 sigma quote on or spec sheet on accuracy, that means, say that tool was tested 100 times, that indicates what was the variance of the tool in terms of its accuracy with degrees for 99.7% of all that 100 data points, the best ones. And then the 1 sigma only tells you what 68% or 68 of the points was of that data. In other words, it tells you, the one tells you what all its data did, what was the furthest it was out with 100 survey shots it does, whereas the other spec sheet only tells you the best 68% of the data. So in other words, you cannot compare apples with apples in that case, because as I'll show you in the next slide, that here's an example of a north-seeking downhole gyro tool. So here is its 68% or 1 sigma stat plus minus 0.1 degrees, 3 degrees, apologies. Whereas when I ask that same tool, what is your sigma 3, it suddenly goes to plus minus 1 degree. So in other words, when you compare any tool to each other, any tool with another tool, you need to have the same sigma when you compare it. Here's an example of a rig aligner. Those ones use those fiber optic gyro principles. So here I can say it's a 1 sigma, it's plus minus 0.08 degrees. Whereas if the supplier is quoting in 3 sigma, that means all of their static survey readings, then suddenly the reading becomes worse. So you should always compare a 1 sigma with a 1 sigma or a 3 sigma with a 3 sigma. Here I've just extracted some of the common spec sheets. You can get these off the internet of multiple suppliers, and you can see that some suppliers actually quote in 1 sigma, whereas others quote in 2 sigma. So you should compare these. Off the face, this one might look like worse than this one, and it is if you compare the 1 sigma to the 2 sigma. But you should ask this supplier here, what is your 2 sigma reading? Or you should ask this supplier conversely, what is his 1 sigma reading? And then you can actually compare the accuracy of the 2 tools that you want to use on your project. So when should a geologist use a north-seeking gyro? Obviously, there are some cases where a north-seeking will not be required, depending on what stage you are, what type of deposit. Is it a simple deposit? Maybe it's a really simple iron ore or a coal deposit, and you're just doing initial probing. Then you will not need a north-seeking gyro. You could maybe just use an easy track and just start to sort of get targets, and then later you can evolve them to a north-seeking gyro. So what are some of the questions you should ask yourself? Like I said, what size and type of drilling am I doing, and what's the orientation I'm drilling? If you're drilling vertical and there's no magnetic minerals in the area, and you're doing RC, it might be better to just start off with a easy track. But if you're drilling at angles, are you drilling deep? Is it a complex deposit? What are the characteristics of a deposit? Yes, then you might want to consider using a north-seeking gyro because of that error ellipsoid example I showed you with the 1,000-meter hole at minus 60 inclination, and to know exactly where you are. Then you need to ask yourself, in what phase of the project are you? Am I only, like I said with the RC, am I only defining boundaries? Am I only drilling for sterilization, or am I starting to drill infill and getting more definition on the ore deposit or ore body? Then I might consider using the North Seeker. Then what will my drill rates be? Remember, magnetic tools need aluminium rods, and they need to go beyond the drill string, and they take longer because you cannot send the magnetic tool down with the wire line every time in the rods. It needs to stick out at the front of the drill string. So you need to put it down, stop drilling, stick it down past the drill string, pull everything up, reattach and start drilling. Whereas with some north-seeking gyros, you can actually send it down with the inner tube and actually get a measurement every single drill run. And what level of data quality am I comfortable with? If I'm just trying to hit, like I said, a large, simple ore body, lower quality tools might be better. But if you're hitting that highly complex mineralized zone at depth, you need the north-seeking gyro. And obviously, if there are any magnetics in the area, you need to use a gyro, and not necessarily a north-seeking gyro, but you will need to use a gyro. So what's the worst case scenarios? Thinner deposits, complex bodies, like I said, complex mineralization styles. I need to be sure where I am and need to very accurately mine at very high cost, deep mining. Magnetics, we've mentioned multiple times. Where you need maximum structural information, maybe there's some parts that's really sensitive where you're going to develop, and you need best data. And then those deep surveys, you don't want to lose accuracy and precision exponentially at depth. And the one thing we haven't mentioned also is drill rod diameter. You need to also determine what your drill rod diameter is, and depending on that, you will also have a limitation on certain tools. Certain gyros are smaller than others, and some magnetic tools do not fit in RC rods as well. So you might not have an option to use magnetic tools, and you'll have to use a gyro tool in that case. So that's also another consideration you need to take when you're choosing the correct tunnel survey tool. So how should once the driller or the service provider has conducted and completed the tunnel survey, what should it actually look like? How should the data be presented? And how do you as a geologist know more or less that the data is quote unquote good? So data from the drill site is usually firstly transferred these days onto a PDA. So you're either going to put in the depths manually, like I said, on a multi-shot method, where you actually have also a little depth encoder that the wireline actually runs through, and that tells you actually how deep the wireline is down or not, and hence the depth of your survey tool. And you're either going to stop or you're going to run it continuously. So that's the two methods, depending on the inclination of your borehole. The data is then firstly transferred to external PDA, which most have on site these days, and it's usually done via Bluetooth at the moment, or infrared. A lot of tools still have the infrared window that you actually plug into the USB port to the tablet, and you actually communicate with the tool. And then you first get a printout, some similar to this on the right, which gives you all the details of that specific survey. And on here, you can already check some details, such as was the temperature within spec. Earth rate delta is the one that tells you what was the change in the gravity. So if that's very high, it could indicate that the tool was maybe dropped. And then these days, the data is transferred from that PDA either via, usually via Wi-Fi onto a cloud database. And different companies different cloud databases, and it goes directly there, where in some instances, some companies even give the ability to assign it to different projects and boreholes and actually approve the data according to certain QA/QC parameters that you can set at the beginning of the project, or actually per borehole that you're drilling. Most of these devices you can still also download it simply onto a USB, and you can export the data as a CSV, which you can then use in other third-party devices. So the one important thing is not even considering the QA/QC and all the other functions is that the less this data is manually handled, the less errors and the higher the data integrity, and the more solid the audit trails as well. So the shorter you have that sort of quote unquote chain of custody, and the more you automate that, the less errors, human error, it's prone to as well. So that's in terms of the data going in, and that's usually what you should expect these days from the top survey tool suppliers in the market. So what are some of the QA/QC things? Well, a lot of these tools, actually the clients set their own tolerances. In other words, when you start a project or you create projects in certain cloud storage spaces, you can actually, for example, with a magnetic tool, you can actually set that if it gets any magnetic fields higher than certain amounts, it should flag you. If any of the borehole path readings varies more than 2 degrees from your planned path, it should flag you, and you can actually set these tolerances to give you early warnings when your borehole might be deviating anything major from 2 to 3 degrees in different azimuths or inclination. A lot of these tools actually have inherent tolerances built in for magnetic dip and field strength settings, and it depends on the magnetic declination actually of where you're drilling around the globe. So that will automatically flag or reject some data in some of the top suppliers' cloud-based systems. In terms of the north-seeking gyros, I think the most important one for a geo to remember is there's a factor that's, and it's one of the previous slides, it's called earth rate delta, and you should ask your supplier on your site what's the maximum earth rate delta a reading could have, and that would actually tell you that the tool actually moved too fast, or it was moving during a survey. So that's one of the most common ones we use. Naturally, you can, in the north-seeking gyros, you can also build in some tolerances and say if the azimuth varies more than 3 or 4 degrees from the azimuth, or a certain amount of degrees from the planned borehole path inclination, it should flag you on that data point so that you can scrutinize it further. And so, what are some of the practical do's and don'ts at the drill rig that I've observed over the years and learned from working with master drilling, and then also with Index, is one thing is always make sure that your running gear sits snug in your drill rod. In other words, and I have a bit of a exaggerated example here of a very small survey tool that is planned to go into a very wide diameter borehole. So the running gear actually ensures that this tool will sit exactly in the center of that borehole when it's taking the survey. If your rods are bent, or it has any shoulders on, or for example tools going through the front of the drill string, if that tool doesn't land exactly and how can I say, vertically and aligned with the drill string, those small little shifts can those half a degree or third of a degree shift in the actual reading can accumulate over time and actually cause a larger error. With survey tools, especially gyro tools, any vibration is your enemy. So the drill rig should always be switched off, and only the wind should be running. So not even a pump or nothing else should be running on the drill. The water should not be moving or being pumped. So nothing should be moving. Vibration is your enemy. try and minimize vibration as much as possible when taking any surveys. If you're doing a precise gyro survey, surveys, you should clamp the wire line. In other words, make sure that that tool is not moving or vibrating. Even on a windy day, the force of the wind moving on that wire line can sometimes affect the survey, because the survey tools are so sensitive. So clamp the wire line in whichever way you can. If you have a casing sticking out, you know, just clamp it to the side of the casing, or just move it to the side and tie it down if you've got a spanner on site. Even do that, so that vibration isn't induced on that wire line running from the casing up to the wire line spool. Avoid stopping the wire line abruptly. So when you're surveying, smooth is better. The operator should hoist and lower as smoothly as possible. Don't do any jerky movements on the wire line. This is also important for doing continuous wire line when you pulling up, going down or up in the drill rod at a constant speed and doing continuous surveying, but also when you lower the tool to actually avoid any unnecessary damage. The running gear does have bump subs on and to prevent any shock to the tool, but still, if you handle the tool with as much as possible care, then it will give you the best readings. When you're on site and you store, and the drillers or the service providers store the tools, store it in a cool place if possible. This is especially applicable to drillers in higher temperature areas, like I used to work in the Western Sahara, and there it can get up to 48 degrees Celsius. So the temperature affects the performance of the tool, and that's all to do with that background noise and increasing that angular random walk and bias stability of the tool. So store it in its case firstly, and store it in the shade. So it will reflect on that tool temperature reading, and your accuracy and your precision will be compromised if the tool is not operated within its optimal temperature range. So with magnetic tools, when we say all forms of magnetic interference can influence the performance of the survey, we mean it. The machine, the drill rods, even the geology. And remember, it's not just a magnetite that's magnetic. You get other magnetic minerals like magnetic peritite, goethite. So you really need to consider that factor when using a magnetic tool. And always remember, use the correct aluminium rod extension. That tool needs to stick out at the bottom of the drill rod. It needs to be away from the steel. So use the correct aluminium extension so that the tool sticks out enough at the bottom to not be influenced by the drill string. When you're doing a multi-shot or those stationary surveys where you have to stop and you have to wait for the reading with the tablet, give the gyro or the survey tool some time to settle. Let it go down, give it 20-30 seconds to just settle, and you know, maybe it could be still in the water, leading the water table, and it needs a little bit of time to actually move down and settle at its final position. So yeah, just give it even a minute or so before initiating the survey. That extra minute is going to help you a lot in the long run and give you better data accuracy. Then a very important one you must touch on, you must ask your drillers or your service providers on site, how do they not calibrate, but firstly confidence check their tools? How regularly do they do it? Do they measure something of a known orientation? In other words, do they have some or other jig on site that they know the inclination and the azimuth of? And do they regularly put their tools in there to see if they actually get close enough within the tool spec to that accuracy check? It's not something complicated that needs to be done. Some sites with a neat piece of a cement block and a PVC pipe, where once again the tool sits snug in, can be used to confidence check that tools, and that just gives you extra, like it says, confidence in that tool's performance on a weekly basis or a monthly basis, or whichever you feel is good to check them. And then another aspect it's not a confidence check, but the tools need to be fully calibrated at a certain date. In other words, some tools every 2 years, some tools longer than that, some of the newer tools almost like 3-4 years, but you need to get that calibration. You need to check that calibration from the OEM or the original equipment manufacturer, and you need that assurance. So if your service provider or your driller is using tools on site, make sure those tools are calibrated and still within the calibration period. Then another one other thing a lot of us, or I never think about, is if you are using a winch. In other words, if you're using the wire line or some other line moving down like here, you need to also calibrate these depth encoders. In other words, this thing's got a little spool in this depth encoder, and as it spools, it knows a known length of each spool, and it will tell you the tool is now at 100 meters, for example, or 101. But how can you confidently say that tool is at 100 or 101 meters? These depth encoders also need to be calibrated. So you can ask for the calibration on these as well. When last was it calibrated? Is it still in spec? Because in the end of the day, it won't matter how accurate your survey is in terms of inclination and azimuth if your tool is not at the correct depth. This gadget tells you how deep the tool is. Especially if you're a rate gyro or reference gyro. On a north-seeking gyro, it has a absolute value in space, but it's good to always check that these tools are always also calibrated to ensure that you're actually at the correct depth that you think you are. And yeah, with that, I'd like to say, just remember, it doesn't help you only know what it is and not exactly where it is. Then you are still treasure hunting. So thank you. And is there any questions?
Thanks for Werner. Okay, well, you've got Werner's email address if you have any questions that you think about later. We're just going to take a 5-minute break, and then we will come back for the last of our session, which is going to talk to us about drill hole sampling, because we learned now how to drill. We've learned a fair amount about drilling and logging and surveying. Now, how do you take your samples? Which is probably the whole reason why you're doing all of this drilling. So we'll start with that at 1:15. So rush off and get a cup of coffee.
Hi, Tanya, I'm here. Can I start sharing my screen?
Yes, please, if you will, Keith.
Okay, can you see my screen?
Yes, it has come through and it's in presentation mode. It's perfect. Just leave it there for 2 minutes and then we'll start.
Okay, cool.
Keith, will you be in a position to send us a PDF of your presentation afterwards for distribution to the delegates?
Can I do it sorry, can I do it tomorrow morning?
Yes, yes. I don't mean right now. And once you finish tomorrow morning is fine.
If I convert it to PDF, I use a lot of layers. So I have to take those out so that, you'll often have an arrow covering the picture because I use a sort of an artistic approach to my PowerPoint presentations. So an arrow will suddenly appear during the talk to emphasize a point. So I just need to take those out. It takes a bit of time. So the actual stanza, nothing is hidden by arrows and pointers and things like that I use to emphasize certain points in the talk. So I need to do it by tomorrow.
Sure, no, that'd be perfect. Thank you.
Okay. Do you want me to turn my video on?
You can if you want.
I find it distractive. That's the only question I need to ask. But if you want me to talk with the video on, I'm quite happy to do it.
I'll put it this way, we're suffering from bandwidth. So if you're happy to without it,
I'm quite happy to do that. I'm quite happy to do it. I know the problem. I've dealt with it. See, I'm sitting in a house with nearly 400 meg of fiber. So for me, it's difficult to understand what goes out on mining properties. We have just got ordinary wireless. So no, I'm quite happy to turn it off because I've got a lot of power here. And I don't know how much this presentation actually puts out.
Okay, no, that's perfect.
Okay.
Hey, everybody. Our last presenter today is Keith Kenyon, who is a geochemical consultant. He originally started work with Tsumeb Corporation back in '68. He spent 25 years at the Anglo-American Research Laboratories, eventually becoming head of the Gold Research Group. Then he transferred to Anglo-American Gold and Uranium Division in the mid-90s and became global manager of geochemistry at Anglo Gold Ashanti. He retired then in 2006 to become the technical and new business manager at Urimum Inc. And he has worked as a geochemical consultant since 2007. And his experience is extremely wide-ranging, different technologies, different commodities, and different geological environments. So Keith, we look forward to hearing about your principles of sampling in drilling.
Okay, thank you, Tanya. Good afternoon, everybody. This talk is quite an extensive one. I don't know even if I'll finish it. Put a lot of stuff into it. It's actually part of a 5-day training course in geochemistry. It covers everything. So this is a portion that I extracted out from it. And what we're going to look at is the principles of sampling and exploration and resource drilling. The emphasis on that day has been on drilling, but you'll find a lot of my slides for illustrative purposes show other kinds of sampling in the mining industry because it's often clearer to see it in the mining environment than it is in the drilling, and not only that, it also shows the scope of sampling in mining. It covers the whole of mining, and it doesn't matter if it's drilling or sampling in a plant. The principles are exactly the same. They apply right the way across. If a chemical analysis is going to be done in it, the approach that I use is the same right the way across. The thing is, you've got to understand that sample, and this is what this is about. And requires meticulous, and I stress this word meticulous, and there's a word missing here, discipline and perceptive sampling, and you've got to minimize the sampling error. We're going to talk about the sampling error. It's a theoretical concept, but a very important concept. I use it in the background of my mind when I'm working, because I'm a practical operator. All my stuff is practical sampling, and in various environments, and my environments include a very wide range of sampling types. So what we're doing is essentially practical sampling for geochemical exploration and resource estimation. The component that's always included in this is a chemical assay or chemical analysis, and that is part of the sampling process. You cannot separate it, and we'll talk about that. So it's an integrated approach. Excuse me a second, I just need to change my view here. Okay, there you go. Sorry about that. Tanya's already given your background. That's what I look like. I don't want to turn my video on because I gather a lot of you guys are on a narrow bandwidth. But that's my background. I've had a considerable background. I worked in base metals, I worked in gold, I worked in uranium, and I have never worked as a diamond geologist, but I worked with the diamond geologists in the old days in Anglo-American. De Beers and Anglo were part of the same business, and I learned a lot of diamond about how diamond sampling is done, and many of the concepts are the same as with base metals and gold. And what I'm involved in now is something quite interesting. I'm actually developing projects looking for commodities that reduce fossil fuel consumption. I think that's mainly stuff, elements that go into batteries, things like rare earths, lithium, looking for those commodities. And there's also another commodity that we're looking for that's related to many of the rocks I've worked in the past, namely greenstone belts, and that is looking for natural hydrogen, which can be actually tapped and brought into production, very similar to oil. I mean, it's a concept I'm working with geologists from the British oil industry, and we started this project, and hopefully it's going to go very well. But it's part of the breadth of experience I have, and that's why I've been brought into this project. But this is what we're going to focus on today. Sampling and chemical analysis for reverse circulation drilling, for diamond drilling as core drilling, and grade control drilling as blast hole sampling. Those are the three areas we're going to focus most on today. It's going to include components of sample management. I'll talk about that, but not much. But laboratories and chemical analysis, again, I can't go into too much there because it'll take 2 days. So it's a specialized business in geochemistry, but I'm going to give you some of the background in terms of how we select laboratories and how we do things at the end. Quality control also forms an important part of this, and that would be another course on its own. And what I'm going to do is I'm just going to refer to it during this presentation because it requires, again, a great deal of understanding of the concepts involved. And it's just important to know that it is part of the discipline of what we do. And the final thing is something that I do as part of the money I make, and I teach geologists how to do this, but I teach it on the rigs and in the sample preparation areas where they split the core or pre-treat RC material. I teach them how to audit their own work. Auditing is a discipline. It requires either an independent person or you yourself to repeatedly and persistently look at what you're doing and document it. If you do it once a week, once a month, that's very good. But your laboratories as well need to be audited regularly. And let me show you, the current commercial laboratories that we use are really good. Improvement in laboratory quality over the last 25 years has been remarkable, but they still have to be audited. And that is formally audited. In other words, a document is put onto the company records that laboratory was audited at such and such a date. Were there any queries about anything in the future when someone is doing a competent person's report or something like that, it can be immediately shown that that laboratory was checked, or checked by somebody and repeatedly checked, or that process was checked, or the drill rig was checked. And it's quite important in drilling because the rig moves and the environment where the rig was has gone. All you have left is the core, and the core is often sampled, often it's tampered with. So one needs as much record keeping as you possibly can through this entire process, and it's discipline. I cannot underemphasize the concept of discipline and rigor in this environment. Some of it looks darn tedious, some of it looks time consuming, but if you don't do it, let me show you, it devalues your project. There's no doubt about that. What we won't be discussing today is trench sampling, channel sampling, stream sediment sampling, soil sampling, underground sampling. We won't discuss it in any detail. The only thing is I'll refer to particularly underground sampling from time to time because it's an environment where we can actually see what happens when we omit things. And I'm using them as by means of examples rather than actual training outside the area of drilling. But let us go back to where I started. When I started this work way back. There were things that worried me about I was mainly involved in the South African gold mining industry, and what worried me is that it seemed to have a history of lack of care about why the laboratories were run and why samples were taken. And the interesting thing was, when I was chief geochemist for Anglo Gold, they were using the drilling for the deep drilling operation. The protocol for that was written in 1951. I rewrote them, but already we started to move out of the industry and deep level exploration had stopped. That means a lot of the deep exploration that was done was actually done without an accurate protocol. And further, the laboratories were a disaster. You don't see this kind of equipment in a modern laboratory, but if you look at that picture very carefully, you see the amount of dust lying around on the floor everywhere. And those machines, those are pulverizing machines, are not fit for purpose. The contamination level in these laboratories was ridiculous. And in fact, this laboratory, I submitted 33 highly siliceous dolomitic samples there. We know they were barren. They were sent to a laboratory in Australia where I asked them to analyze them as low-grade samples, in other words, in the parts per billion range. And then I asked one South African laboratory to analyze them in the parts per million range, and this laboratory to do the same analyses. The assays that came back from Australia were not a single sample contained any detectable gold. The South African laboratory, which is very close to the old Crown Mines mining dumps, and this was done 20 years ago, near the South African tailings dams around Soweto and those places in Johannesburg, came back with the odd slight low-grade value, and I mean by low-grade 0.1 or 0.2 gram a ton. But remember, I was comparing this to the Australian laboratory, which is measuring in parts per billion. The point is, the South African laboratory, the maximum grade from this laboratory you're seeing a picture of, was 105 grams a ton, and the mean was 9 grams a ton. That shows how badly the laboratory was contaminated. That means the run-of-mine material was not being assayed accurately. And the reason for this high level of contamination was that they were assaying both plant materials and underground grade materials in the same place. You can't do that. And these are things that are part of the auditing process. I go and check in laboratories how they're separating materials, how they're preparing materials, and how the samples are handled. And that sample that is in the laboratory is part of a holistic process that starts at the diamond rig, or at the RC rig, or at the blast hole rig. And assay and chemical analysis should not be uncoupled from the sampling. It's part of the same process. Because that sample that you take at the rig is a piece of half core, for instance, goes through various stages of crushing and pulverizing, and the size of the sample diminishes until it goes into the instrument that does the analysis. And the instrument that does the analysis uses a couple of drops of the material that contains the artifact of your ore. So you can imagine you take a 50 kilogram or 70 kilogram RC sample, and you reduce it in size, and reduce it in size, and reduce it in size, till a couple of drops are sent into the nebulizer of the machine that's analyzing it today. And the machines that we use today, the instruments, these ICP, inductively coupled plasma instruments, either the mass spectrometer or optical emission spectrograph, they analyze an enormously small amount of material. But in that process, the material that has just arrived at the machine is in a flask, and that's only 100 cc's of liquid into which your rock sample is dissolved, and that's only 0.1 of a gram. So your whole ore body is actually being represented by 0.1 of a gram of sample taken many, many times across the ore body. So you've got to make sure that the process of reducing that sample that you collect on the rig and handing it to an instrument to analyze is consistent all the way across the process. So you do not bias or damage the sample in any way that causes a bias. And we'll get to that in a while. And that, therefore, that requires an effective and procedure for auditing the course of assay and sampling process from site to database, and that is integrated. So the geologist is doing an audit on his rigs. He's documenting what is done. You mustn't just say, I went to the rigs this morning, and they're taking the samples out of the core barrel in the way we told them to. That's not the way it's done. You actually check it and you have a tick list. Checklist. It has to be done properly and documented. It sounds like it's time consuming, but if you don't do it, I can assure you there will be questions asked, and a good independent geologist who's coming in to write a competent person's report. If he's good, he'll ask for those things. And so therefore, it's inclusive and holistic data collection. And this is so important that you have to be able to conceptualize the entire process of taking a sample and getting a chemical analysis and putting it in a database. And when it's used by someone in 5 years' time or whenever, it means something and can be trusted and can be relied on. I can assure you, I've been in this game for 55 years. And in that time, I've gone on to more projects than I can ever count where there's been massive oversight. And to repair that oversight can be extremely costly. I can promise you that. And therefore, what I try to do with many big projects, particularly when you're going onto a massive resource drilling program, I ask at the beginning of projects, if I'm employed as a consultant, if the company is prepared to pay for the writing of protocol documents. I've got copies of these things. I've used them before. There's a protocol document for RC drilling and so on. There's a protocol document for putting in the quality control materials and using quality control materials. There's a quality control document for how to split and divide the core. Each one of these are documents. They are there to ensure that when one geologist moves off the project and the next one takes his place, that they both do and work in similar fashions. And you can often see when a bias comes into a project, you can often see the geologist changed, or in the lab analyst has changed. And that's because people work in different ways. And the aim here is to try and make sure that people may work in similar fashion and work to a set of rules. And where does this come from? The mining codes demand that exploration results, mineral resources and ore reserves are reported. And they're reported properly. And what I've got here are two diagrams which are exactly the same. One is taken out of the JOC code, the 2012 edition. That's the Australian mining code. And the other one is taken from the SAMREC mining code, which is published in 2016. If you look at those two diagrams, they're absolutely the same. And now what these are graphs. The left hand or the y-axis of that graph shows the increasing level of geological knowledge downwards as you go down. I just don't know to get it down. As you go down towards the origin. So in other words, in this direction, you're having an increased level of geoscientific or geological knowledge. In this direction is everything else that would go into mining. That's consideration of mining, the metallurgical, can all be treated, infrastructural, the economic, the marketing, the legal, environmental, everything else that goes into the mining operation is considered in this direction, because this is the reserve. This is what you're going to mine. And this is what geologists do. Geologists deal with resources. And you start off with exploration results, you know very little about them, you don't even know how much you've got there. And as you do more and more drilling, and as you do more and more sampling, so you go into a better understanding of your ore body. And this is based on how close your boreholes are, and how accurately you're measuring everything, how you're collecting everything, how you're sampling everything. And as your understanding increases, so the geological knowledge increases. And as this understanding increases, so it becomes more and more possible to move things across into a mining mineral reserve. And what often happens on projects today, when I go out to them, and I'm not even a metallurgist, but I've worked with them for over the years, the earlier you can get samples to metallurgists so they can understand that ore has to be treated on a new project, the better it is. It's no use right at the end of the project. And I know one project in South Africa that was delayed for years because they never did the metallurgical test work early enough. And the ore was complicated. Those things should be found out early. Once you get your third or fourth holding, you can start submitting samples for metallurgical work. And this is where you, again, move things across. But to do that, you have to sample the borehole properly, and you have to determine what part of that borehole can be used for sampling, and what part of that borehole can be used for metallurgical work, because you always have to have a remnant of sample material left over. And I have been on projects where the core has been sampled so badly because they divided it up between metallurgy, between resource drilling, and what they had to keep is record that they were sampling quarter of drill core. You cannot sample quarter of drill core for anything. Half of drill core has enough limitations without halving
the problems that you have, or doubling the problems you have by halving the core, by quartering the core. These are the things that we have to go into, and I'll talk about them more in detail. That the material that is submitted for sample for assay must be of the same type of sample, the same method of sampling across an entire project. And if the changes are made, then these have to be documented. Otherwise, these type of resource and mineral resource and reserve type reports have got flaws in them. So everywhere where the change is made, or to sampling or to assay, these need to be recorded. I've got data, tons of data where people couldn't understand things because they changed something in the process, or they weren't consistent in the way they sampled. And remember that all of these resource statements and competent persons reports are all based on the fundamental, one fundamental thing, that's sampling and chemical analysis. And what I'm talking about now, when people talk about the geochemistry of the core, what they mean is what that core is worth. And you're using a process of data acquisition, data management to make sure that that data that you present, so that the resource statement can be written up and is as accurate as possible. That that process follows the same set of protocols over and over again. And there are 5 basic components that I have in my idea of how I do things. There's the sampling, which you see as red, because that's what we're talking about today. There's the chemical analysis. There's a quality control that applies to both the quality control of the sampling and the quality control of the chemical analysis. Quality control of sampling is making sure that you do everything as accurately as possible, and where you can measure, check measurements and things like that, you do it. The quality control and chemical analysis means you add things like standards and blanks, or standards or certified reference materials, blanks, and certain kinds of duplicates. And again, all these things have to be documented. What kind of duplicate is required for that project? Is it a coarse duplicate, a pulp duplicate, or is it a combination of both? What check samples you do at other laboratories? All of that is part of the sampling process. And of course, then there's data management and databases and interpretation, which is the final part of all this work. Now, this is a diagram that I use to explain the sampling and chemical analysis process across the entire the entire sequence, from sampling at the drill rig to the chemical analysis. And what I've done, this diagram has got an upper half and a lower half. The upper half is the bit that happens in the field, which is sampling, logging and labeling, sample reduction, splitting, and transfer the samples to the laboratory. Now, this bit here, I can make as big as this and also extend it, but I don't do it because most geologists know this environment and have a fair idea what it's about. But this is the environment that you don't see, where your sample is now passing through a laboratory. Now, what point I want to make out here is you've got a drill rig here, and the word sampling appears. It's sample reduction, transport of samples to the laboratory. Now they're in the laboratory, sample receiving, sample preparation. Sample is crushed, it is split, and is pulverized and weighed, and all the way to chemical analysis. The point is, it's still a sample. When it starts at your rig and ends there, it's still your sample. And you've got tens of thousands of them going through a laboratory, and you want it all to be the same, and you want it to be as reliable an indication of what you're measuring in the ground as possible. And that is why you will find that when you separate these two different entities, you'll find that there's a gap. And people come in, they say, have you done this? And I say, I don't know, because I don't know what goes on in the laboratory. You do need to know what goes on in the laboratory. It's very important. And what I've done, and I've done a lot of this in South America, where they're very receptive to it. We've trained the geologists to actually audit the laboratory. We've had incidents where the geologist, one geologist actually got violent with the laboratory manager. We don't encourage that. We do expect the geologists to be firm with the laboratories. The laboratories know what they're about. They're analyzing tens of thousands of samples a day. They have got lots of clients. You're one of them. You just must make sure that whatever work they do on your samples is the best you can get. So, what comes out of this? The most important part of this is this arrow. From the top, which is sampling the rig, to where you do the assay, in the laboratory, which is down here, from there to there, there's a massive reduction in the amount of sample material or the size of your sample. Okay, there we go. So there's a significant reduction in sample mass from the beginning to the end, but there's also a cumulative loss of sample to the process environment. And what I mean by process environment is that during the entire process, you're doing things to your sample, and the laboratory is doing things to your sample which reduce its mass, and it's this loss of material on crushing, on riffle splitting, on cutting the core, bits breaking off the core, bits falling off at the rig, that you don't want to happen. You do not want the amount of material you take out of the ground reduced by any significant amount. It's impossible to stop it happening, but you've got to limit it. And this is again why we have this discipline. Because the moment you start losing sample, you generally find that the part that you're losing is either lighter or heavier than the ore. So what you do, you either enrich or impoverish your sample or deplete your sample, your ore in the sample. So it's not an accurate reflection of what's in the ground. It's either overread or it's underread, because you've actually lost sample in the process. And this has got to be avoided. So these are examples. These are examples. I can promise you, I can go into my database and I'll produce another 200 or 300 photographs. And you'll find today that a large number of my photographs are mine. I don't put them on the internet. These are photographs that I've taken while working. And these are examples of sample loss during sampling. The effect is cumulative across the process. And don't forget, as your sample is being reduced in size, a greater and greater proportion of the sample may be lost. And these are examples. This material here. This is a laboratory. This photograph was taken in a laboratory in Tucson, in Arizona. It was taken about 15 years ago. This was copper ore. And this is in the sample receiving area of a laboratory. Now, bear in mind, there's a problem here. This is one client. Your samples come in and they've got gold in them, and a lot of copper ore has also got gold in it. This guy's samples are going to contaminate your samples. That is why one of the reasons why he ordered the laboratory. Those bags were not suitable for that kind of ore. They were leaking material all over the place, and they contaminated and dirtied the laboratory. That is what is, in my view, one of the biggest sins you could ever perpetrate in this process of geochemistry, and that is contaminating the laboratory. And that is why when I showed you that very first picture, that had all that where a gold mine laboratory was so contaminated that you couldn't do an assay at it. That is what causes the problems. Now, these are commercial laboratories. They have a very, very rigorous approach to keeping the laboratory clean. But it doesn't mean that contamination doesn't take place. I had samples in Elko, Nevada, badly contaminated because people were submitting mine grade, in other words, concentrate samples, gold concentrated samples, to a laboratory doing exploration analyses, and they were contaminating the laboratory. This kind of carelessness is encountered all over the place, and it's particularly prevalent here in Africa with many of the laboratories where material is submitted that is coming out of a plant and is mixed with material that's been used for resource drilling. That cannot happen. The next picture, the top right-hand corner, that was taken a short while ago in a laboratory in Zimbabwe. That is a tray on a pulverizing, next to the pulverizing machine that's used to turn your sample into bug dust, so it's homogenized. And that material that's lying there was swept away. That is sample loss. In other words, it fell off the sample while they were pulverizing. That's not permissible. Nothing may be lost. That was a black mark in the name of that laboratory. You do not do that. The next one on the bottom right hand corner, this one over here, This one here is a drill rig in the Central African Republic. We were drilling for uranium. And this is an RC rig. But the drilling environment was nothing but mud. As you can see the stuff. Now, this picture is interesting. It was taken 2 hours after that rig was put in. And those guys arrived there, that nice clean blue overalls. Look what they look like after 2 hours. You can imagine what it looks like after a day or two working on that rig. There's mud everywhere. But that fine slurry, that's these guys sitting down in, that is sample loss. That material should never have been lost. That's got ore in it. We do not know what the ratio is of uranium in that muddy material to the uranium, the coarser material that's in the bag underneath the cyclone. They were actually, if it was muddy and liquid like that, they just let it go away. You couldn't do that. And we had to ultimately get them to sample into large plastic drums so that no material is lost. That is the extremes that you have to go to. With that meter that you take out the ground on an RC rig, that sample may not be reduced by any means other than a controlled splitting method. You can't reduce it by, which is fine, I'll throw it away and keep the cool stuff. That's not on. The same project, next, they had to dry all this material. So they dried it over open fires in these metal, you see in the middle diagram, in these metal containers. But you notice the size of those containers got sputter in them. The material is boiling. You can see the closest one to the camera, there's a little bubble in it. Well, that bubble pops and shoots material out all over the place. That had to be stopped. You can't have sputtering. It had to be dried so there was no loss. So we actually put in proper drying ovens with gas dryers, and we could actually control it. So every sample was closed up and not taken up to temperatures as high as it was slower, but that's the only way they could do it. The bottom right-hand picture that looks where the drill is standing in a cloud of dust, that's an RC rig. So they're drilling for gold in Alaska. That there are so many mistakes in that photograph from my point of view, from a sampling point of view, that I like to use it. First of all, this here, this is a riffle splitter. I don't know if anybody's familiar with a riffle splitter, but the way they design is that you split. It consists of shoots, and half the shoots come towards us, and the other half of the shoots go away from us. And so they divide the sample in half, and again in the half. That's done. There are three splitters, and one on top of each other. But a couple of things are wrong. First of all, this is a cyclone on the RC rig. That cyclone is dropping samples just in the middle of the river splitter. That's not the way to do it. A river splitter is as wide as that. So the whole sample must equally cover the whole width. You don't just shoot it through the middle. So that was the first thing that was wrong. The second thing that was wrong was an excessive amount of dust around the machine. Just look at the dust lying on the ground. This is wrong because you're losing samples, and of course it's a health hazard as well. Found a similar project with a project called Veduga up in Siberia, in Russia. This is before they went, when it was, we were still looking at mining there. It's not easy to work in Russia. And we found exactly the same problem. Using only the middle of a riffle splitter to split. And all those projects had been going for weeks or months. And so that tons of material where the sampling was dubious. No, it doesn't only apply to how you sample, but it also applies to how you sample. On the left here, we have the thing that has given me, a machine that has given me, since it was developed nearly 15, 20 years ago, is a portable X-ray fluorescence machine. I'm actually grateful for this to this instrument. It's given me a lot of work because it's never used appropriately at all by anybody. Most geologists are not analysts, and they think they can do their own analysis to save money. I would say that these instruments have been responsible for more ore bodies going undetected than just about anything I can think of. And it's not only my view. The guy, he just retired, who was CEO of SGS Minerals Laboratories, he agreed with me. He said also the laboratories in Canada were getting a lot of work because people that come onto projects who require work to be redone because the instruments were being used inappropriately. And I'll go as to why. All three of these instruments are X-ray fluorescence. This is the portable X-ray instrument. There it is there. This is it being used correctly. It's on a sampling, in other words, a sample is put inside that little box. It's on a sampling device. A lot of guys think I can just point this at the core. There are two things I have a problem with that. One, this is an X-ray source. I know it's only full watts, but you get exposed to full watts of X-ray for a couple of weeks, you are going to get some blood disease later in life. And nobody takes any precautions using machines. They are dangerous. X-rays are dangerous. Because you can't see them doesn't mean they're not dangerous. With the low wattage, it doesn't mean it's not dangerous. It's extremely low wattage X-rays. But still, you don't want to repeatedly be exposed to these things. And someone like myself, last night or the night before last, I was at Heathrow Airport, where I was subjected to a full body search because I have artificial knees. Both my knees are made of steel. So when I walk through security, I set the alarm off. Now I have to be X-rayed. That's again a very low dose of X-rays. But you have that, plus working with these machines all your life. And bear in mind, I've worked with all these other machines. Also, I'm very careful as to how much X-ray exposure I get because of the amount of X-rays I've had. But the point I'm trying to make is that I believe that these machines are not handled carefully enough. They're used in the mining area with lack of due consideration. I actually do not believe a lot of what the purveyors of these machines will tell you, because the problem is this bit here. Now, young geologists particularly do not know what this symbol is. They should do it, and everybody in the mining industry should know what it is. LLD stands for lower level of detection. That is the lowest level of sensitivity instrument. That means that instrument is detecting at that level. It doesn't mean that the data as it approaches that low level is good. As you approach low level of detection, data becomes noisy. So if I tell you that something has a low level of detection of 10 to 20 parts per million, actually has a useful level of detection. That's the way you can actually use it. It's generally about double that. So that lower level of detection on most instruments will be probably for a hand-held XRF in copper. I know it's 35. I don't give a damn what the manufacturers tell me. It's 35 parts per million. You cannot use it for soil samples, and you can only use it for a scanner on core. And then if you're going to use it as a scanner on core, you have a protocol document which determines how that sample of core is taken with that machine. And the reason I'm showing this is that what I am trying to get to is the concept of homogenization of a sample. And we're going to talk about that. A homogenized sample is one that when it's crushed and pulverized and sent to the laboratory, that you take two aliquots out of it and you assay them. And everything else is equal. They should be the same. A coarse sample will not produce repetitive analysis. And when we submit coarse duplicates from the rigs to laboratories, we don't get the same reproducibility as you do with a fine minus 75 micron sample, which is homogenized. So if you look at this, the nature of these samples, this is a bagger sample. This is actually taken out of and this is the other problem we have. They just took a scoop out of the RC material and did this analysis. You can't take a scoop. You actually got to go through the same sample preparation for this cheaper approach to chemical analysis as you do for these. Otherwise, it's not representative. Now, this is a best XRF machine. It's a highly accurate machine. This is the instrument we use in industry. It's WDS, that's wavelength dispersive XRF. This is nearly as good. This is energy dispersive XRF. The nice thing about energy dispersive XRF is that it can give you a wider range of elements without interference, whereas there's a lot of interference with this one. But first of all, the current is so high that if you want to do accurate analysis, is that you could compare. This is a 4-watt instrument. This is a 9 to 40 kilowatt. You can imagine how powerful that's X-ray. You put your hand in the way of that machine, you're going to know all about it. You're going to get a nasty burn. Fortunately, the safety standards on these machines are terrific. You're not going to get the amount of X-ray radiation that leaks out of these things is negligible. The amount of radiation that comes out the nose of that thing, if you point it at someone, is enough to give you a kick. And this is the WD. This laboratory. This is very good in field laboratories, in the hands of an expert XRF analyst, not in the hands of, in the one case, metallurgical technician. These things must be used by people who know how to use them. As you can see, they have got very advanced software with them. But the beauty of this machine is that the sample preparation does not need to be pressed into a pressed powder briquette. This is your sample. It's fine, but this is a briquette. This is a sample. It's pressed dry using a press that has the pressure is 40 tons per square inch. It's a monstrous pressure to get these. These are pressed powder briquettes. The net result is you get highly reproducible. This, with things like for uranium and elements like that and lithium, it's fantastic, this instrument. Titanium, great. But whereas this instrument is more of is more of an instrument used in plants where you want a accurate analysis. It is very similar to this in concept, but it's much more accurate. Again, the lower level detection is 2 to 5 ppm, depending on the element. But the point I'm trying to make here is that the sample that you're producing on the rig has to be homogeneous. This is poorly homogenized. This is highly homogenized, and this is super high. This is super high. This is why I say it's also highly. This and this are both pulse. The difference between this is best powder briquetting creates a dimension of flatness here, which X-rays respond to very easily. The beauty of XRF is the sample is not destroyed. All the other techniques that we use or routine in laboratories, the sample is destroyed both by fusion in the case of precious metals, as platinum, gold, or is dissolved in acids. And so you never get your sample back, and this is what we have here. These are two of the instruments. There's another one which is coming into its own and has been coming into its own for the last 10 years. The atomic absorption we tend to do is not really a multi-element technique. You can do 1 or 2 or 3 elements in one go, and is reasonably accurate, but its use is diminishing. Before the ICP mass spectrometers in the mid-90s were being used, we could measure down to 1 part per billion, not 1 part per million. 1 part per million is 1 gram a ton. 1 part per billion is 1,000th of a gram per ton. We could measure these instruments, we could measure 1 part per billion, but the technique was highly specialized and requires special techniques, and the instrument had to be fitted with a device called a graphite furnace. That's where is a specialized burning device in there, so the instrument could detect the flame for gold more readily. But this instrument has been more or less replaced for the lower levels. This is optical emission spectrograph and the optical emission mass spectrograph, which is very sensitive. And although in geology we don't do it, people like archaeologists who want to really measure small amounts of material, much smaller than we do, they can go down to parts per trillion. In our case, it's not necessary to go to that low level. But all of these techniques require the sample to be broken up in some way, either by direct digestion, as in the case of most base metals, or by fusion, as in the case of gold and platinum, where you actually do an assay and the material is extracted using something like lead to extract the gold from the rock, and then the lead itself is removed, and the remaining little silver prill, because I use silver as a co-collector, is assayed. And that little prill about the size of a pinhead that comes out of here, when you finally finish this process, is dissolved in acid. And then that is then put into these instruments. But the point is that sample at this stage is very small, and it is most homogeneous. Okay. And of course, now the gold assay, we have this problem. We're going to go into it now, but I'm showing this, I'm putting this in now. This is the latest technique of gold assay, photon assay using XRF, but it's a whole different approach. And in this particular case, the sample is bigger and it's not broken up. And this is a very reliable technique of assay. The big commercial labs are offering it, but because I've not worked on gold much in the last couple of years, mainly been base metals, I have not been able to test this. Now, in my case, if I was chief geochemist like I was at Anglo Gold, I would have put in place a rigorous testing process to test this. I did it for all the multi-element techniques that we use now, and it's a lot of fun doing these things. You test this way, you take the sample and everything, and it requires you working on contemporary projects with a geologist. Now, I've gone through that as the preliminary part. Now let's look at the concept of the sample itself. And these are sampling maxims that I use. The first one is the one that's fundamental to all of what I'm talking about today. The quality of the sample dictates the quality of the analysis. How you take that sample on the rig, how you take that sample underground, how you take that sample, if it's a soil sample, a stream sediment sample, no matter what it is, it dictates the quality of analysis. So your method of sampling must be good, must be appropriate. Now, if collecting a sample that's not going to reflect what you've got down there, And it's no use selecting analytical techniques. It doesn't reflect what you want. You've got to get the techniques right from the beginning to the end. These together dictate the quality of the project and hence its value. If you can hand a project over for mining with all the confidence in the world because you did the job right, it's fantastic. You don't want to keep on going back and checking. In many cases, it takes a couple of years to bring, or many years, to bring a project to a mine. And if in that process, there were periods, long periods of time where either the geologists running the project or even individuals weren't doing their job properly, that has to be redone. And people often don't remember. It's a lot better now than it used to be because we've got databases and with all the meta files, we do have control, but you've got to make sure that the geologists that starts the project and the geologists that finish the project, because they're not going to be the same people, they're going to be promoted. These projects last many years, they're going to resign, new guys are going to come in, new ideas, that there's a certain amount of rigor and control over what's done, so there's consistency. And then other important thing, and we're going to talk about it, there's no such a thing as a perfect sample. The aim is to get as close to perfection as possible. That's what this discipline is about. Good sampling requires sustainable and consistent rigor and attention to detail. It really means a lot of work. And people say, oh, well, it's your personality that you do this kind of stuff. It's not my personality. I learned this from bitter experience. I'm going to show you in a while how I learned it, because I think that example is very important. And the mining industry that I work for, I don't think ever learned it. Because one of my beliefs is that the South African gold mining industry would still be going strong if they'd been disciplined. But it was production at all costs. And I don't believe they achieved as much in terms of production. In other words, how much value they got out of those operations as they should have. It was, I always call it spreadsheet geology that was being done on many of our gold mines. It was just the bottom corner of the spreadsheet was important. That's how many tons of rock came out the ground, not how much value came out the ground. And that brings me to the next point. Sampling areas are cumulative across the process. In other words, you start making a mess and you continue making a mess across the entire project, it just gets a big bias. And many of the cases, you cannot measure that bias because you're actually doing the same things wrong all the time. The process, so it's the process's own creation of the bias plus your, as a geologist, your lack of control. And one of the things I try, and this is generally geological managers and mining engineers and metallurgists, they think that the areas now we put a fudge factor in. Fudge factors do not correct for analytical errors and bias. They don't. Because the bias and analytical errors change over time as different people come in, as the ore changes, as the methods of sampling change, all those things that you change. So you've got to make sure that the actual measurement you make and the way you sample that measurement is the same across the entire process. More bad sampling corrects nay, I can promise you. And I've often asked, the number of meetings I've sat in where guys said, don't worry about it, it'll correct itself over time. Never does. I promise you. And when I think part of the problem is that happens here is that I use advanced statistical techniques to actually analyze these things, and I go into the detail of historical documents, and that's where my view of these things has happened. I've had the opportunity to look at what has happened to big projects over time, and in many cases, there is no correction factor that you could actually bring into actually accurately change everything so everything matches. It just doesn't work. The only thing that works is discipline and concentration on what you're doing. And this brings me to this point. I'm showing you this. And it's only part of a very big case history. I started as a young geologist. Good afternoon. I'm here again. Is everybody there? Okay.
Yes, Kit. Yes, Kit, we're there.
Okay, cool. Thank you. Okay, I'm just going to continue. We just to quickly recap. I've just been sort of giving an introduction of the sort of loose ends that we're going to tie together in a while of how we sample and where we sample. And it's quite important that we remember that there are a lot of components to this, and it's the discipline is the same across the entire industry, whether it be underground sampling, soil sampling, and drill sampling. But I want to go, this is a part of a very much bigger case history as to why I think like I do about this. And it shows how an industry actually could have suffered as a result of this. Way back, and this is 50 years ago, I was still a young man. I could actually run miles and do all kinds of interesting things and play rugby. I was given a project on one of the South African gold mines. There's an Oldwell Reefs number 5 shaft, which is closed down now. Someone had the imagination to suggest that they were losing gold on mining.
Could you please share your screen?
Please share my screen. Just hang on. Oh, I didn't notice that. Okay, now can you guys see my screen now? Right, I'm terribly sorry. Can you see my screen?
Yes, we can.
Now.
Okay, sorry. I will have moved these slides. I'll start again. There's all these concepts that have started when 50 years ago working on the Witwatersrand gold mines. When I was given a project to investigate the gold losses on mining, and the results were quite staggering. We discovered that between 5 and 35% of the gold grains were liberated on blasting. And it was worse on the carbon seam hosted reefs. Those are the reefs where the gold occurs in a thin carbon seam. It's about a millimeter to about 7-8 millimeters thick, mostly about 2 or 3. And that is where all the gold in these carbon seams occur. And at that stage, underground sampling in those early years showed that the gold was all over the mine face. It wasn't. And I'll show you in a while how we proved that. But the carbon seam reefs were where it was most prevalent. And it was very clear after I did my work that why this was happening. The carbon seams are very friable compared to the hard quartzitic conglomerate that is the host rock. And when they blasted, this stuff came out of the rock. And an interesting point about these carbon seam reefs, when they were drilling into those deep boreholes, those deep drilling boreholes, they used to drill through it. And because the cost of the hole was so high, they never drilled a drill pattern like we do today on the shallow ore bodies. They drill, intersect the reef, come back up, and then drill deflections. And up to 30, 35, can't remember exactly. I think it was 32. They brought it down after a couple of years. Deflections were cut. They go up the borehole, put a wedge in, and then drill out and intersect the reef again and intersect the reef again. But one of the things I noticed when I was actually working on that core was that many of the drill cores, the carbon seam was missing, but the core had been assayed. Because the core recovery protocol stated that the core loss had to be, was only discounted if there was core loss above a certain percentage. That wasn't the way it should be done. When I changed the protocol, it was that the carbon seam was missing. It's no use losing 5% of the core, or having all the core there, but the carbon seam is missing because that disappeared. And that only constituted less than 0.5%, if not less, even a small amount of the total core. So you ground that away on drilling, it was gone. And that meant that there was nobody there. And at that stage, no one clearly understood, because of the poor nature of underground sampling, again, sampling playing a role, that they thought the gold was all over the face. It wasn't. And I proved it. And it took a lot of proving, because mining engineers are notorious in not believing this kind of stuff. And what happened was the initial part of the project, we instituted a program sweeping the stopes and using protective barriers. So when they blasted, they didn't blow everything back into the stope and all the gold was lost, because everything is blown back into the stope. And one of the other interesting things I'll point to in a while was the amount of gold that was blown into the wood packs. Further investigation revealed that 1 to 5% of the gold was sitting in the cracks of the stope footwall as particular gold not recovered. In other words, when we swept it, we actually swept more back into the cracks in the footwall. The more broken the footwall was, the more gold was lost. And 5% of gold in a big a megaton ore body like these is a lot of gold. And then did more work, and it comes again with madness that I have about sampling, that the additional gold is lost between stope and plant, suggesting the total loss of gold on mining was between 8 and 10%. And over the years, therefore, reasons for the high mine call factor. Now, a mine call factor, those of you who don't know what it is if you have a mine and you send surveys down, you measure the size of stopes, and you've got geologists measuring how much ore there is and how many tons there are. So if you say at the end of the month, I've mined so many tons of rocks and I've called for so many ounces of gold to be mined, and you discover you only get 80% of the gold you predicted. Well, the mine call factor is 80. That was what it was 80. And that was 80% of what you called for was recovered. Okay, and that's called the mine call factor. Some of the mines, particularly Western Holdings in the Free State, they all had mine call factors of 65%. And that had the thickest carbon seam of all the mines I've ever worked on. And that's when we came to the conclusion that the carbon seam played a big role in contributing towards the gold losses. But I will argue that the illegal Zama success, these illegal underground miners in Johannesburg, their success is due to some of these factors and the amount of gold left behind. It's just that their mining costs are so much lower than a big mine. So for us to have recovered those gold losses would have been incredibly difficult. I'd love to go underground and work with these Zamas to see exactly what they're taking out and where they're mining. It'd be very interesting. Stand on a second. I just want to. Okay. Now all this work, let's go back to slide. All this work I spoke about over here was done with a petrographic microscope. There you can see a picture of that microscope. That's an expensive microscope. That's not one of those little ones you have at university. That's a Pucker research microscope. I actually own it. It's standing in my cupboard now. As a private consultant, I do microscope work, although I try and avoid it these days because the cost of making the thin sections is very high. But to do the study, we didn't use just a conventional microscope thin section. That's a piece of glass about 3 centimeters in length. This is a big thin section. That thin section you see is the ruler next to it is 750 or 7.5 centimeters. So it's a big slice of rock. And that is the carbon seam you see there in the bold reef gold ore. And that sample ran at 165 grams a ton. And the mine call factor on that particular mine was high. It was about 80, it was about 70, between 75 and 80. That's high. And all the gold occurs in that carbon seam. If you look at the bottom slide, this one where it says gold ore, the bottom left-hand slide, you see this is a microscope slide of some of that wall reef, and you'll see it consists of this dark grey material, which is uraninite, and the material in between is a carbon, and that is what breaks open on drilling and on mining, and the rest, this malleable stuff in between is gold. There's a whole lot of other stuff that came out of this work, which was of a more academic level, and we could show conclusively that this ore body is not a placer as everybody thinks it is, or a remobilized. It's something else. And we ultimately believed initially there was a thermal deposit rather than a placer, but I've since changed my views on that, but I'm not going to go into that. But again, it comes out of looking at material that you've sampled carefully. But this is nickel ore that we looked at in a similar fashion, and chrome ore. We actually tried to understand what the ore was as an ore entity, what that you're going to mine or drill. And this is what we did. To prove that the gold only occurs in the carbon seam, this is a schematic diagram of a face, mining face. From there to there is a mining width, which is about 110 centimeters. These little red lines across here are thin sections. They are the big thin sections. And this white patch in here is what we call the tombstone sample, because when they get people to actually carry these heavy pieces of rock out, we couldn't just use the underground grade control sampling. So these patches here represent what a grade control sample channel looked like. And this is the large tombstone samples, and we took thin sections all the way through these things. And looking at this, the only place we could find the gold was there, but they've got grade all over the face. And this is what it looked like. These are the measurements we took. This is the leader carbon seam, same sort of thing. We measured it. And this is what I've done. So I've got a background where I've actually looked at the ore in the sample. I then take this into the drilling environment and say, this is what I can visualize what it looks like. You've never seen it. Most geologists have never seen it in that fashion. That's how you sample it. So the causes of this mine pool factor. Now, that was 50 years ago. I worked in this. I was chief geochemist, Anglo Ashanti. I was working all over the world, so I couldn't do this project all the time, but it was something that held my fascination. And the biggest contributor of this mine pool factor was inadequate and unrepresentative sampling. In other words, the mine pool factor may have been higher or lower. They didn't know. The cumulative gold loss between the stope and the face and the plant, that was another big thing. So in other words, they were losing material on mining, and it was being lost. And I'll give you an example. We sampled the sludges, those deep shafts that go underground. We went to the bottom of those shafts and we took samples out there. We got higher grades in the stopes that they were mining where the operations were taking place. Then there was a gold loss on mining, gold loss in the support and back areas. Back in 1991, one of the gold mines, Anglo gold mines, had something like 120 tons, if I remember correctly, of wood chips as it come out of underground water, which they collected. Those were running at higher than mine grade ore. It's very interesting. They actually recovered the ore from those things. Another component was gold theft. Again, underground gold theft, you often saw examples of it, where you'd go into stope that had been sort of abandoned for a day or two. People hadn't worked in there, and places along the face, someone had taken a nail and scratched out the carbon seam. That, for a small worker, he can get himself a bit of gold out of there and a bit of money. And the other big one is shoddy tramming. This is sampling of underground ore. Inadequate better sampling. Ore was sent to waste dumps. But all of this related to a sampling problem. And this is what it looked like underground. This is a stope that hadn't been cleared properly, but each one of these bits of wood in some of the stopes had gold in them. And this is what the problem was. They were blasting the gold out into the back areas. So we then looked at this whole thing in terms of representativity and the sampling error. And this is a fundamental concept of what I've sort of been working towards in the first part of the presentation. This is a theoretical ore body, okay? This is a grid where drill holes are put in. The blue drill holes, this is mining from the surface, drilling from the surface, are those that have been drilled already, and the red ones are the planned holes. The reason I've done that is that you're gathering information during the drilling process, and you're slowly working out how your ore body is going to look. So at this stage, when these blue holes are drilled, you've already got some plan as to what occurs, but next week you'll have that area, and slowly this ore body shape will come in as a concept. It's a three-dimensional ore body. That's just a plan. It's a three-dimensional entity. And bear in mind, the reason I've done this is that this black inside this black line is the major part of the ore body. That's where the richest ore is, theoretically. And out here are the low-grade parts. So the question is where is this boundary between where there's no ore and there's ore? Again, that's related to sampling. So what do? You've got a whole lot of processes that involve sampling. Yes, blast hole sampling, there's diamond drill hole sampling, there's RC sampling, there's underground sampling. All these sampling methods are always treated in the same way. It's sent to the laboratory in a reduced form. Yeah, the amount of material that comes out of your blast hole is at least 80 kilograms. These are sampled in meters, so that whole meter there is sent to the laboratory. But only half of it goes to the laboratory in a bag. And the core is broken into pieces, so it fits in the bag. Here's RC material. In this particular case, that's in the yard outside ALS Chemics in Johannesburg. The client had sent the entire meter to the laboratory in a bag and asked the laboratory to split it, because he felt that they could split it more accurately than they could do in the rig. He did not have access to a decent splitting riffle splitters, and they are a problem getting hold of decent riffle splitters. They really are. Most of them aren't fit for purpose. And this is underground sampling. And the reason this one got put in is that I spent hours underground with the guys looking at the way the sample was taken. This hard rock is impossible to sample, but millions of underground samples have been taken by sampling teams consisting of men who got a very routine job in a very dangerous environment, and it's boring as hell. To expect him to consistently take a decent sample is hugely problematical. And I spent hours with these guys, and I can tell you, I never was satisfied with sampling. No matter how many theoretical pieces of paper were written on it, when you sit with these guys, the work is not, and I was doing it almost in disguise, as an underground cop, as it were. And it was not satisfactory, ever. But no matter how it's done, that always lands up in the laboratory in bags of sample size round about there or slightly smaller. ALS laboratories on their website have got a beautiful example of the entire floor of their sample receiving area laid out with client samples, and they're all of different sizes. But this is the bit that's sent to the laboratory. This material then goes through a whole process of crushing and pulverizing and digestion, and eventually 0.5 to 30 grams of that material that there is just digested in a bottle. And that bottle is a volumetric flask. It's very accurate. So you now use 4 acids, or you take it. You've got another process which is also very violent that may be used for gold and platinum, where you assay it and then it goes into that machine and it's assayed. So you're expecting whatever comes out of there to represent a point in space over there. It's costing a lot. And that is why I pitch this gospel of control. And the important thing is the sampling error. And this is the equation. I'm not going to go into the detail of this. This is a whole course on its own. How to relate this sampling error to reality. It is probably, in my view, is one of the most important equations that is around there. Because there are components of it which are really important. And there are aspects of it, and a lot of this is a book by Francois Petard on this, where he says this component, the highlighted green, the preparation error and the analytical error, are a low component. I disagree with him. He's never done a chemical analysis in his life. He understands the stats. I know how I spent hours again working and assaying with labs. The errors just from oversight alone are huge. So that's the equation laid out in pieces. So what I've got, you see here, is NE and FE and a GSE and all these different bits. The NE is a in situ nugget effect, and this is the equation for it. We're not going to go into detail. This is Guy's law. We're not going to go into detail about it. I'm just going to show you the equation and explain to you what the important components are. And really,
Keith, you've got 15 minutes.
Really?
Yes.
I thought I had until 5:30. Sorry. Okay. Thank you.
No, 4:30. So you got 15 minutes.
Okay, fine. So those are the elements that thanks for that warning anyway, that are part of that. And you go all the way through this, and then you have the weighing error and the preparation error. These are the bits where I come in and make sure that this component is effectively handled as well. But these are the bits we look at. We use the microscope, we measure this, and again, using a microscope, and I just want you to concentrate this middle table here. These are measurements of gold grains in samples. And you'll find that when you measure the grains, one grain only was 400 microns in diameter, whereas 1,488 grains were around about 15 microns. Now, when we totaled up the grains and we calculated the waste based on grain volumes, we found that 60% of that sample was just one grain. Now, you put that into a fire assay, and you've got those 2 grains in there, and now these little diagrams all, excuse me, these little diagrams all represent one pulp, a 30-gram pulp fire assay pot. So, in other words, you're taking 30 samples out of here, but only 2 of them are going to have those large gold grains in. So, only 2 of them are going to show grade, and all the rest don't. Again, this comes to making sure that your sample is homogeneous. So we go through this process, and then we come to the concept of what is a sample. There's a lot, a sample, and an increment. I'm not going to go into the detail of it, but a lot is the truck or the mine or the piece of coal or the bag of RC, the meter of RC material that you take a sample from. And the increment is every stage when you take out of it. So that truck could be a lot, that front end, that pile of material that you're blending is a lot. The digger, this is sulfide concentrate going for assay, that's a lot. There's a lot. There's an increment that is spade. There's a sample there on the RC materials, a lot sample. This is RC grade control drilling, a lot and an increment. And the same applies to diamond drill core. And this is the important bit. These are what's a lot, what's a sample, and what's an increment. And it's very much more difficult the concept to understand because the materials often split and cut. And this is the bit. So every one of those little blue lines on these core trays is a break, is the beginning and the end of a sample. But there, the core hasn't been split, there it has been split. So that sample there which is sent to the laboratory, the other half of it stays behind. So this is a case where the sample is split in half. And is it really an increment? No, that doesn't really apply to diamond drilling. But the point is how that sample is taken and what that represents in drill core is very, very important. And drill core is not homogeneous. So then you have all these components of it. There's various, I'm not going to spend much time on it, other than to show that it's a very complicated set of data that goes into it and what these errors are. But the point is that fundamental sampling error, and that's what that equation is about. I'm not going to go into detail. It's not important at this stage. It's part of the inherent variability of the material being sampled. And there's a loss of precision inherent in the sample due to chemical composition and particle size distribution. Every ore body is different. Every single ore body. And the more variable the mineralogy, the more complex is it, and the difficult it is to sample and understand. Particle size distribution. The sampling error can be reduced by maximizing the sample mass and reducing the fragment size and minimizing the steps. But we have a problem. If we maximize the sample size for gold assay, for instance, we won't do a decent fire assay. So that, now the sample's too big. So you've got to optimize the sample size rather than maximizing. This word, maximizing, the old-fashioned word. When another lab auditor and myself, actually 3 of us got together one day and we said, guys, this pressure that has been put on the gold assay process by maximizing the sample size to make it more representative cannot be done because you're not going to fuse the sample properly. In other words, the assay is not going to be done properly. So it's optimizing. This is one of the pulverizers that used to be used. They are smaller. It's made by the same company that uses that most of the labs use. Your sample is put in there from the drill rig and is then pulverized to bug dust. But this thing was so big and so complicated, so it was designed so they used a big sample. But it didn't work because what it did was so heavy that when you slow it down, heavy minerals like gold and platinum, when this thing slowed down, it acted like a panning device because it sit on springs. And this is so heavy that when you slow it down, it will be slowed down gradually, otherwise the motor will get damaged. And in that process of slowing it down, it was actually acting like a pan. When you pan for gold in the river. So what happened was most of the platinum and most of the gold and all the other heavy minerals slowly worked their way to the bottom. So the sample is no longer homogenized in that particular pulverizer. This is the whole thing. It's got to stay homogeneous. It's got to stay representative. That's why we have 2 components here. One is, and this has to be remembered when you take any split diamond core, in particular diamond core. RC drilling doesn't have quite this problem, but then you can't see the geology from RC drilling. Bear in mind, RC drilling gives you a better homogeneous sample. Diamond drilling gives you an idea of how the ore and the geology of the ore is. So it often, on many projects, we recommend that you do a combination of both, treat both data sets as separate, and then see if you can merge the 2 data sets. Compositional heterogeneity. There are 2 components of it. This is how heterogeneous the ore is. You're going to reduce that heterogeneity before you send the sample into an instrument to analyze it. This reflects the differences in the internal composition between individual fragments of sampled ores because of the way they're constituted and composed. Let's say you've got epithermal gold vein, or you've got calcite veining in a copper deposit. That veining is not coherent. Sometimes it's a nice angle in the core and you cut through it, other times it runs up the core. The way you sample that material is very important, but you cannot change the sample, the way you sample the core every time the sample direction changes. You've got to keep the sampling of the core and the methods that you use to sample the core the same. And your logging, your core logging has to be accurate enough to actually identify those areas of heterogeneity. So when you get the data in your database, you precisely can relate the assay to the way the sample was when you took it. And then there's distribution heterogeneity. This is normally bigger in scale. This represents the difference in average composition of the lot from one place in the next in the lot. So in other words, this is a bigger entity. So a lot in this case would be a portion of your ore body. And is responsible for irregular distribution of grade and values in groups of fragments of broken ore. The distribution heterogeneity can be influenced by large differences in density and fragment composition. And measurement of ore densities are another thing That is very important with sampling core. How do you actually determine the density of the core? That's the bulk density. And that is another whole area which I haven't got time to talk about. So the total eliminating the fundamental area is not possible because the goal is to minimize the fundamental area as much as possible. In conclusion, what I'm going to do is I'm actually going to go here and just point out by using the mine face and the core tray, it's exactly what the problems are. Here is a mine face. What these guys are doing, this is at the Kuru government in Fiji. And they didn't even understand their problems. They've been doing this for years. This is a sampling channel from there to there. Imagine it's a piece of drill core. You see these black areas? They're barren. That's got gold in it. And see who's got across? No gold. So what they were doing is they were taking a sample there, not sampling there, then sampling here. Well, guys, that's your mine face from there to where this guy's feet are on the ground. That is what goes into the plant, not just the materials got the gold in, the light colored material. That is one of the big problems I've had many mines. They only sample what they think is great. You've got a sample of what you're actually going to put into the plant. So this dilutes the ore that's in the plant, and that goes into the plant. So you need to know that. Now, look at these. This is a single borehole. This is borehole here. Is right near the surface at 5-6 meters. This is 85 meters in the hole, and this is 132 meters in the hole. Look at the difference in ore. But I'll tell you something. This is all stuff that's going to be mined. I haven't actually included a bit of ore here. The ore is in the adjacent trace, but I wanted to show you here is how heterogeneous the ore is. And there's only small amounts. This is copper sulfide. But here it's no longer copper sulfide. That's copper oxide. This is the supergene zone. This gets treated with heap leach. This goes into a flotation plant. So this is the same borehole. So you're going to have to look at you've actually got two boreholes. You've got two ore bodies essentially in the borehole. The average grade here is about 2 grams a ton. The average grade, sorry, not 2%, this is copper, and the average grade there is 11%, which is supergene. So they treat it differently. This thing, your recoveries are going to be of order 75%, which is heap leach. Then this, your recoveries are going to be of the order of 98% because it's a flotation. And all these concepts have to be taken into account when you're sampling the score for analysis. And how you submit that. How do you cut something as soft as this in half, and this you're going to saw in half? These are things that are so important when you're looking. So that and that are identical. And the same things appear with blast hole sampling. Look at these blast hole samples. These guys are using a spade. That just come out the blast hole as well. But that's left on the ground. He's only sampling the fine stuff because that's all that fits in his tray. That's not how you do it. These guys are doing it correctly. They've got a device that's designed to take a sample. Here, they were actually using a cyclone on an RC rig to actually sample, and then they just put a spade in here and took a sample. That's not the way to do it either. So these are different approaches. And so I just want to leave this. Oh, sorry, but the bit I want to go to is diamond drill sampling. Now, this very complicated slide covers the whole of exploration drilling that I've actually drilled. All these are my photographs, every single one that I've taken. The top row of photographs is.
But 5 minutes, Keith, then we have to shut down.
Okay, the top row is diamond drilling. The next row is reverse circulation drilling. And the next row is blast hole drilling. Every one of these projects have got a different problem. This is in Siberia. These guys had already RC drilled and they were infilling with diamond drilling. But when I went there, I wanted to know why the core trays are in such an untidy mess. This is your sample. That's got to be properly organized. Here, they were dropping core into the mud. It's rainy season in DRC, the core in the mud. If you look very carefully, you see there's a bit there, there's core everywhere. That doesn't happen. You're not allowed to do that. Here, the drill rig has been put up on the edge of a cliff. So they're actually sampling on the edge of the cliff. So that means there's no section there. They should have stepped in and drilled away from the cliff. Here, it was a drilling operation that was being done properly. This, they were sampling correctly. They were using all the correct processes required for sampling. Yeah, RC, these guys are using cyclones. Every one of these cyclones, the sample wasn't properly taken because Here in this case, the sample goes directly to the middle of the river splitter. They make dust. Here, again, it was dust. This project, I was called from Johannesburg to come and stop the dust by the farmer. Our own geologist hadn't noticed that he's losing half his sample. You can see, look at the white color of the ground here. This is grew. Yeah, now it's blast hole sampling. These two projects are good. These guys are not doing blast hole sampling. They had RC rigs in the pit. They were doing it easy to sample. Yeah, again, they were sampling using a RC rig. And here at Cripple Creek in Colorado, they're using the blast machine. And we found that these guys weren't doing it properly. This is correct, this is correct, and this is correct. And the final slide requires is what happens when you audit these processes. It's based on the approach that we use to audit laboratories. It's done on some 300 laboratory audits that I've done in the last 25 years. I've designed it in exactly the same system. It's a sampling operation, and it has to be audited so that it includes the QA/QC applications. All rigs and operation drilling are to be included in the audit. The evaluation of the drillers and their teams, their workshops, their stores, all core handling and transport, core marking and measuring, core logging, core splitting, core sampling, insertion of QA/QC items in the core, the photography, the bulk density measurements, the core storage, and a whole lot of things are even left off this list. It's a monstrous program, and it's done by an external auditor like myself once or twice a year, but the rig geologist does all his rigs at once a month, and it's written up. And the key component to all this is an in-house manual protocol. So the entire process is done the same way year after year after year. And if you change it, it is documented with a new set of protocols, and the dates of the change are put in the database so people know when the old data was thrown out and when the new data was brought in. But it's still measuring the ore body. You just have to make sure that everything matches and that you knew what you did. So when things change or there's an indication that something's wrong, you can go back and check it. Thank you very much.
Thank you very much, Keith. Much appreciated. We're going to have to get you back to do a much longer course.
It's a long course. It's 5 days, and it's workshops, and it's working at night. And I don't do it by Zoom. It's got to be done hands-on.
Yeah, we'll make a plan with that.
Yeah.
Okay. Just before we shut out about a minute or so, just finally, a reminder of the assignment for those of you who wish to get CPD credits. The recording will be on YouTube, and we will send you the recording link and the PDFs of the presentations.
Okay.
So with that, everybody, thank you very much for your time today.
Tanya, can I just ask one more question? You asked you want copies of mine. Can I leave a couple of extra slides in that weren't presented today?
That would be perfect. That would be absolutely perfect if you could do that. Yes.
Okay. Okay. Because there's a whole section on how to select a laboratory and how to connect the laboratory to your sampling, which we never have time to talk about. But I'd like to include it.
No, that would be great. I think everybody would appreciate that. Well, yeah, I hope the day has been useful for you, and we'll see you again at another GSSA event sooner rather than later. Thanks, everyone.
Thank you, Tanya.
Bye.
Thank you. Bye-bye.
Thank you.